So, okay, with that, we'll get started. So our first speaker is Paulo Nussesnzveig, who's actually the pro-rector for research here at USP. So we're, again, very happy and delighted that he could join us. He's actually also a participant for the whole meeting, but as an administrator like me, his time is a little pressed, so he will join us when he can. Anyway, as it happens, his father, Moises Nussesnzveig, was here at USP and actually worked with David Bohm. So we're going to hear a little bit about that from Paulo Nussesnzveig. Paulo?
I think I'm probably in a kind of a triple capacity here as a provost, pro-rector for research and innovation. So in that capacity, I'd really like to give you the warm welcome to the university, to the whole of the university, as a physicist, quantum physicist, and also as the son of a physicist. Probably it's the third capacity which will be maybe most interesting to you. I'd like to say a few words on that. Myself, I am not a specialist on David Bohm, definitely not a specialist on Bohmian mechanics, though I appreciate it, and I have a few friends, one of them is in the audience here, who have been working on this. But maybe I should start by saying that even if I am not a specialist, definitely David Bohm tackled what was at the time one of the greatest problems in physics, one of the greatest challenges in physics. And you all know certainly much better than me what he had to face in terms of his political activities or beliefs. Kind of weird to say at this time, you know, that in a country like the United States, people could be persecuted by their beliefs. You know, that doesn't really make sense, right? In a country like the United States, that something like this would happen. Well, but also from the physics community. And I like a quote that I've mentioned at a few talks before, attributed to Oppenheimer. If we cannot disprove Bohm, we must agree to ignore him. This is something I picked up in a book by Louisa Gilder, very nice book, and she goes on to mention how much influence the whole conundrums of local realism and making sense of quantum mechanics were a triggering for John Nash's mental illness. She mentions that. So my father, Moises, he was a physicist. He did his training. He actually was probably one of the only persons in the University of São Paulo who was a student here without ever participating in the entrance competition to the university, the vestibular. My father was admitted to the university in the second year because he did his first year of undergraduate studies in Paris in math. And when he came back, he had to decide whether he wanted to go into math or physics, and he chose physics. At the time, this campus wasn't ready yet. It didn't exist. So it was in the town center that they had classes, Rua Maria Antônia. He had classes with Ernesto Hamburger, Amélia Hamburger, and they were all students of David Bohm when he was here in Brazil. He told me more than once what an experience it was to be a student of David Bohm, that not only was he a great professor, great mentor, but that during his classes, especially when he was addressing the issues of, let's say, hidden variables or something like that, he would say, well, do not pay attention to what the author of the book wrote here or there. He's definitely wrong in that, and he would refer to it in the third person, although they were using his book. So this is something my father told, many times, and actually Alain Aspect picked up on that. I'm not sure you've seen Alain's recent book on quantum theory. There's a footnote in which he mentions that he heard that from my father. I actually met Alain very recently and told him there's a slight mistake because he says that Bohm was in Rio and not in São Paulo. Alain promised me he would correct that. Maybe another part of the story, which I think we as physicists have to be accurate. David Bohm's experience here in Brazil was not, all good. And you certainly know even better than I do, but I read an account in our popular magazine, Ciência Hoje, about letters he exchanged with Einstein, complaining about the food. Can you imagine that? I mean, complaining about the food in Brazil? An American complaining about the food in Brazil? So he was complaining about the food, but not only the food, he also complained about his colleagues, people who were running the administration. Yeah, we have some trouble with that here at this university. And he was complaining that there were lots of struggles for power, for, telling people what to do, and that the faculty was even, not that good. But they, they had like the kings in their bellies and they wanted to be bossy with everybody. I would love to tell you that that story has changed completely at this university. We're still working on it. So my father, he did his undergraduate studies here, and that's when he was a student of Bohm's, and he was, in his later years, he was always telling me how much he was fond of David Bohm, and also that he thought that Bohm was not recognized for, probably what he thought, my father thought were his most influential contributions in plasma physics. I think Iberi Caldas will speak about that later on. Definitely the work with the Haronov-Bohm effect, which I think is also extremely inspiring in that it tells us, about a physical nature of a vector potential, which does not really have a classical analog. So my father was extremely fond, he was really an admirer of Bohm in all those aspects. Just probably to sort of conclude saying how coincidences happen in our lives. In the early 1990s, when I was doing my PhD thesis, my parents spent 5 months in Paris, and they, through the brother of Claude Cointanouji, Gilles Cointanouji, they rented an apartment in the 13th arrondissement from a guy named Jean-Pierre Vigier. And we, met him a few times related to the rental of the apartment. So life is made of strange coincidences, right? My father was such an admirer of Bohm, and to just end up in Paris and rent an apartment from Jean-Pierre Vigier was quite a coincidence. So I think, given my little knowledge of the aspects that are being discussed at this conference, it was most interesting to tell you a few of these anecdotes, and to say how much, really, to try to impress on you how much an admirer my father was of David Bohm. He was really influenced by Bohm, and I think a lot of his thinking in quantum mechanics, we all are very influenced by our early teachers in quantum mechanics. And my father was extremely fortunate to have a teacher who would not just quote from scripture, right? Even if he had written that scripture himself. I think this is a very powerful example to the critical thinking that physicists have to keep throughout their lives. And so this made a huge impression on my father when he was very young, and he passed a little bit of that on to me. Thank you.
Okay, at this point, I will turn things over to your proper session chair for the morning, who will be Paavo Piilkainen. Again, I apologize for the pronunciation there. Glad to hear it.
All right, so good morning. And I think are we having Chris?
Okay, so I need to find my screen to share. This one. First of all, I'd like to thank Bill very much for the invitation to the conference, and I'm really sorry I couldn't actually be there in person. What I'd like to do here is just talk a little bit about what it was like at Birkbeck in the 70s when I was doing my PhD in Bohm's group. It was obviously a great privilege to interact with David Bohm at Birkbeck, and it was, I think, quite an unusual place to be. So when I arrived at Birkbeck in the late 70s, there were two physics professors there. There was John Hasted and David Bohm. And they were both rather radical, to say the least. Hasted was a communist, peace campaigner, prominent folk musician, who was also a good great experimental physicist. And there was also David Bohm, also communist sympathizer at least, influenced by Marxist thought. And what was going on at Birkbeck just before I arrived was, in a way to me, quite startling, because they were carrying out experiments in the paranormal there. It was mainly under the guidance of Hasted, but also Bohm, who took I think, a more critical approach to it. But the aim was to see whether psychic phenomena were real, and if so, what this meant for science. So, in fact, they had invited Uri Geller and other parapsychs, whatever you call them, to engage in experiments there to see these effects could be investigated in a scientific way, to see if they were real. And if so, what did this mean for science? In fact, it was around 1974 that the investigations began in earnest. And I think the fact that Bohm was open-minded about these investigations was a clear reflection of his general approach to knowledge and human understanding in general. So no ideas for Bohm were going to be dismissed out of prejudice. Everything was to be considered carefully and taken as of possible value, and unless shown otherwise. So as you can imagine, in a physics community, this was highly controversial. And in fact, as late as 1975, Hasted and Bohm were defending their ideas and their experiments in the journal Nature. So both Hasted and Bohm, the two professors at Birkbeck, were social and political outsiders. And this really fitted with Birkbeck's intellectual tradition, which cultivated radical thought. Birkbeck's receptivity to alternative science was only matched by its long-standing encouragement of radical politics. From its conception, the college was a centre for Marxist social science. The common room at Birkbeck was dominated by great radical scholars such as J.D. Bernal, Eric Hobsbawm, Robert Browning, Roger Penrose, possibly less radical than the others, was also there in the early days and occasionally took part in discussions with Bohm and Hiley in the common room. Maurice Wilkins at the time was interviewing David Bohm for a biography he was planning to write. Clive Kilminster from King's College was a regular visitor, and actually turned out to be my external examiner later. And on one occasion, I remember a very notable event when Clive Kilminster had arranged a seminar by John Bell, and of course everyone from Birkbeck in the theoretical physics area went down to listen to that talk, which as usual was a model of clarity and simplicity while still getting his ideas over very effectively. Jean-Pierre Viguier, of course, who worked with Bohm in Brazil and published with him there, was also a regular visitor. And in fact, it was this visitor which actually led to an invitation to me later on to work with Bohm, to work with him, Jean-Pierre Viguier, in Paris, which was really great experience as well, because I'd gone from Bohm's university to the institute where Louis de Broglie himself had worked. And I always remember, I don't know if any of you have visited Viguier, but when you visit him, it's always the case that you're invited into his room, and then he says, sit in de Broglie's chair. So he had this leather chair in the corner there, which belonged to Louis de Broglie when he was still active. In fact, he was still alive when I was there, but he was very ill, and unfortunately, I never got to meet him. So Jack Sarfati, some of you might know, was also a regular visitor. So there was a constant stream of people from all over the world, from all different disciplines, who would come, may or may not give a talk, but certainly they would spend time in discussions with David Bohm. But in spite of all this radical nature of physics at Birkbeck, it kept a very English tradition of afternoon tea at 4 p.m. in the physics library. Tea was brought in on a tea trolley. Staff and postgrad students would meet for informal discussions over tea and biscuits. But although traditional in respect of tea, Birkbeck physics presented a fundamental challenge to orthodox physics. And as I've alluded to before, Hasted and Bohm had a radically different view of the nature and purpose of science and the way in which it should be carried out. So what else was the context back then? Well, John Bell had published his paper in 1964 on the EPR paradox. It's well known that Bell was an important advocate of the de Broglie-Bohm approach. After all, as is well known, he was stimulated to produce his inequality through consideration of the non-local character of de Broglie-Bohm theory. And it's well known also, it's been discussed previously at this conference, that the idea of using spin correlations to test EPR effects originated from David Bohm's quantum theory textbook. Obviously, the singlet state was known and used before, but it was Bohm who really brought this to the fore as a way of exploring the non-locality, and of course led to all the experiments. In fact, again, part of the context, Rob mentioned this yesterday, one of the first experiments that was carried out to test entanglement was actually carried out at Birkbeck by Wilson, Lowe and Butt, published in 1967. And they were testing the idea of spontaneous localization, the idea that entanglement would be limited by distance. They found that there was no localization up to 6 meters, which was the limit of their experiment. As Rob said yesterday, Aspect had a bigger lab and could do more, although their experiments were actually rather different to Aspect's experiments. So Bohm and Hiley had discussed Wilson, Lowe and Butt's results in their 1975 paper, as Olival also mentioned yesterday. But apart from recognizing the importance of non-locality in quantum mechanics and the action of the quantum potential in mediating this non-locality, No one had really worked on Bohm's 1952 theory, and certainly no detailed calculations had been carried out. And so 11 years after Bell had published his seminal paper, still nobody was really working out the details of how Bohm's theory would work. In fact, there was little interest in Bohm's 52 theory at Birkbeck at the time I went there. Bohm and Hiley were pursuing the idea of the mathematical description of a deeper underlying process from which space-time and quantum theory would emerge. They saw the de Broglie-Bohm theory, if it was mentioned at all, simply as a staging post or as scaffolding that could be removed when the new theory emerged. So it was the development of these ideas of pre-space processes and the search for their mathematical description that was the focus of the work back in the 70s there. So at the time I arrived, Bohm was deep into the analysis of the foundations of quantum theory and of knowledge more generally, and indeed of the nature of being. He was further developing his ideas about order, wholeness, and the implicate and explicate order, and the search for a formulation of these ideas in mathematical terms. He was also working out his ideas around dialogue as a method of making progress, the nature of consciousness, and spirituality. So it's clear from all this that Bohm was not a naive realist. Reality was not something that was out there in a definite, finished, well-defined form, a form which we could gradually approach through careful experiment and investigation. In fact, Bohm rejected the established philosophical binaries of rationalism and empiricism, subject and object, knower and known. He talked of the qualitative infinity of nature, which of course has echoes from Marxist philosophy, and the multiple ways in which our participation as a part of nature could explicate different worldviews. So he distinguished actuality and reality. Actuality was all that exists, unknowable in its entirety, but we could explicate different worldviews by our actions as part of this actuality. So Bohm was critical of Bohr and Copenhagen. That was obvious from interactions with him, but he was always sure to bring out those aspects of Bohr's writing that he considered insightful. For example, Bohr's thoughts on language and human knowledge more generally, the subject and object distinction, I think were highly valued by David Bohm. It was obvious that Bohr was not a naive realist either. And I always remember at one point when we were talking about these things, David Bohm said, well, he'd often come up with these sort of aphorisms or statements. And this was one where he said, well, you know, physicists, they talk like Bohr, but they think like Einstein. And, you know, I think that's from my interactions with various physicists, it's true. If you press them, they retreat to the Bohr line. But actually in casual discussion, you can see they really are thinking like Einstein. So this was the intellectual context in which I arrived at Birkbeck, and I was immersed in this world. I have to say that I was a Bohrian back then. I'd written a dissertation at Cambridge about Bohr's interpretation of quantum mechanics, in which I explored his deep philosophical ideas, complementarity, arising from the indivisibility of the quantum of action, the arbitrary division between subject and object, not just within physics, but within all aspects of human knowledge. And I planned to write a thesis at Birkbeck that explored these philosophical ideas in the context of quantum mechanics. Things changed, of course, but half of my thesis was still about Bohm's philosophy and his opposition to the domination of the ideas of reductionist mechanism, both in science and in philosophy. So what was it like there? Well, it's a very unusual place to be. There was no organized Bohm research group at Birkbeck. There were no research council grants to support Bohm's work. It wasn't recognized by the establishment, and as we heard yesterday, still suppressed, for example, by the journal Nature. I think I was the first British Science Research Council PhD student in Bohm's group. His group was an eclectic and diverse thing. He attracted visitors from all over the world in different disciplines, keen to discuss their own and Bohm's ideas. There was no regular seminar program and no focused research program. All of the other people doing postgraduate work, loosely in Bohm's group, were part-time. The theoretical physics room was empty during the day, apart from me and the few doing more orthodox research with other faculty members. But it really came alive at night, with people turning up at random on different days of the week to discuss their work and how this in some way related to Bohm's ideas. And so they'd come and talk about category theory, chaos theory, or whatever. There was such a diverse range of ideas going on there. Others trying out some aspects of mathematics to describe this fundamental process that Bohm believed was underlying our experience of the world. So there was Fabio Fescura, who was working with highly on-Clifford algebras and quaternions. Peter Holland was there. He joined Birkbeck a year or so after I arrived. He was also doing his work in the Clifford algebra area, and he too had no interest in the 1952 work at first. It's interesting that this radical nature of the college there seemed to attract left-leaning students. And I can remember, I suppose somewhat in an embarrassed way, that we set up something called the Association of Socialist Physics Postgraduates in order to further our ideas there and to make sure that the faculty at Birkbeck were not, well, perhaps less said about that, better. So it was a stimulating and lively environment for sure, but ultimately bewildering for someone looking to write a PhD thesis, as I was. I was told that at Birkbeck, you weren't given a problem to work on, you had to find your own. Highly warned me about this before I arrived. And also, he warned me that I was not likely to make a career doing a PhD with David Bohm. So, as I mentioned, Birkbeck was an evening institution. The undergraduates were all part-time, so Bohm gave his quantum theory lectures in the evening. Attending these was one sure way of interacting with Bohm. They were a very different kind of lecture. Sure, he would refer to a battered manuscript of his quantum theory book and scrawl some notes on the blackboard, often saying, well, you know, if I'm not mistaken, he was not a hugely confident lecturer. But soon, after writing something from his book on the board, he would be expanding his thoughts about the implications of quantum mechanics and its problems. So it was just like Roger Penrose has described Bohm as starting off with something very precise, like a, delta function wave packet, but soon afterwards spreading all over the place. I remember one time during these lectures, he demonstrated to us that Hamilton in the 19th century could have anticipated quantum mechanics. So he believed in dialogue and would listen to what anyone had to say and to reflect on it. Sorry, I've been forgetting to move this on. So Bohm's physics intuition was staggering, as I think anybody who had interacted with him would see straight away. He could see how a particular suggested approach to a problem would work out without doing the detailed maths. He once told me that the way I was working on something wouldn't work out. He told me why. I didn't quite get it, but several days later, I realized, oh yes, he's right. Another of Bohm's memorable statements, which stuck in my mind, was one when we were talking about understanding quantum theory, when he stated, well, you know, before you can understand the meaning of a theory, you have to have a theory of meaning. And, you know, this very much indicates the way Bohm used to think. Another thing that stuck in my mind from those years, almost 50 years ago, was when I was reading Bohm's Causality and Chance in Modern Physics, and I was talking with Bohm about this. He suggested, well, why don't I go and read Lenin's Materialism and Empirio-Criticism? Well, I think, you know, the story about how we got together and produced the two slit experiments, trajectories, is fairly well known now. And I think, you know, having done those trajectories, we then thought about what else could we do. And, you know, any introductory quantum theory book will deal with simple square potential phenomena. And that was the next focus of the work. And in fact, I made some 16-millimeter movie showing just how Bohm's theory worked for quantum tunneling, for example. And I think, you know, these pictures that we produced back then, I think had a very, for me anyway, a very strong, gave me a very strong intuition about quantum mechanics. And, but I began to understand why Bohm wasn't talking about his work so much anymore when I started presenting this stuff at conferences, and, you know, was met with, first of all, incredulity. I think not many people had really thought about Bohm's work, but also then you had a whole list of objections, criticisms, which the only thing they did was show that the person who was making them hadn't really understood Bohm's theory or really worked on it. And so, you know, Bohm didn't have an interest in propagating his 1952 theory. And I remember him, as I talked to him about this, he said, well, he was tired of being dismissed for no good reason, tired of people rejecting his theory without studying or understanding, tired of rebutting criticisms that were naive or otherwise unfounded, and tired of being ignored. So, well, okay, so I think I'm obviously run out of time here. But I believe that, you know, those images that we made in those movies back then really did help rekindle Bohm's theory. And I think just, you know, Bohm's theory wasn't just another way of talking about quantum theory. You could actually do stuff with Bohm's theory. You could actually do calculations, work out trajectories, and so on. I think, and since that time, of course, many people have used Bohm's theory in a variety of different ways. Okay, so yeah, so I think I've said all this. Perhaps just finish with showing you that movie, which I referred to. So this was made in 1981. It's a bit blurry. The digitization of it didn't go so well. But what we see here is a wave packet approaching a barrier, which is the dashed lines. The solid line is the quantum potential. The stars are possible particle positions, and their height in the frame is the energy. And so you can actually see the particles tunneling. Okay, so this mysterious phenomena was one that you could actually make a movie of, and you could watch it actually tunneling through the barrier. Okay, all right. Yeah, I did have rather more to say, but I think I better stop there and let the rest of the conference proceed.
Thank you, Christian. We'll meet you again on Friday.
Yes.
And you have a 45-minute talk then on this. What have we learned from the Bohm trajectories, right?
Yeah. Okay.
Yeah. Thank you very much.
Thanks. Everybody, please take your seats, and I think we can continue. Okay, so welcome back, everyone. We're going to continue this talk about catching a quantum tunneling particle in the act. We're talking about quantum tunneling, as I've already introduced. And the idea is that while we have this idea of a particle picture on the left side and a wave picture on the right side, the essential insight of Bohm, as described by this nice review paper by Norsen, it says it's not particle or wave, it's particle and wave. So you have both the particle and the wave ontology in the Bohmian picture. And I really like this picture because if I see this space-time diagram, what he says is that you have the waves coming in. You have the incoming wave, you have the reflected wave, and you have the transmitted wave. But it's the combination of these waves that guides the particles. So the lines are actually the particle trajectories being guided by those waves. And something very cute happens. He says the first few of the leading ones, the leading particles, the first 1, 2, 3, 4, 5 of these particle lines, they're the ones that make it through. So the leading edge makes it through. The back edge, the ones that arrive late, they're the ones that get reflected, okay, in the Bohmian picture. So I think that's quite cute. And then something else also very interesting happens, described in this picture here. He says, look at this accelerating character. So what happens is that if this is a space-time diagram, here I'm going fast. These guys in the middle here in this triangle, they're going slow, and then they get reflected going the same speed as they have to be. So in order to go from slow back to the same energy it had, they have to accelerate through this classically forbidden region. So they actually speed up as they go through this physically classically forbidden region. And indeed, Norsen points out, indeed, the mere presence of the trajectories here reflects the highly non-classical nature for the law of motion. And of course, the Bohmian reasoning for why they're even allowed is because it's not just the potential I drew that's active, it's also the quantum potential that we have to think about as well. Okay, so this is the Bohmian picture. I wanted to kind of give homage because this is a Bohmian conference. But I want to go further. I want to do something deeper, I think, than Bohm did or any of people in quantum tunneling do. And just a few words about, we were talking in the coffee break, very often an old problem in quantum mechanics is the question, how long does a particle spend in the classically forbidden region? And so there have been lots of theory and experiment over the years. This is in some atomic hydrogen experiment in Nature. This is another paper by Ephraim Steinberg, my friends in Toronto's group, measurement of the time spent by a tunneling atom within a barrier region. So people have been worried about this time problem for a while. I simply mention it to say, that's not what I want to talk about. I want to talk about something new and different and exciting. Okay, so what we're going to do is we're going to try to catch this tunneling particle in the act. And so we're going to use measurements to investigate the tunnel barrier occupation and rate for different measurements, types of measurements, and see if we can see what's going on, lift the veil, so to speak, as this particle is sneaking its way through that classically forbidden region. And the way I want to motivate this talk is with the following puzzle. And if you forget everything else from this talk, just remember this puzzle I'm going to give you. There's Lev Weibin. Lev Weibin likes these little physics puzzlers. So in the spirit of Lev Weibin, I'm going to give you this problem. A particle does not have sufficient energy to classically exist in the forbidden region. It's in some kind of, it's in a virtual, in quantum mechanics we say it's in a virtual state. But what if we measure to check if the particle is in the forbidden region? According to quantum mechanics, the answer must be provided to that measurement. The measurement will tell me, yes, the particle is there, or no, the particle is not there. If it's not there, then tunneling cannot happen. If we accept the premise that to go from A to B, the particle must go through the intermediate region, then I kill the tunneling effect. On the other hand, if I find it is there, I just told you it didn't have enough energy to be there. So if it is there, where does the energy come from? So either we kill the tunneling effect, or we're creating energy. This is the kind of puzzle that I want to pose to you. And the rest of the talk will be kind of fleshing out these various scenarios. Okay. Good. So the way we approach this problem is I wanted to give a experimentally realistic way of doing it. And so we're going to take a kind of discrete version of it. So what I've proposed here is the system we're going to be considering. And this is a system of 3 quantum dots. So these are isolated systems which have a discrete energy level in them. So these are typically done in mesoscopic quantum systems. And you have these 3 different quantum dots. And the idea is that the two outer ones have a given single particle energy, but the middle one has a detuning, a delta E, delta delta, above that energy. And so if I, for example, apply bias between a source and a drain in an electrical circuit, I can have a tunneling process where I go from the left dot, left lead to the left dot. But then you might say, aha, that doesn't have enough energy to go any farther because it's detuned. But we know from quantum mechanics you can have a co-tunneling process where you virtually excite this level and then de-excite to be over here. Okay, this is called co-tunneling in mesoscopic physics. And then you exit to the right, creating a current. Right? And so this is the kind of, so this is what I call the discrete version of tunneling. And what I'm going to be doing to check if the question I want to ask is, can I catch that particle in the virtual state? And the way I'm going to try to assess that is I realize this particle has handles on it. In particular, it has a charge, if it's an electron. And so I can use the fact that it has a charge to create a capacitive coupling to another electrical conductor. We call this a quantum point contact. And the current that passes through this quantum point contact will be sensitive to the presence or absence of an electron on this central dot. So by examining the kind of current flowing through this device, we get a hint as to whether or not the central dot is occupied or not. So this is a little bit just describing the details of it. I have a left ohmic reservoir on the left. I have a right ohmic reservoir. There's the different definitions. I have a hopping rate, a tunneling rate between the dots omega. I have the energy detuning delta, the epsilon of the left and the right dots, and the tunneling rates left and right, gamma left and right to the back. Okay, so that's defining my notation there. And the central message is that this central dot will act like a discrete tunneling barrier. Okay, so the Hamiltonian we have just for the isolated system in the middle, the 3 dots, I can write down with fermionic operators. I have some epsilon, dd dagger, d are fermionic operators here. So this is the occupation of these 3 different dots. And then I have hopping terms that take me from left to C, L to C, and C to R, but no direct hopping from left to R without going through C. And that's the critical thing I want to have. In order to go from left to right, I must pass through C. That's what my Hamiltonian is telling me in this model. Okay. And so the first part of my talk will be when these rates omega are relatively small compared to the other parameters in the system. We call this a weak hybridization regime. So the central dot has a virtual state, the so-called co-tunneling regime in mesoscopic physics. Later on in the talk, I'll be talking about strong hybridization, where these omegas become very large, and then other interesting effects appear. Good. So a word or two about this detector here. So this detector, this quantum point contact, as Marcus Bodeker taught us, the conductance through a transmission through a device is proportional to the transmissivity or transmission of the device in the scattering sense of the word. And so we say the transmission coefficient depends upon the central dot occupation. We call it T0 if it's unoccupied, T1 when it's occupied. And so in the weakly responding limit, the measurement strength of this detector will be given by the difference of those transmissions squared divided by this quantity times the voltage and other physical constants. This just tells me the rate at which I can extract information about the presence or absence of electron on the dot. It's also an ensemble-induced dephasing rate. Okay, so this parameter gamma will enter in a fundamental way to our theory of measurement, describing what's going to happen in predicting the physics of this device. So little gamma is measurement strength. Okay, and so I can actually operate the measurement in two different regimes. I can probe either strongly or weakly. So a strong probing is if I check that the particle is there or not on a very fast time scale compared with tunneling on or off the dot. But I can also do very weak probing, so I basically get a noisy hint if the central dot is either occupied or empty, and this is of course following the pioneering work of Yakir Aronov, Weidmann, and many others. Of course, I've written way too many papers on this stuff over the years. So this is the weak measurement limit. And of course, we can go anywhere in between by tuning this parameter gamma. Okay, and I'm going to be interested in the so-called continuous measurement. And what I mean by that is I just simply turn this detector on all the time, and then I'm looking at what the current is doing as a effectively time continuous process. Of course, it's not really continuous because the current is made up of individual electrons, and so on a very short time scale, it's going to be jumpy. But on the time scales we're interested in, we have two different types. So one is the so-called diffusive quantum measurement, where the quantum back action takes on a diffusive nature, and the other is a so-called quantum jump measurement, and I'll give you physical examples of both of these. So a little bit about quantum measurement theory. What we can do is we can describe the physics of this device using a master equation for the central system, the three quantum dots. So I have that Hamiltonian I defined a few slides ago. This is the von Neumann term. And then additionally, there are Lindbladian terms that operate on these devices. So the first part is just going to be the jumping from the reservoirs on and off the reservoirs that's captured with this kind of Lindbladian form of the Liouvillean operator. So these are the jump operators into and out of the leads. So that would describe this first term. The second term is going to be given by L gamma, and that describes the influence of the measurement. So that will be the quantum point contact operating. So it takes this form in terms of formulas. Importantly, there's going to be a stochastic term here on top of this, and this is the so-called diffusive quantum measurement theory. And so this will be very important, the fact that this is a random process associated with the shot noise of the detector. And this operator that's associated with the measurement is simply going to be a projector on that central dot, whether the electron is present or absent. And of course, the measurement rate gamma appears as a prefactor to that. Okay. So this is a little bit about the quantum measurement theory that goes into the formalism. And then in the diffusive quantum measurement limit, we say that the detector acts in a weakly responding regime, so the difference between the two different transmissions is small compared to the average. And so, for example, when I write down equations of motion for the dynamics, this is the stochastic master equation. Here I write it in Ito representation. I just give you one element to give you a flavor of it. Here is the time rate of change of the central occupation of the middle dot. So it has a term related to the Hamiltonian of the system. That was the hopping rate gamma. And then there is this stochastic term that involves the measurement rate, the occupation, and 1 minus the occupation, and then this noise. Of course, the noise is coming from the noise through this detector that's being monitoring this system. Okay. And the results are, I'm just giving you some sample trajectories, so then we can iterate this. When I solve these equations, we take a particular realization of this Wiener process, and then that allows us to integrate this equation of motion. And what we find is we get trajectory something like this, okay? And so the occupation is either going to be something down here towards 0, then there's some stochastic motion up towards 1, some jitter back to 0, and so on. That's one realization. Here's another one, like in orange. It goes up a little bit, then back down, and so on and so forth. And so for the most part, you see, at least for this rate, gamma here is 5 times omega, so this is a relatively strong measurement rate. We see that the dot is either fully occupied or not occupied at all, typically. What we can also do is we can average over everything, and I can look at two different things. One is the steady state occupation on the ensemble. I should say it's not really steady state. It's really the ensemble occupation, rho CC. The other thing is how much current is flowing through that triple quantum dot system. I can measure this experimentally as a function of the parameters of the system. So one parameter that I can change, that's on this axis here, that's the detuning. That's how unlikely, how difficult it is to occupy that central virtual state. And then on this axis here, this is that gamma, that's the measurement strength. So let's first start, let's turn the measurement off, that's gamma equals 0. And then you see, as I change delta larger and larger, that the tunneling, that the occupation gets smaller and smaller and smaller of that central dot. That's basically showing it's a virtual state. And that's because the effective tunneling rate goes like omega squared over delta the detuning. So the larger the tuning is, the more unoccupied that state is, and also the amount of current that flows through the triple quantum dot system also goes down, 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 down as delta gets larger and larger because it's harder and harder to tunnel through that central dot. Okay, so that's that first axis. That's with no measurement. But now I want to start thinking about turning the measurement on. And let's look at the large detuning limit where I'm in the strong tunneling. As I start turning the measurement on, what happens, I used to go from almost zero occupation to suddenly start increasing, 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 and I saturate around 1/3. Okay, so suddenly before that the dot was not occupied, but with the measurement added, as I make it stronger and stronger, I occupy it basically 1/3 of the time. What's also very interesting to note is that the current, you see, first of all, it's very small, and I start measuring, the current actually increases, 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 then it starts decreasing, going down. And we call this effect measurement-assisted tunneling. So what's going on there physically is that here there's essentially no occupation of the dot. When I start measuring it, I start allowing the occupation to exist by the tunneling process, by the measurement process. I start occupying it. But if I measure too strong, I tend to localize the electron on the dot or off the dot, which then inhibits the tunneling. And so I have a local maximum as a function of my measurement strength. So this is a prediction we're making measurement-assisted tunneling. Because that's the ensemble average. Let me say something about what we call the quantum jump measurement. So in the quantum jump regime, what we do is we have basically now this detector itself is in a strong tunneling regime. Oh, sorry. Yeah, so now the detector itself is in the tunneling regime. So both of these transmissions are very, very small, but one of them is smaller than the other. Let's say T0 is much smaller, or so T1 is much smaller than T0. In this case, we say the electrons can only pass through that quantum point contact, or really the tunnel junction now, when the dot is unoccupied. So I'm essentially sitting here waiting to get an electron through this tunnel detector. Occasionally, I get a click. Essentially, electron passes through. When that happens, then we say the quantum jump occurs. So I start with the density matrix of the triple quantum dot system that looks like this. And then suddenly, I go over here. I put zeros everywhere I see a C. That's because I know that the dot is unoccupied. So therefore, anything with a C in it must be 0. And between the jumps, I have a different kind of dynamics. And we call this the quantum no-jump dynamics. And so I describe this as the quantum dog that did not bark, an homage to Sherlock Holmes. So when things don't happen that could have happened, we have to account for that in the quantum mechanical formalism. And so there's a deterministic conditional equation of motion that's given by this equation here. Okay. So combining those two jump and no jump processes, we're able to then give these kind of results. So this is an example of two different kinds of probing. One, the weak probing, when gamma is very small, 0.5 capital omega. And on the right, strong probing, when gamma is very large, 5 times omega. And what we see is that, first of all, note that the scale here, this is between 0 and 0.15. For omega t, goes from 0 to 5. And you see that there is a kind of oscillatory dynamics, but then the blue line are the clicks, the number of electrons you detect through that through the detector. Whenever there is a detection of an electron, you see there's a little discontinuity, there's a little jump in the quantum dynamics here. So there's a jump here, 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 and here, but with oscillation. So mostly it's oscillations around 0 with these little jumps, okay? But in the strong measurement probing limit, this is the result we get. Here is, now we have the full range, 0 to 1, and you see a kind of telegraph process up here. So again, so the blue line is the number of electrons we collect, so it's going from 0 to about 2,000 here, and you see there's this kind of jumpiness. So sometimes basically it goes between 0 and 1 with some jumps in between. And what's interesting is that there are some periods like up here where you get trapped in 1 for a long time. You're like 100 time units up here where you're in 1, you essentially get trapped. And so we say that after there are long periods of no jump and jump, electrons can get trapped in that central dot. So you get localization there. And so here there's a smooth evolution between the jumps. It's described by this equation that we derived. And so these are the two typical kinds of behavior that we predict. Okay, how am I doing on my time?
20 minutes with questions.
Perfect, perfect. Okay, I want to switch gears a little bit because this is kind of the foundational thing. I want to give a little twist on it because this is something I'm very fond of, is trying to take these informational things and make them maybe a little bit more physical, which is I want to talk a little bit about energetics. So, and I call this making the virtual real measurement-powered tunneling engine. So I want to take this kind of effect and then push hard on that puzzle I gave you earlier in the talk. Where does the energy come from, and what can we do with the energy that we find? Maybe if we have energy that's being created somehow, can we do something with that energy? And this is what we call the concept of the engine. Good. So what I'm going to do to make a little spin on this is I'm going to add to the system another reservoir, a third reservoir. Up here we'll call it reservoir C, that only couples to the central dot. And the job of this reservoir is to collect localized particles of higher energy to this terminal. And now I'm going to move to the strongly hybridized regime. So I want to let these triple quantum dot act like a molecule. So now omega is very small, so I can't think about left, central, right anymore quantum mechanically. I have to try to diagonalize this whole system so the whole thing acts more like a molecule rather than 3 weakly coupled atoms. Omega is large. Omega is large. Did I misspeak? All right, I apologize. We're all only human after all. Okay, so yes, so in this limit, yes, so we have the strongly hybridized regime. And so what I can do is I can take that Hamiltonian I showed you at the beginning of my talk, the one I wrote right now, and now I diagonalize it. I try to think about the natural excitations of the system, and I find there are 3 eigenstates. One is left minus right, that's the left electron on the left dot minus electron on the right dot. And these other 2 states, which are combinations of left, right, and C, with some theta parameters that depend upon the functions of the Hamiltonian parameters. I'm not going to write them out here. Now, the reason I call this state D is because the central dot does not contribute to it. And we'll see later that in deference to quantum optics, we're going to call this a dark state. And we can define some rates using Fermi golden rules, rates of tunneling into the bare tunneling from the reservoirs into the dots, capital omega. And I can calculate then, in this problem, what are the rates of tunneling into states D plus or minus, again with Fermi golden rule calculations, and I find these following results. The important thing is I can't tunnel from C, the central dot, to D, because remember D doesn't have anything involving C in it, but I can have these tunneling rates. This is the Fermi occupation F here, involving the various energies of the problem. So the energies of these states is ED, E plus, and minus. These are the guys that are appearing here in this energy guys, and these are the chemical potentials of the left, central, and right leads that enter into the calculation. Again, we can then write down some master equation for this problem that we can then solve numerically. involving these rates I just defined in this way. Here I've defined this x and y parameters are the real and imaginary part of the coherence between the plus and the minus states. So remember, I've moved from the left central right basis to this d plus minus 0 basis. So that's why these plus 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 minus dd things appear here. And again, I have some state C that's involved that involves this plus and minus states like so. Okay, so I do this calculation, I get this results, and now let me tell you what we find when we actually crank the calculator. So what we find, first of all, is that this is the current passed through into that central reservoir as a function of the parameters of the system. So this y-axis here, this is the detuning of the central dot. This other axis here, this is the energy of, I think, the central dot versus its chemical potential. And this is really the same thing, just written in another way. So yeah, so this is the chemical potential of the central dot. So mu actually is the bias across the triple quantum dot system. The important thing you see is I've drawn this vertical line. So when there's no bias here, so when I don't bias any of the leads, and I don't turn on any measurement, then no current can flow. And indeed, you see here, the current is 0 here. If I were breaking that, I'd be creating a perpetual motion machine, which is not right. But nevertheless, you see that even with no bias applied on any of these leads, by turning on the measurement strength from 0 to 0.5 to 1 in units of gamma, you see I start going up this line here, and I start generating current. I'm rectifying current flowing through this central dot because of the measurement process. So I'm localizing particles, I'm giving it energy. That's the hint, of course. Where does the energy come from? I'm not pulling it out of the ether. The fact that I'm doing the measurement is providing the energy to the system. And nevertheless, you see, again, that as I start changing the tuning, you can see where is the current maximized. Well, I can't make it really, really super big, but it's going to give the maximum current here around, in terms of the temperature, around 3 of kBT. Okay, so I can get this rectified current. I can then ask, okay, if there's a current, and I'm applying a current against the voltage, I can get power. So here is the power generated by this engine as a function of the different measurement rates. So I plot these different curves. This is a function of the bias of the central dot, the central reservoir minus the other reservoirs. This is the thermal bias here. This is the efficiency of the engine, and so on and so forth. Okay, so I'm plotting the various engine parameters for this measurement-powered engine. And then I notice also it can be we can use it as a refrigeration operation as well. Can run the engine backwards. And I can apply, rather than a voltage bias, I can apply a thermal bias. So one side is hot, the other side is cold. And I can plot then the cooling power. So I'm plotting the cooling power versus, again, the tuning on this axis and against the epsilon energy on that axis. And what we see is actually there are two types of cooling that can occur. One is an exchange-like process with a detector, which is similar to an absorption refrigerator. And the other is a selection of dynamical paths. We call that checkpoint cooling. And so I'll give you a couple of examples. So here's a little schematic of what's going on with the absorption refrigerator. What we do is we put we actually make the detuning negative in this case. And so what's happening is that I can take hot electrons off the reservoir. I can bring them into this central dot, which then escapes to the third reservoir here. And so this is like cooling the left lead by taking off the hot particles off of this guy and taking them into the third contact, which is acting like an absorption refrigeration. And then the other mechanism is what we call checkpoint cooling. And this is quite an interesting effect. So most particles that go from the left are detected when they're trying to virtually go through the quantum dot C and never reach R. Rather, they get localized by the detector over the barrier and then captured by reservoir C in this case. Okay, so in this way, the electrons that are injected from terminal R tend to cool it down, as we see in this blue regions here. So I'm cooling then the right reservoir with this selection of dynamical paths in this process. Okay, and then the one last thing is, as I mentioned, there was a dark state here. So the dark state was the anti-symmetric combination of the left and the right. So this is a little bit like when you're driving on the highway, and you notice that there's no gravel on the highway, but there's gravel on the shoulder of the road. It's because every time the car rolls over the gravel, it tends to scatter it off to the side. Something similar is happening here, that the detector is acting like the car is on the road, so it keeps measuring and measuring, is the central dot occupied or not? Are you empty? Are you full? Are you empty? Are you full? And so anything that involves the central dot eventually gets localized and then sucked out to reservoir C. So the only thing that's left behind is that dark state, that anti-symmetric combination of the left and the right dot, C. And so this is actually a coherent superposition of these the far left and the far right dots. And so because the detector mixes the plus and the minus states together, only the D remains behind. So you actually purify the state into state D. And so here we're plotting the purification as a function of the parameters. And so it turns out you actually want to detune relatively largely to get a good purification. So C is the purification as a function of the parameters, and you see when epsilon is sufficiently large, you get basically purification to 1 in this dark state. All right, so I think I'll end here. And so what are the conclusions? What did I find in this talk? The measurements can greatly influence the quantum transport in situations involving the virtual state. An electron does indeed populate the classically forbidden region when passing through a discrete tunnel barrier. It can be captured by having its presence revealed or not revealed by a nearby detector. The occupation increases with the measurement strength and saturates around a third, while the current reaches a maximum before gradually decreasing to 0. This is the so-called measurement-assisted tunneling. And then furthermore, the effect that I'm adding energy to the system by the measurement process can be used to create a heat engine or refrigerator from the measurement-induced energy transfer. And just one last thing, I'll advertise. So first of all, this is the paper. If you want to read more about the details of the paper. The first part, anyway, is on the archive, Capture an Electron in the Virtual State. My co-authors are my student, Alok Singh, my postdoc, Bibek Bhandari, and my longtime collaborator, Rafa Sanchez in Madrid. The next part of the talk should be appearing on the archive very soon. And I want to advertise, I recently published a book on quantum measurement, in which I actually talk about David Bohm and his contributions to the field in a historical first chapter. And I published this book with Cambridge University Press and my longtime co-author and friend, Irfan Siddiqui, where we talk not only about the formalism of quantum measurement, but also the practice of it as well, how to build quantum detectors, build quantum systems, how quantum amplifiers work. So if you're interested in the most recent advances in quantum measurement theory, I encourage you to check out my book, and thanks for your attention.
Okay, so do we have questions over there? Yes.
So it was a very, very interesting talk. I'm just, if I look at your conclusions, though, I have a feeling that the first two conclusions kind of contradict each other. And let me try to explain what I'm saying. On one hand, you say that the electron does populate the classically forbidden region, but the first conclusion says that the measurement influences the electron. So aren't those two, it's a kind of a complementarity principle.
Yeah, okay, so let's dig down a little bit. So indeed greatly influence the quantum transport. So indeed, one of the plots I showed is, what's the average, or let's say the ensemble average occupation as I increase the measurement strength, and so it starts to increase, right? And then the second conclusion is electron does populate the region while passing through the detector. It can be captured. And so another way of saying that is when we're able to check. So the whole point of this talk is peeking under the hood, trying to see, can I get evidence for what the electron is doing as it passes through. Some people might say maybe it never goes through that central dot. Maybe it goes directly from left to right. And one of the things we show is that for every time we do check, when the measurement strength is, say, non-zero, we do find there's evidence that it's either occupied or not occupied as it goes through that central region. Does that clarify what I mean by that?
But on the other hand, the measurement itself influences.
Yes, absolutely.
And so if the question that we're asking is what is the electron doing when we're not actually interfering with it, then we still don't know.
Right, and so that's kind of the beauty of the weak measurement paradigm is I can take the measurement strength down to epsilon, right? And so I can say something even when the measurement strength is, maybe it's not zero, but it's epsilon, and say something about the occupation of the dots. So hopefully that clarifies things, yeah.
Thank you. And what's your barrier height comparably to the temperature in the system? Because like in chemistry, there is always thermally activated way to go over the barrier and tunneling. And at low temperature, tunneling wins, and at high temperature, a standard, like Boltzmann exponent wins.
Yeah,
is it the same in your situation?
Yeah, that's a great question. And so so let me say, in the first part of the talk, I was mostly focused on the more fundamental question. So there we take simply temperature equals 0, so we assume that there is no thermal activation. But in the second part of the talk, temperature is present in the calculations. And so if you look at some of these plots, for example, here I'm plotting things as a function of the detuning over the temperature. So here the temperature appears explicitly. And so here I'm plotting it from 0 to 5. And so I see, for example, some of the cooling effects occur here around 2 or 3, and I think on the previous slide, yeah, also in this slide as well, this is like power over temperature as well, and rate over, yeah. And so so typically, here the power is small, but yeah, so typically the detuning, the interesting effects, usually the detuning needs to be larger than the temperature. So typically we take a factor of 5, say, bigger than KBT, right? So, good.
When you consider your weak coupling in between as a weak measurement, so the interesting phenomena happening when you condition on particular post-selection. So, do you see some anomalous weak values? So, maybe, for example, the weak value 0, it's a kind of anomalous if you have current. Can you get weak value 0 even you believe there is even the particle goes through? Or?
Yeah, so indeed, if you look at these results for the conditioned, let's go back a little bit. So here, in a sense, we're looking at the conditioned dynamics of rho cc based on the detector, or what's going on. What you could also do, which we didn't do, but you could also do is you say, now I make, say, a projective measurement, and I select a final state, and then look at what the average current is given that conditioning, which is exactly what the weak value would predict. So we didn't do that, and let me tell you why, Lev, we didn't do that. Because there was already a paper from Yakir several years ago who looked at this problem, looking at the question of what's the weak value of the Hamiltonian, or let's say a weak value of the kinetic energy when you post-select on a successful transmission. And as you might guess, what he finds is the kinetic energy weak value is negative, right? Which is sort of what if you know weak values, and again, you and I have both written like too many papers on weak values, you would have kind of guessed that. So I wanted to go in a different direction here. But certainly the question is interesting and valid.
Yeah. I'm co-author. It's a long time ago, the paper about negative kinetic energy. Yes.
Yeah. Okay, good. So you're also an author on this. Yeah, good.
So you said that when you were talking about energetics, that the measurement is actually adding energy, and that's what's getting you over the barrier in those cases. Is that still tunneling, or do you think it's still tunneling, or have you just given it enough energy that it goes over?
Okay, good. Yeah. So there are different interpretations you can make of these results. So one, I think, interpretation that I like, and then there's, we talk about, this is a conference about David Bohm. And so one of the things, even though I'm not a Bohmian, I don't think that's the right interpretation of quantum mechanics. I think it gives us a new way to think about quantum mechanics that's enlightening and shows us that there are multiple ways of looking at quantum mechanics that gives insight. And so I'm a big advocate of thinking about the same problem in many different directions. And so one way you can think about this problem that the point you mentioned, Kai, is you can think about that there is a virtual level, and if I don't do anything, if the measurement off, there's sort of a sharp virtual level it's virtually occupied. But when I start measuring it, you can think about it as a kind of dephasing process, and you sort of broaden the level, right? And so in that sense, by measuring it, you kind of kick the system around, and so you broaden the level, and when you measure it really hard, essentially the fact that it's detuned doesn't really matter because you're giving it, you're kicking it a lot. And so in that sense, the fact that it's still forbidden kind of becomes irrelevant in that point of view because you broaden the level so large, and so it becomes not so much a tunneling as more like an extremely broad level, but nevertheless, regardless of how you think about it, these are the predictions for the thermoelectric properties of this system in these different regimes.
So one more. Very interesting talk, Andrew. The question is somehow in connection with what David and Dmitry asked you before. You have said that in the first part of your talk, you introduced temperature. Okay, that's fine, because the temperature doesn't appear as explicitly. However, you have some noise, and the noise somehow has an influence on over the barrier. So, in this regard, I do agree with David that if there is an influence, how are we sure that that the barrier is not being modified, and therefore what we are seeing is not something that goes over the barrier, like classically?
Yes. So one thing at a time. So first of all, if there's no temperature here, let's go back. Let's go back. Oh, sorry, I'm going the wrong way. My apologies. Good. So if there's no temperature here, first of all, where does the noise come from? Because usually in these kind of problems, the noise comes from thermal sources. Here, what we're considering is the noise is coming from the shot noise of this quantum point contact. So when I apply a voltage between source and drain, electrons try to flow, and sometimes microscopic electrons make it through, and sometimes they reflect. And this is a stochastic process. We call this shot noise. It's like hailstones hitting on the roof. And so this is the origin of the noise in the system. So as I have noise in the current, I also have noise in the charge of this region, which creates, by the capacitive coupling, noise or fluctuations on this dot. Okay? And so indeed there is an influence, because on one hand I'm giving fluctuations to this system, but that's also the only way I can extract information. So there's a trade-off between disturbance, information, and quantum measurement. So I need to do something like that in order to extract information about the quantum system. But you're right. So you can think about, as I mentioned before, the fact that I'm doing this, you can also think about this as broadening this level, because I'm adding essentially noise to that system, and so I'm broadening it. And so you can think about, in some sense, there's a tail that comes down here that allows you to come through the system because of the influence of that noise. So I think that's also a valid system, a valid way of thinking about the physics as well. Okay, so but then you can tune that, right? You can make that really, really small as well, and so you can and that's the fun thing about this measurement theory, is that you can sweep out the whole parameter regime of very, very weak disturbance to a very, very strong disturbance.
Okay, and another question is, maybe I missed, but have you given the explicit form, functional form of the Limnat operators that you are using?
So here, so here are the Lindblad operators for the leads.
Okay.
That's on and off the leads. And here is the Lindblad operator for the measurement. So the measurement is a projector on the occupation of the central dot, okay? And this in the prefactor is the measurement strength. And so this goes in, this is the jump right here that goes into the stochastic master equation. And so this then tells you, so this basically is telling you, you're asking the question, is the dot empty or full? And this is the operator that tells you the answer to that question.
Do you know of any of similar study just in position space?
Certainly you can do other versions of this. So if you check out my textbook, there's a nice article about one of my group's custom formalisms is something called the stochastic path integral formalism of continuous measurement. We work out this stuff out for like a free particle and a potential, for example. But here I wanted to keep it simple, discrete, and also something I'm very keen about, something that our experimental friends can actually do. And so I've got a few experimentalist friends interested in trying to do this experiment. And so that would be really awesome as well.
Okay, thank you.
And now I think we have a Zoom talk by Valia Allori from the University of Bergamo in Italy, with the title Relativistic Pilot Wave Theories as the Rational Completion of Quantum Mechanics and Relativity.
Okay, here. Hello. So thank you very much for inviting me to this conference, and I really apologize for not having been able to come in person. Okay, so let me share my slides. Okay, so first of all, so this is a conference to honor David Bohm. However, I'm not an historian, so I'm not going to talk about David Bohm himself. I'm a physicist and a philosopher by training. So what I plan on doing is talk about the impact that Bohmian mechanics, also known as pilot wave theory, or the Broglie-Bohm theory, has had and is having and will have in physics. And so this is why the title is just a tiny little bit provocative, and a twist on something that sometimes it is said about this theory being totally in contrast with relativity. So I totally disagree. And provocatively, I'm going to argue on something about that. Indeed, this theory is the right way to look at if you want to reconcile quantum theory with relativity. Okay, so this is kind of a summary of what I will be talking about. So I will show how quantum mechanics and relativity are actually in tension. Quantum mechanics, on one hand, displays no local interaction, and however, it does not show any clear or obvious or explicit spatiotemporal entity to describe matter, what the philosophers sometimes call ontology. Actually, not sometimes, all the time. So if you hear this word ontology, I don't know how many philosophers are in the audience, but I mean, I know for sure that some of you know what the word is, but it's nothing strange. It just means whatever describes matter at the fundamental level. Whatever matter is at a fundamental level. So this is quantum mechanics. On the other hand, relativity is fundamentally local, and it is space-time based. So the claim that I will try to defend is that quantum mechanics and relativity are both incomplete, right? And this is, to me, is just the obvious take, right? That's why I said rational, right? I mean, if you were to think, right, to treat things from outside, you don't know anything about physics, and people tell you this is quantum mechanics, this is relativity, then what are you going to do? And forget about everything that you have taught, the fact that we have been taught from a certain type of teacher, that we have interacted with certain type of people, and so on and so forth. If you just told the facts, what are you going to conclude? And I think that what you're going to conclude in the most straightforward way is that first, quantum mechanics needs to have a spatiotemporal entity describing matter in space-time to adequately explain the phenomena and also to be compatible with relativity, while relativity needs instead some sort of a preferred frame in order to explain the experimental fact of quantum non-locality. And guess what? There is a already there to be developed theory that provide them both, and this is indeed the pilot wave theory in the relativistic version. It is indeed the minimal, simplest, most straightforward completion of them both. Okay, right, this is what I'm gonna do, but it's better if I actually do that and not wasting time more than I just did on this. Okay, so start with quantum mechanics. Okay, so if you've heard that quantum mechanics has a problem, the problem that you've heard about is the measurement problem, also known as the Schrödinger cat, which is straightforwardly put as follows. If the wave function evolves according to the Schrödinger equation and if the wave function provides a complete description of physical system, then the theory predicts unobserved macroscopic superpositions like the superposition of a dead and alive cat. This does not happen, so the theory is actually falsified, right? The usual textbook way out of this falsification is to say, no, right? When there is a measurement, right, then the wave function no longer evolves according to this linear equation. It collapses randomly in one of the terms of the superposition, the so-called collapse rule of von Neumann. Okay. However, people have complained, okay, yeah, if you care for a variety of reasons, this is not ideal. It's imprecise, right? It's unclear what counts as a measurement. So it's unclear actually when are you going to apply the rule, or you can say something like, oh, but isn't measurement supposed to be just another physical process? Shouldn't we be able to actually explain that in terms of the theory instead of postulating something external? Anyway, so in light of that, sometimes people say that there are certain, we should look for other theories which do not have this problem. And among them, we find de Broglie Bohm, DBB stands for that, or what other names you can call it, the GRW theory, Pearl, GRWP stands for the fact that also we never mentioned Pearl, which is the spontaneous localization theory, or we have the many words theory and so on and so forth. We have many others. Okay. However, I do think that this is not the deepest issue that quantum mechanics raises. I do think that it is true that people usually focus on the measurement problem. This is true for sure among philosophers, and that they say, oh, I need to solve the measurement problem and then everything's going to be fine. I don't think so. I do think that, and this is something that not only me, but many people before me have tried to point out, is that even if you do fix the measurement problem, you solve it, still it is unclear, right? Or at best, or there is no space-time fundamental entity which describes matter. Why? Well, because 2 out of 3, at least, of the theories that I mentioned before, are a theory that you can say are about the wave function or the quantum state, whatever you want to call it. And when you're talking about the wave function, this wave function cannot be seen as a real physical field oscillating in space, right? This is something that Einstein himself, and talking to Lorentz and talking to Schrödinger and de Broglie and even Heisenberg were having a problem with, right? The idea was that that particular entity, right, that mathematical entity, right, that the wave function, right, is not defined in three-dimensional physical space. It is defined in more abstract space, like, for instance, configuration space or whatever. Some people think his nature is to be defined in Hilbert space. But anyway, it's not straightforwardly understandable in terms of something that is like a field, like the electromagnetic field. As I said, this is something that, the founding fathers of quantum mechanics and, all the deeper thinkers of that, or the the beginning of the 20th century were aware of, even if they reacted very differently to this. So if you focus a little bit on Einstein, for instance, he is known among many things, but in this particular case, for having thought that quantum mechanics is incomplete. He provided several arguments to try to convince people that of quantum mechanics incompleteness that I'm going to elaborate on in the next slides. Some of them are more known than others, and perhaps not everyone is aware of the fact that, or is convinced like me of the fact that somehow they are, not independent arguments, but they are one after the other. They have a logic. So one starts in the beginning, right, in 1926, which can be called the unphysical field argument, which is what I've been saying right now, namely that quantum mechanics is incomplete, right, because there is nothing that moves in space, okay? Which I'm going to elaborate a little bit more later. The second argument is the EPR argument in 1935, which is the no-locality argument that says that basically quantum mechanics is incomplete because otherwise quantum theory would be non-local, and non-locality is something to be rejected. And then it is uncontroversial that when Schrödinger proposed his Schrödinger cat problem, he was influenced by Einstein's discussion. And so we do have, we can actually say that the measurement problem was actually something that Einstein was putting forward to show that quantum mechanics is incomplete because if it weren't, it would predict unobserved macroscopic superpositions. Okay, so let's start with the first argument. So what is actually wrong about having a theory which is not grounded in space-time, right? Well, one first reaction is, well, of course, that would be just crazy, right? It wouldn't just be physics, right? What are you talking about, right? Physics is about stuff moving around in space-time. However, if you are a philosopher, you are challenged whatever you say. And so somehow it's interesting to dig in and try to explore what's really wrong with that. I mean, why do you think it's crazy? Why do you think that physics, right, should describe matter in terms of stuff moving around in three-dimensional space, moving in time but living in three-dimensional space? Well, that's because, first of all, that's what physics did successfully before quantum theory. Okay, physics before quantum mechanics has been always explained macroscopic phenomena in terms of the dynamics of this fundamental microscopic object. Right, the type of explanation that is provided by that can be called with different names. It doesn't really matter, right, how you call it, right, because maybe none of the names that I'm using is right. Because maybe with that word you intend this or that, it doesn't really matter, right? But the basic, you can call it reductionism, you can call it constructive explanation, you can call it compositional explanation. The point is that, like in classical mechanics, microscopic point particles move in space, evolve in time, according to Newton's laws, and they compose macroscopic objects, right? Pictorially, like Lego bricks compose the cat in the picture that you see over there. And this compositional explanation works, right? Because, both, particles, microscopic particles, and the cat, that whose behavior you want to explain, you want to explain, if you want to, predict or whatever, say when it's dead or alive. That works because both the cat and the particles live in the same space, right? So somehow you say, okay, the cat has temperature is given by molecular motion, blah, blah, blah. Okay. However, if you instead insist that no, quantum mechanics is different, right? You want to explain everything, including the temperature of the cat, in terms of, say, the wave function, then this type of explanation will not work. It's because the wave function is not in three-dimensional space, it's in some other abstract space. So you need a rule to project the wave function down to three-dimensional space, and that rule will not be justified compositionally. It's just a rule that you apply over there. So maybe that's the right way to go, maybe not. I don't think that there is any reason whatsoever to go that way if there are alternatives, right? And I do think that if you really care about this type of reductive, constructive, compositional, whatever you want to call it, Lego style explanation, you need to have a spatiotemporal ontology at the fundamental level, like you did in classical mechanics. Okay, so Copenhagen people like Bohr did not care too much about ontology, matter, or even reductionists, because for all practical purposes, they were positivists. Regardless of whether they denied it or not, they didn't care about this type of things. So Einstein shifted completely gears to try to convince them that quantum mechanics is incomplete. And therefore, so this is just like my reconstruction in my head, what could have happened, right? I'm not an historian, right? But to me, the logic was this. You try to convince them in saying, okay, this is totally different what was happening before. So why? So that this is evidence that something is missing. Say, oh, I don't care about what's going on in the macroscopic scale. Okay, fine. Do you care about what's going on at the macroscopic scale? Yes. Okay, so here's this argument. EPR argument is something like this. Do you care about interaction? Do you care about this stuff? Okay, right? So assume that quantum mechanics is complete then. So by reduction, right? And then the usual argument, right? Consider a single state pair of particle going in opposite direction. If A measures her particle being spin up, the spin of B's particle, which was undetermined, it was not determined because as A's measurement becomes determined to be down, okay? This is instantaneous action at the distance, right? Namely, it's just like non-local action. And according to Einstein, this was absurd. Right? This is evidence that quantum mechanics is not complete, right? And he argued together with Podolsky and Rosen that, of course, he wasn't arguing really like in terms of spin, right? This was arguing about in terms of position and momentum. This is the reconstruction that later on David Bohm gave to make the argument clearer. So the idea was both spin have always had definite values, even if quantum mechanics doesn't give them to us, and measures what they do is simply revealing them to us. So quantum mechanics was saying, oh, before measurement, right? They don't have a definite value of spin. You measure one, so you create spin up for one, spin plus for one, and the other one instantly is determined to have spin down, regardless of the distance, right? This is no local action. This is crazy. The only way, according to EPR, to explain this, this correlation is to say, well, they were predetermined all the way. They were there all the way, right? And when we measure them, we discover them, okay? So no local action is evidence of incompleteness, okay? Let me see how much time I have. Okay. So here's the structure of the argument, just to be redundant. From quantum mechanics, it follows there's no locality, and this no locality is absurd because he was assuming, like everyone else, locality must to be true. That means that locality plus quantum mechanics together imply that there have to be these hidden values of spin. That implies that locality implies that there are hidden variables to explain the EPR no local correlation. All right. Okay, so just before going on, just let me just summarize very quickly why people thought that no locality was totally absurd. Well, no locality, one notion that I do think it's crucial and is playing a role here is the idea that interaction, in this case between the two particles, travels at finite velocity. I mean, this is just like intuitively can be seen by this image of a toy boat floating in the pond. You throw a rock, the boat will feel the rock's presence after some time, not immediately, right? When namely, the boat will feel the rock presence only when the waves created by the rock reach it. Non-locality is just like the opposite, namely that some interactions are instantaneous and arbitrary distance. And this is wrong for a variety of reasons. First of all, it seems empirically false, right? Because if if non-locality were true, then we couldn't really treat object as isolated, right? Because that means that somehow, right, arbitrarily far away objects could just influence the presence of the behaviors of object over here, while that doesn't seem to be the case. Okay. Also, usually causes of phenomena precedes their effect, and we can usually identify the cause, if you like this kind of idea of causation. Which I don't, but that's beside the point. But I mean, the idea is that, you can identify the cause of the phenomenon in the neighborhood of the phenomenon itself. Okay, so I mean, I know that this is not really a very strong argument, but I mean, if you don't have, because I mean, maybe there are reasons, right? And there indeed, right? There are ways to explain, right, why, right, this non-locality somehow is hidden from us, right? But I mean, if you have no other reasons to believe in non-locality, then you have no basis of the evidence that you have no reason whatsoever to believe that something like non-locality is true. Aside from the fact that what the heck would even mean, right? That you have instantaneous action at distance, right? This is something that was also there in classical mechanics when we had, forces, right? Forces are acting instantaneously. I wave my hand here right now, and instantly I modify the orbit of Saturn, right? They're, we all know that they're different from what's going on in quantum mechanics, but the idea is that Newton didn't like that, right? Because there was no underlying mechanism that explained what would carry this. How does that work? What is the interaction? How can we understand that? In addition to that, we also seems to have, for Einstein, this was very important, obviously, it seems to contradict relativity, in which somehow we have a maximum velocity given by the presence, the velocity of light, okay? The problem with the APR argument, as you all know, is that is the following. So Bell went on to with the APR argument and said, okay, fine, right? Assume that you're right. Okay, locality in quantum mechanics implies that you have hidden variables. So you complete quantum mechanics with this hidden variable. Okay, let me see. Does it give us the same predictions quantum theory? No, it doesn't. Okay. Oh well, that's great. So we can make a crucial experiment. Okay. So for a variety of reasons that are historical importance, but I'm not going to summarize. Otherwise, I'm not going to finish my talk in time ever. Let me just say that this crucial experiment was actually made. Okay. By Alana Specht, which is in the picture together with me, and with Jean Bicmont a couple of years ago. And the result is that, the quantum mechanical predictions are the ones that, if you want to use this word, are confirmed. Okay. That means that the assumption of locality is false. That means that no locality is essential to whatever theory makes the same prediction as quantum mechanics. Okay. Nature is non-local, right? So this is the reaction that people should be having, right? Like scream. It is a very big conclusion to swallow, right? As we have seen, right? This is totally mysterious, seems empirically flawed, difficult to put together with relativity, and so on and so forth, right? So for this reason, many people have tried to bypass the conclusion that I proposed last time, last slide, and they've proposed, and these are two examples of the proposed solution. One is what they're called the superdeterministic theory, which reject the hypothesis of statistical independence, which is connected to what in the derivation of Bell's inequality that is at the basis of the crucial experiment mentioned before, or they appeal to retrocausal theory that allow events to have causes in the future. I'm not going to talk of these things at all, but they seem to me much worse than accepting the locality itself. So in this talk, at least, let's just assume that nature is non-local, right? Maybe there are other ways of disputing that I'm forgetting or that I think are dismissing or whatever. Fine, just grant to me that nature is non-local just for this talk and see what happens. All right, so here where we are. Quantum mechanics to have a spatio-temporal ontology if we want reductionism. That's what we said before, right? Matter needs to be made of three-dimensional microscopic stuff moving in space. Quantum also needs to be non-local, right? So matter has to be in space, and also interaction between matter needs to be, non-local. What are the options? Well, to me, this is the option that naturally comes to mind. The pilot wave theory, also known as the Broglie-Bohm theory, Bohmian mechanics, right, in which the ontology is made of point particle, namely matter is made of point particles. They're guided by the wave function according to a law which is called indeed Guidance equation, in which the wave function does not represent matter, but represents the interaction among the particles and naturally mediates non-locality. Which is this slide, what he's saying, right? Particles, matter is never in superposition, so you're never having the problems like the measurement problem, and non-locality is right there, naturally carried by the wave function. Right. Just a quick word about hidden variables. They're not like the one that we find in EPR. In EPR, the idea of the hidden variable, there were spin property values. In Bohmian mechanics, that's not the case. I'm sure that Jean Brickman and Sheldon Goldstein will talk about this more in their talk tomorrow. So I'm just going to assert that spin is not a property at all in Bohmian mechanics. The thing which is added to the theory, if you want to put it in this way, which is odd, is the particle's position, right? And the important thing to understand is that in this theory, the EPR correlation are not explained by this hidden variable. So you're not adding this hidden variable to explain those, right? The EPR correlation are explained by the fact that, non-locality is the case. So you will wonder why, to put things together, right? You need to understand that hidden variables, positions in particles are there to ground the theory in space-time. That's what they're for. Okay. Let's very quickly move to relativity, which of course I'm just going to not talk about in detail because it would be useless. So you can talk in terms of a principal theory, just say what the principle are, the constancy of the speed of light independently of the frame of reference, and the relativity principle, which is in this case embodied by the Lorentz invariance of the laws. You can also talk in terms of the geometric formulation, in terms of Minkowski space, and in that particular case, you see that one feature of the Minkowski space-time is that there is no preferred frame, and this leads to the idea that there is no absolute simultaneity. So here's the tensions, right? So we do have on one hand quantum theory, then we have on the other hand relativity. So relativity is local in the sense that, for instance, in the case of the geometrical picture, you can see directly that interactions is confined to the light cones. And while quantum non-locality violates this assumption, we have just seen that the aspect experiments that are confirming that some correlations are indeed instantaneous. This is the first tension. The second tension is relativity, the theory of space-time. While if you don't consider the Broglie-Bohm, right, and we want to focus on the wave function, then the wave function is not of space-time, aside from the fact that you care about reductive explanation, right? But if you want them to be compatible, they need to be grounded in space. time. And just, okay, space-time can emerge, but why should it? Anyway, so what's my take on how to alleviate link tensions? So first of all, it recognizes that quantum mechanics is incomplete in the fact that it lacks a spatiotemporal ontology, right? Matter should be defined in space-time, and if the wave function is what defines matter, then this is missing. And this is important to fit well with relativity and also to make sense of reductionism. But also recognize that relativity is also incomplete. Why? Because it lacks a structure to accommodate no-locality. Now we know that no-locality is something which we have to deal with. Einstein did not, right? So he constructed his theory on the basis of the two principles, because in the constraint were fine for what he knew at the time. Now we know we need to take into account that there's this additional empirical fact, no locality, and the structure which is given by relativity, as described in the previous slides, is just missing that. So on one hand, Einstein was right to think that quantum mechanics was incomplete, but for the wrong reason, especially when focuses on APR. He thought that one needed to have both the spatiotemporal ontology with the very first argument of 1926, and the local interaction, as APR pointed out. A spatial ontology is indeed needed and can be given, say, in Bohmian mechanics. But in addition, Bell and Aspect have shown that local interaction is empirically falsified, is untenable. Therefore, since relativity is local, relativity needs to be modified too. All right. So what is required by the next question? Okay, fine. Given this, right, what is required from a relativistic quantum theory? Well, at least, the very least, right, and I don't mean to be precise because this is just like a 35, 45-minute talk. It must keep, right, space-time, Lorentz invariance, and no locality. These are the three ingredients they must put together. They need to stay together. Why you care about space-time? I've said it more than once. Just let me repeat that. Reductionism, right? Explanation, right? That you can visualize, like physicists like to do, and philosophers should like to do as well. And but even if you don't care about that, relativity is a theory about space-time. So if you have a theory, a quantum theory which is not given in space-time, somehow you have to come back to space to make it compatible with relativity. Then Lorentz invariance, because that's the structure that Einstein reasoning led us to. And then of course we have quantum the non-locality of the interaction because of the experiments that were performed in the 80s. Okay, so look at Bohmian mechanics. There are general kind of wave theories, namely theories that work starting from the idea that there is some micro stuff that moves around in space and evolves in time, right? And they can be made Lorentz invariant, right? There, I'm sure that you can find the references. You will find references of these in the talks, at least of tomorrow. You can use Dirac's equation or Klein-Gordon equation to implement the evolution of the particles, and they are non-local, right? They are not local, and this is because of the nature of the wave function that needs the position of the particles, of all the particles, to be specified at the same time, so they have a what is called the preferred foliation of space-time, which can be this foliation of space-time can be implemented in different ways, can be postulated, can be seen as more naturally emerging from the theory itself. Different theories have been proposed, but the core idea is that this preferred foliation is something which is added on top of Minkowski space-time structure. But this is needed in order to accommodate of non-local interaction. This foliation is undetectable. Some people have said, oh, okay, this is a problem. It is not a problem because you can actually understand why, explain why it is undetectable as in terms of quantum equilibrium hypothesis, which again, you will hear again for sure next tomorrow. Okay, so we do have this. So space-time stuff, moving around in a Lorentz invariant way and interacting non-locally, and space-time having a preferred foliation. Okay, you may say, can we do better than that? Do we have any other options? Well, there is a sense in which, I still have time, right? There is a sense in which I don't think so. I mean, there are alternatives like anything, but, I don't think they're not working just as well. And I apologize this for being short, for instance, right, one approach that I was extremely attracted to while I was studying these things was the spontaneous follow-up theory developed by Girardi, Rimini, Weber, and other scholars. Since this theory, in which collapse is actually embedded into the law, is not so that the law becomes stochastic and nonlinear. This theory, the first thing that you need to do is somehow assume that this theory describes something in space-time, and usually these theories are specify either matter in terms of a field function or in terms of event in space-time. Okay. So what is interesting about this theory is that they have been proposed, some versions of them have been proposed. One important theory was proposed by Roderick Tumulka is you can actually make those theories Lorentz invariant without adding any foliation of any sort. So the very exciting thing about this theory is that they are foliation free and Lorentz invariant. However, and you should just get very excited about this. However, right, they are aside from they are stochastic and also nonlinear, but the stochasticity of them is actually brings together with that many downsides. For instance, it's difficult to identify what is the cause, what is the effect. You have to rework all the these notions. They display, they are more local than for instance, the Bohmian mechanics, relativistic Bohmian mechanics, or even Bohmian mechanics regularly, because they show non-local transfer of matter only with one particle in quotes, because it's not like there are particles over there. And this is problematic for a variety of reasons, including the fact that if locality is about interaction, you have only one particle. What does it even mean that you have no local interaction with one particle? In addition to that, they contradict quantum mechanics. They make different predictions. They do not conserve energy. They have parameters with ad hoc. They're artificial in many respects. But however, these are an attempt to say, okay, let's just keep relativity as is and modify a little bit and modify quantum mechanics. Let's see what happens. And this is what happens. Compare that with relativistic pilot wave theories, which you're changing both quantum theory and quantum mechanics. All right, you change quantum theory because you ground it in space-time, but also do they, right? GRW type theories also do that. And you also change relativity, adding a foliation, right? You can say, oh, adding a foliation is bad because you're modifying relativity. Okay, just bear with me, right? You're changing little things here and there. So what are the consequences? We do have Lorentz invariants. They are deterministic. Maybe you don't care, but you don't have super null locality. They are as null local as needed to account for the EPR correlations. Energy is conserving. They're not ad hoc. You don't have free parameters that you need to fix, right? And they preserve explanatory power in the sense that you can use the very same structure of explanation that you use in classical theory to explain the phenomena, modify, considering that the equations of motion are different and particles do unknown classical things. Okay, so in my perspective, quantum mechanics, so the Bohmian mechanics provides a balanced modification, a balanced combination of quantum mechanics and relativity. That's why. Why? Because quantum mechanics is incomplete because it lacks a spatiotemporal ontology, and Bohmian mechanics gives you just that in the simplest way. Relativity is also incomplete because it lacks the structure to accommodate quantum locality, and Bohmian mechanics just give you that, right? Very naturally. How do we explain no local correlation? Well, you just put a foliation. That is the Broglie-Bohm mechanics modifies quantum theory and relativity minimally and most naturally. And doing that, it retains many features that we value. Okay, it's a simple, coherent, explanatory, and not ad hoc theory. So here are my final thoughts, and hopefully I'm on time. So if you want to think, this is the way I'm thinking right now, which is a kind of simplistic, but maybe not that much. Quantum mechanics can be seen as a theory of matter. Matter needs to be somehow real. Real in the sense that in physical space, what is the simplest way of describing matter? Particles. Just try that. How is matter interacting? Well, it's interacting non-locally. Okay, and therefore just embrace that conclusion. How? Well, just build a spatiotemporal Lorentz invariant theory in which matter is interacting non-locally. There seems to be no advantage to do otherwise, or to do something else. So to me, looking for relativistic Bohmian theories is the rational step forward. With this, I don't mean to say that we can all go home and there is nothing to think about. I'm just thinking that among all the possibilities that you as a researcher should look at and should study and should put your efforts in, that's where you should go and work on. There are for sure many open issues, both in physics and in philosophy and whatever, right? In physics, what about quantum field theory? What about, I cannot even name them all, right? In philosophy, the biggest question is, how do you understand the notion of no local interaction? But I think these are the things that you should focus on. If you think from a perspective which is as simple-minded as mine. And so the last line is just a joke. That's one small step for man, one giant leap for mankind. Just work on Bohmian mechanics, and that's it. Thank you for your attention.
Yeah, we have. Okay, there's time for one question. You want to get it?
Hold on. For some reason, I cannot see you. Okay, now I see you.
Hi, Valia. Can you hear me?
Yes.
Okay.
Hi.
So, intriguing talk. I enjoyed it quite a bit. The part that I take issue with is relying on Klein-Gordon and Dirac as the pilot wave part of relativistic Bohmian mechanics. They're problematic on their own for a single particle. In fact, the Bohmian trajectories you get from those really are a great way to highlight what the problems are with those particular with choices of pilot waves. The other thing, too, I would comment on is there's no difference between configuration space and space-time unless you have more than one particle.
Yes.
So like the whole thesis about non-locality has to enter in. I accept that, I buy that. But that means we're talking about at least two particles. And that means we're talking about a configuration space with at least two times. Because configuration space is now 3 + 1 × 2 or times n, where n is the number of particles. And that brings a whole host of new problems in if you're talking about a fixed number of particles. Of course, you can go the quantum field theory route, but I don't think anybody here wants to do that. So that's, I think to make it work, the hard part really is coming up with a better pilot wave. Once you have that, then I think all the pieces fit into place. So that's really more of a comment than a question, but if you want to make comments on my comment, that's fine.
Yeah, thank you. I mean, I couldn't agree more. I mean, my talk was very provocative in the sense that as I said at the end, right, this is what we should be working on, right? This is, if you take this theory seriously and you try with this equation, you said, okay, they do not really work, right? Yeah, and yeah, sure, let's all work in trying to find a better wave, maybe we just go and use multi-time. I don't know. I mean, there are too few people working on that, and so we just need more, more strength, just to go forward. Yeah, I agree completely.
Okay, I think we have to move on, right? So thank you again. Thank you very much. Okay, and then we have one more talk before lunch, and this will be the second plenary or keynote talk, as we might say, and this will be by Professor Anthony Leggett from University of Illinois Urbana-Champaign, and with the title Experiments on Macroscopic Quantum Coherence. How might a Bohmian react to them?
How long do I have?
Well, you have altogether 45 minutes, so for example, 40 minutes for the talk, 5 minutes for discussion, or as you decide.
Oh, okay.
4-0.
Okay. Thank you. Well, it's a pleasure to be able to contribute to this meeting in honor of David Bohm and his work in Brazil. I didn't really know Bohm personally. I think we met once. I had a small amount of correspondence with him and a somewhat larger amount of correspondence with his disciple and co-worker Basil Hiley. I was very sad to learn about Basil's death a few months ago. I'm going to be talking about a set of experiments which Bohm himself really could not have commented on because they all took place after his death. But I think that some very people who follow him and call themselves Bohmians might want to comment on them. These are the so-called macroscopic quantum coherence experiments. I will start by just giving a very brief motivation for these experiments and spend most of my talk describing what they are and how they differ from previous experimental work on the foundations of quantum mechanics. And finally, I will spend a fairly brief part of my talk talking about what the implications are from a Bohmian point of view. I'll talk about both about the experiments which have actually been conducted so far, the so-called bare version. If I have time, I will just spend a little time talking about the recycled, what I call the recycled version of the experiments. Okay, so let me just very briefly start by talking a little about the motivation for the experiments on macroscopic quantum coherence. Um, in 2014 to 15, there was actually a set of experiments on different set of experiments. Let me emphasize, these are not the inputs that we're talking about. These are the so-called EPR Bell experiments, which of course have been conducted over the last 60 years, but there's a particularly notable set of experiments conducted in November, December 2015. And this slide is not really terribly essential, but I've just noted some of the parameters of these experiments. The so-called Einstein-Podolsky-Rosen-Bell experiments, in which one measures the correlation between two particles which have been emitted by a common source but are subsequently measured at spatially very distant positions. And as I say, here are some of the parameters which go into those experiments. If we assume that the data reported in these the papers reporting this experiment, we assume that the data are real, what are the implications? Well, the experiments were meant to act as a test of local realism, and indeed, I think to most people's view, they have refuted anything we could call local realism. But as always, there are loopholes. The outstanding loopholes which have been actually noted are those of superdeterminism, the idea that the result of any particular experiment is determined from by the initial state of the universe. I suspect that is actually untestable in practice. The second possibility, which people have proposed, is retrocausality, that the future can affect the present or the past. Again, I suspect that's probably untestable by a real experiment. But there's a third possibility, which has not been explored perhaps as much as it might have been, which is the loophole of collapse locality. That is, we have to ask, we are, in some sense, in these experiments, making measurements, and in those measurements, a definite outcome or different outcomes were realized. But at what point was it that a definite outcome was realized? Was it when for example, in a photon experiment, is it when the photon passed or failed to pass the polarizer? Well, that seems unlikely because there are other types of experiments in which one can actually measure the interference between the transmitted and reflected photons. So is it when the photon, having passed or not passed the polarizer, is actually absorbed in the anode, I think it's the anode, of a photodetector? Well, possibly, but that's not what quantum mechanics at least says. And so on and so forth. And if we postpone the actual realization of a definite outcome in the EPR Bell experiments to a late enough point, for example, the point where the measurement results are combined in a local correlator, then we can in fact still maintain some version of local realism. So the question is now, are there experiments of a different kind which can say anything about where a definite outcome is realized in the experiment? And the answer is, well, at least in a sense, yes. And these are the experiments that I'm principally going to talk about, the macroscopic quantum coherence experiments. Basically, in these experiments, what you have is a macroscopic system which can be in one of two or possibly more different states, which I will label by q equals +1 and q equals -1, just to have a notation for them. And the important point is that these states are actually, in some reasonable sense, macroscopically distinct. And what we're going to do is to try to conduct an experiment in which we induce the system to occupy either one or of these states or some superposition of. Now, what kind of system are we talking about? Well, it turns out that the most promising, or certainly the most widely used system for this kind of experiment is one which was hardly available when David Bohm was still alive, namely a flux qubit, or what we now call a flux qubit. What is this? Well, it's a superconducting ring which is interrupted by a single Josephson junction. In the simplest description, the ground state of such a ring is doubly degenerate, corresponding to a certain current flowing either clockwise, in which case we say repeat that around, either anti-clockwise, in which case we say that Q is +1, or clockwise, in which case we say Q equals -1. Then you see the minus there; it's supposed to be minus. Now, experiments have been done for some time from a couple of decades ago on this kind of system. And what these experiments had told us is that if you interpret the raw data in quantum mechanical terms, that is, if you ask, if we apply quantum mechanics to the system, is the intermediate state a quantum superposition of two states, clockwise or anti-clockwise circulating current, or is it rather a classical mixture of those states? Then the answer is clear-cut, that the data show that it must be a superposition. But this is actually not terribly convincing, because in order to draw that conclusion, you've got to interpret the data in quantum mechanical terms, which in some sense begs the question. So the question is, can we say something about the implications of this kind of experiment without necessarily interpreting the raw data in quantum mechanical terms? Just let me make a note on this system. People sometimes argue about whether the states in which the current is circulating clockwise in one case or anti-clockwise in the other, whether these really should count as macroscopically distinct. I have a little note on that, which is noted at the bottom of this slide, in which I compare this situation with a situation involving direct observation by the human eye. And I claim that these experiments are at least as macroscopic as that experiment. And you can, if you want to go into the details of that. Anyway, let's for the sake of this talk, let's take for granted that these states can be counted as macroscopically distinct, and ask what kind of experiment we're going to do. Okay, next slide, please. Well, what we're going to do is to compare the predictions of quantum mechanics with those of what I call a macro-realistic theory, sometimes abbreviated MR. And what defines a macro-realistic theory is the conjunction of three postulates. One is actually macrorealism per se, by which I mean the assumption that at all times the variable Q of t, which distinguishes these two states, is either +1 or -1, or possibly from small time intervals in which it's making a transition between these two states, which one can actually allow for in the analysis. So that's the first postulate, the idea that at all times a macroscopic system which has available to it two macroscopic distinct states at all times, except for these small intervals, must occupy one or other of these states. The second postulate is one which we normally make without thinking about it too much, which is simply the absence of retrocausality, just as in the EPR Bell experiments and postulates that what happens to a system in the future cannot affect its behavior now or in the past. Now, we're still lacking one of the postulates which would correspond to the third postulate in the EPR Bell experiments. Very important, a third component in the local realism, which is tested in the Bell experiments, is locality. There's no question that we're dealing with local processes here. There's no question of having non-local separation. So it has to substitute something for that. And what one substitutes is a postulate which I call non-invasive measurability. And so let me just say a word or two to explain what I mean by that. So let's assume that we set up a measuring device which basically interacts with the system only if it is in one of the two macroscopic states, let's say the Q is +1 state. And then we will do our experiment, and if our measuring device actually clicks, then we'll throw away that run on the grounds that we could have affected the behavior of the system by making the measurement. However, if the measuring device does not react, then we argue that then the system must have been in the state Q equals -1. The measuring device then is not interacting with it, and therefore we can keep that set of data based on that line. And we can actually prove that it's possible to get all the data we need for our purposes of these negative result experiments. That is, experiments which gave a negative result in our measuring device. Now, in this case, it's unnatural to assert postulate 1, that is, macrorealism per se, while denying postulate 3, because if the system really was in the minus state, then the measuring device could not have interacted with it, and therefore, indeed, it could not have affected its behavior. Now, we can't actually explicitly test this postulate of macrorealism, but we can actually make it plausible by an auxiliary experiment as follows. We just construct our experiment so that at a given time, Q of t is known to be, say, +1. And then we can see whether a non-invasive measurement does or does not affect the subsequent statistics. However, it is essential for this purpose that the measurements be projected, this is polynomial time. So measurements using weak, experiments using weak measurement, I think do not really really satisfy this criterion. So before December 2016, there were various experiments which used weak measurement techniques, and therefore, as I say, are not, I think, totally convincing in this context. Moreover, in these experiments, the states measured were not actually macroscopically distinct by any reasonable criterion. They were indeed done on flux qubits, but the two states of the flux qubit which were distinguished were not, I think, by any reasonable criterion, macroscopically distinct. So I think until December 2016, one didn't really have any firm evidence of whether or not a macro-realistic theory was viable. Next slide, please. In December of 2016, an experiment was done at NTT in Japan. I'm actually a co-author of the paper reporting that experiment, although my own role in it was distinctly minor. This is roughly how it goes. Rather than imitating the PR Bell experiments and measuring, doing the analog of those, where you can measure time correlations, what we do is to just check directly whether a measurement, which need not necessarily be non-invasive, but whether a measurement at time t2 affects the value of Q, measured value of Q at a third time. We do them first for the different macroscopically distinct states, and then for their possible superposition. So to be a little more technical, for any state sigma at the intermediate time, T2, we define a quantity which is the difference between the value measured at T3, having made a measurement at T2, and the value which is measured at T3 without any intermediate measurement at T2. So that we do for any state, sigma. Just a definition. Now, so in this case, our ancillary test, our first ancillary test, is to just make the state sigma the plus state. That is, we do an experiment in which we know, or we believe we know, that at T2 the system really was in the plus state at the intermediate time T2. And at T2, in one set of runs, we do a measurement to distinguish between plus or minus, and in the other one, we make no measurement at this intermediate time. And then we measure the state of the system at the final time. So we do that for a state which is known, or we believe is known, to be in the plus state. Then we simply repeat this for a state which is known to be a minus state. And we again measure the quantity D, which is the difference between these two possibilities. Next slide, please. And having done this ancillary experiment, basically find out what is the effect of an intermediate measurement purely classically, that is, when the system is known not to be in a point of superposition, but in one state or the other. We've done that without now doing a main experiment on preparing the system in such a way that, according to quantum mechanics, at the intermediate time, it's going to be in a superposition plus or minus. And then we compare the results of a set of runs in which we actually measure the the state of the system at the intermediate time, and a set of runs in which we don't do anything at intermediate times. And so we define a quantity d some rho. That's the value of quantity d, this experiment. We define and then having done that, we compare that with d plus and d minus. And we define this difference, delta, which is d sub rho, the difference measure for the alleged quantum superposition state, with the minimum of the minimum value of d plus and d minus, the minimum of those two. If you believe in macro realism, then you predict unambiguously, this is actually done in the theoretical part of our paper in 2016, you actually predict that the quantity delta has to be larger than 0. However, the experiment very definitely shows that delta is negative and has the value minus 0.063. So it turns out, if you put in the appropriate numbers, that this experimental result violates the macro realistic prediction at the macroscopic level. So now we've refuted realism, not just at the microscopic level, which is what we did in the Bell experiments, but also at the putatively macroscopic level. However, there's still a question as to what this means. Remember that in a field very different from physics, there was a famous quotation from a well-known person saying that so-and-so depends on what the meaning of is. And the same applies here. What do we mean? What we really mean by saying that the system is in one state rather than the other? And that I think is a problem for any interpretation of quantum mechanics. But I think it's particularly well, not particularly, but it's certainly a problem for the Bohmian in the interpretation. So let's go to the next slide. Yeah. As I say, the postulates of macro realism, so repeating basically, are first of all, the macroscopic object is at all times a definite macroscopic state. Secondly, in the ideal negative result measurement of the negative result, neither the state of the system nor subsequent dynamics is affected. That's what we call non-invasive measurability. And finally, this is one often not mentioned because it's taken to be obvious, but finally, ensembles are defined by initial conditions and not by final conditions. The future cannot affect the past. Now, as we've just seen, macrorealism is in contradiction with the result, with the experimental result. How is the Bohmian approach going to deal with this? Well, remember that one of the principal virtues, perhaps the principal virtue, claimed for the Bohmian approach, is that at all levels it is realistic. So it can't deny postulate 1, I think. And therefore it must deny one of the postulates, 2 or 3. If there is no measurement at the intermediate time, then the components of the wave are both non-zero at the intermediate time. And that's true, of course, in Bohmian interpretation, just as in any other. And therefore, subsequently, you can get interference at the final time, just as in standard quantum mechanics. So I don't think the Bohmian interpretation has any particular difficulty with that part of the statement. Now, what if the measurement is made at the intermediate time? Well, presumably, since we are talking, I should have emphasized here, when I talk about the Bohmian interpretation, I do mean an interpretation and not an alternative theory. That is, I'm assuming that the Bohmian interpretation is just a way of interpreting the results which follow from standard quantum mechanical formula. And so, if you do that, then just as in standard quantum mechanical formalism, for any time greater than the intermediate time at which the intermediate measurement is made, the wave function is an entangled wave function of the system, that's the sigma, and the measuring apparatus, which are denoted by x. And the two different states of the measuring apparatus by construction are mutually orthogonal. And once you're given that statement, then you can argue, just as in standard quantum mechanics, that decoherence arguments show us that although the sigma z equals plus one component is suppose we measure or claim to measure sigma z equals minus one. According to standard quantum mechanics and also according to the Bohmian interpretation, presumably, the sigma z equals plus one component is still there. However, because it's coupled, because it's entangled with an orthogonal state of the measuring device, its existence is irrelevant to the subsequent behavior. So basically, in the Bohmian interpretation, there is something, namely the non-observed probability attitude, which is there, but is not in one-to-one correspondence with the actual behavior, that is the actual value of sigma z. And therefore, we are, in effect, able, within the Bohmian interpretation, to violate postulate 2. So I don't think, in fact, that the Bohmian interpretation has any greater difficulty in dealing with this situation than any of the many other possible interpretations of the quantum formalism, but it perhaps does so in a more explicit way. I think that's my last slide, isn't it? It is. So basically, as I say, I don't have any more difficulty than other interpretations. You might just pretty up this experiment a bit by asking what would happen if, having made this negative result experiment, we then apply an operation to the measuring device which resets it in its original untriggered state. Could you still make the same argument? Well, I guess the situation is yes, you could. The point is that in order to do this re-preparation of the measuring device, you have to affect something else in the world, namely the environment of the measuring device. And that is, as it were, going to act as a record of whether or not you've actually measured Q plus or Q minus at the intermediate time. And you can then again go forward with standard quantum mechanical decoherence arguments. So I think in conclusion, I would say you don't. The Bohmian interpretation doesn't, in fact, have either more or less difficulty in interpretation of these macroscopic quantum coherence experiments than most others, but it may perhaps make them nature of the difficulty and the more explicit. Thank you.
So there is time for some questions. Anybody? See on this side.
I suspect I didn't actually present the experiment very clearly. Anyone who wants to follow it up, we do actually have a paper in Nature Communications in 2016. Yes.
Right. Okay. Anybody with the question? I think we are also late to go for lunch, so maybe the audience is already expecting to make a move there. But anyway, let's thank very much again, and we'll continue.
Hello. First of all, I would like to thank the organizers, especially for this kind invitation and this rich environment to discuss foundations on quantum mechanics, and especially Bill, because we are keeping in touch since the first moments to talk about this conference, this meeting. So I'm very happy to be here, and I will share some developments from our group in ex-Marseille University. Let me coordinate the mic and this guy here. So one of our concerns is about to understand the time evolution of quantum systems, of course. So we use time-dependent Schrödinger equations for that. And we are very happy to do this. But we need this extra postulate to measure the final measurement. So the collapse of a wave function, this is a main topic from the objective collapse theories. Those are candidates for unifying quantum time evolutions. So the first development, we use the Yoshi-Penrose model to understand how gravity can cause the quantum superposition collapse. And this is the main part about my talk today. There's not a one way to explain the transition from classical to quantum. And we understand better now about the coherence. So the coherence, since the seminal papers by Zurek and others, we can understand now the coherence can solve two main problems considering the quantum measurement problem. It's about the preferred basis and the preferred basis and the non-observability of the interference, especially in the macroscopic system. So, okay, the coherence solves these two of them, but it remains the problem of outcomes. So, objective collapse theories can handle with this. That's the main goal. So, in summary, you can understand the coherence starting from a density matrix of a quantum system. So we trace it, after we trace it over on the environment, we keep this simple two-level system, quantum system, considering the diagonal terms and the off-diagonal terms, showing us the coherence. If you have the coherence process, we have just these diagonal terms, but we don't know beyond that. We still have these two scenarios about to collapse to one of those states. So I think this is not the end. We understand the coherence, we can live with that, but we must show a complete theory about to understand the final state of a system. So comparing the objective collapse theories and the coherence, we can understand the coherence from this unitary and in principle, a reversible approach, right? And we have the proposal from objective collapse theories as a non-unitary and a reversible process. But we have a full comprehension about these two concepts. So our contribution, we derived these general atomistic models to understand the Auship-Penrose model, to compute collapse times, and we employed some equations. We derived analytical equations for systems considering small molecules and some macrostructures. Basically, when we have a quantum state in the Hilbert space, we can measure this. And we know from the textbooks about this. We have a quantum state, and we can describe this quantum state using the dependence on time and using this Schrödinger equation. And start from chosen basis, we can see those complex valued coefficients to understand when, how to solve this Schrödinger equation, and the probabilities about to measure that initial quantum state in one of them. But specifically, I'm talking about here about pure states, right? And we can face, as we know, different systems with mixed states and so on. So we can understand time evolution of quantum states, consider it's two pathways. Using Schrödinger equation, the well-known Schrödinger equation, but we are dealing just with unitary and deterministic systems, right? And we can deal with this modification about the Schrödinger equation, take into account the non-linear terms to understand the non-unitary and the stochastic process. Basically, the objective collapse theories deals with all the time with this modification about the Schrödinger equation. So, talking a little bit about objective collapse theories, to include the collapse, because the main goal about this is to understand, not to put an extra postulate, as I said, but to handle with different equation, including collapse. So, simplifying the main from the continuous spontaneous localization, we can understand the stochastic Schrödinger equation looking this guy here. And we have normalized a normalized quantum state, and we can describe this equation with this part, with a well-known part, and adding some extra part here. Now you are seeing here just one operator, but we can handle with many self-adjoint operators we want. And you use this Wiener process to control the noise of the system to measure the collapse. And the extra term, this nonlinear term, to control the linearity of the response of this equation. So this is the main formulation about the modification of the stochastic Schrödinger equation from the objective collapse theories. And there is a subtlety here about the technicalities. This is about the expectation, the value about this Wiener process using this eta parameter here. It is a free parameter considering those objective collapse theories. And the main idea is about to handle with this time evolution of that quantum state to see the spontaneous collapse to one of the eigenstates of that operator of the set of operators. Of course, you can see right now we don't recover the Born rule using just a single realization, a single trajectory. We must count with statistics to do multiple realizations to understand, we will recover the Bohr rule over multiple realizations. Just to give you a simple example, suppose we have this A operator, the Hamiltonian of this system, with the ground state 1 and the 2 excited states with those coefficients. So to realize, to solve with using a single trajectory, you can see just the collapse of one of them to the green or the blue curve, but especially if you are using the one of them, each realization, we can see this a kind of the different measure. But we can see here the Bohr rule. But after 10,000 realizations, we can see the recovery of the Bohr rule over there, looking at the histogram. So the continuous spontaneous localizations is an approach that modified Schrödinger equation, but now we're using a formulation to deal with this number operator. This is a number operator counting with the ladder operators, and the free parameter it is there, and we have this Wiener process here. I show you just one of them, just to simplify the facts. And we can deal with these two free parameters using to solve that equation. And this RC parameter came from this many times about the coordinate we are using to measure the superpositions, about the mass distributions. So one interesting feature considering continuous spontaneous localizations is really agnostic considering the cause of the collapse. So those free parameters you can use, for instance, gravity, to see if you will observe the coherence or collapse from that modified Schrödinger equation or stochastic Schrödinger equation. It's possible to understand the quantum state collapse from this gravitational phenomena. So Lajos Dioschi proposed this equation to compute this is the modification about Schrödinger equation, where you can see the gravitational constant over there, and we use mass distributions and the noise to control the behavior of those realizations to understand how gravity can cause this and to compute the collapse time. So considering the Dioschi's proposal, we can see this using all the time the mass density operator. So to solve that, Dioschi's proposal is very simple, but very intriguing because all the time he departed from the simple, just showing here just the simple state, and we can reach this collapse time using this this formula. But this formula has a previous arrangement I will show you from Penrose. At the same time, or I don't know, same time, sorry, but I think in the different ways, Penrose and Dioschi proposed the same equation for to compute collapse time. But Penrose departed from this heuristic argument, considering this conflict between quantum superposition and the equivalence principle. So the Penrose idea is about, let me take here my little friend. This is the ammonia molecule. It's a simple molecule using just one atom of nitrogen atom and 2 hydrogens. So if you put those in the space-time, we have 2 states, and we can measure this with the simple state here. And we can consider according to Penrose, we can consider the free fall accelerations to compute computing from the gravitational potentials. And after that, we can see this instability. It's unstable to see the same thing in different space-times. So according to Penrose, there is a gravitational self-energy computed from these 2 free fall accelerations. And we use a free parameter, but we use Newton's gravitational constant to reach this expression to compute the gravitational self-energy considering this system. And this is the final formula to compute the collapse time using the h bar and over the gravitational self-energy. Joshi and Penrose proposed, using different ways, this beautiful way to compute the collapse time without using extra arguments. So we can see here, if you after a while you can see our little guy here in the one state over another, and we can compute this. But so what's the high ambition of this? The high ambition is to solve the problem of outcomes. So, but the main goal, according to the 1996 article, Penrose article, I think this is a beautiful statement. Penrose said it's meaningful to quantize the gravitational field, right? But why not to gravitize quantum mechanics? So it's okay. Penrose has a strange way to be right sometimes, but it's Penrose, right? And some point, Professor Mario Barbat and I and Rafael Matos, we started to test this model using the molecule atomistic scenarios. So we departed from this simple way to compute the gravitational self-energy using mass distributions. And since theoretical chemists are crazy about Gaussian distributions, why not? So we use the Gaussian distributions to compute different atomistic models. And analytically, we published this main formula to compute the self-gravitational energy using different molecules, considering the mass of each atom, and using the geometries of those molecules. Of course, considering the stable states of each model, of each system. So, looking at again about a little guy, the ammonium molecule, you have this down and up pyramidal structure. We have these 2 stable states. It's a 2-level system, quantum system. And we have this nuclear wave function here to help us to compute the self-gravitational energy, gravitational self-energy. And okay, this is a straight line just to guide our eyes only, okay? And as you can see here, we have these 2 states, considering the nitrogen up or down, right? So if we compute this isolated ammonium molecule to compare the results, we have here this reference, Jones and Z, about the calculation about the coherence time. So Our final result about using an isolated ammonia molecule, computing the collapse time to see the ammonia molecule up or down. And we have this huge value here, 10 to 17 seconds, which means 10 to 9 years. So it's too long to see something, right? But considering an environment with thermophotons, the coherence time is longer, 10 to 20 seconds. But if the environment considers, if you take the best lab in the world, you can put this time, the coherence time, to 10 to 6 seconds. But with environment considering just a gas, we can see the coherence is too fast, 10 to minus 19 seconds. So we can observe collapse. We can observe collapse before the coherence or the coherence before collapse here, according to the environment, right? But in a certain sense, this is not a reasonable value to observe something, right? So it's well known the Talbot law interferometry used by Arndt and Zeilinger about to compute the famous experiment about to see carbon-70 to show the superpositions of the carbon-70 using this interference between the two neighbor slits, but using this experiment using the system of greatest. But the two-level system here, we use the geometry of the Fillery, the original one, and we just did rigid translation in the x direction to compute a few Fillerines. And we start with a small one, the carbon-70, and you can see another huge value for the collapse time. And even even after we did the computations for the carbon-60, carbon-70, and to the big one, carbon-720, the collapse time is longer. And just to give an example, considering the famous carbon-70 and carbon-720, you can see you did not reach some reasonable value again. So we moved to a big system, but instead we did not see this. With a larger system, we can see a reasonable collapse time here. So, but what about to simplify the main equation of the work, treating the system using homogeneous models, like using one single atom and just using this one Gaussian width. So we can simplify the equation using the superposition displacement, the delta capital R here, and the mean distance between any pair of atoms, consider delta over line R here. And it's possible to simplify this equation considering comparing the values of mean distance and the superposition displacement. So, and using this to a simple model, we can use sorry, I don't know. Sorry, I did something wrong here. It's not mine. I don't know. It's another talk. Oh, sorry, Carlos. Yeah. Okay, thank you. Sorry. And considering this simple model about the neuron, we have this, we can deal with these two states, considering the two-level system. We understand that we only have sodium cations outside of this membrane. We have this state, resting state, an activity state, and when the neuron is on fire, we have the all sodium cations inside. So we consider the two levels to compute to compute the collapse time. So the value we found was about 10 to 10 seconds. Okay, again, too long. But when the environment, when we can find this neuron proposed by Tegmark, in water and ions and other ions, the coherence time is about 10 to minus 20 seconds. So pretty fast compared to the collapse time. So we will not see this the collapse of the system, right? But especially because comparing to the well-known axon recovery time, we have to 10 to minus 3 seconds. So we are far considering the coherence in collapse time. That's okay, but going back to our filterings, we compare the geometry specific and the homogeneous models, considering two different scales, and we see this saturation about the gravitational self-energy. So if this gravitational self-energy saturates, we reach minimum Garashchuk-Penrose collapse time. So the proposal about to go to larger systems, it's not working here, considering atomistic models. But if we take a different system, like an iron crystals, consider just this BCC structure, we can see the just two level systems again, considering just the vacancies. And we can compute the collapse times. We computed the collapse times considering different masses. And even we've considered a 1 kilogram piece of iron, we found something like 1 second. But again, it's too long to consider the collapse time, right? The coherence survives so long. So the first drawback we found, considering the Garashchuk-Penrose model, was about extensivity. See, if you consider just the system, but we have the environment, actually the environment does not contribute with the gravitational self-energy. And we can see here in this simple expression, we have just the contribution about the difference of the mass distribution considering the state A and B. And another problem about the saturation, you can see we use a simplification about the demand formula of our first work. Is about taking the superposition displacement here to go into infinite. We have this simple formula to using just we can see we have this the maximum of the gravitational self-energy. So to compare using some examples, using just a carbon atom systems, considering the equivalence masses, like if you use the carbon 70, we have this huge value for the collapse time, but a rhodopsin protein, it's not so optimistic, but you can go to adenovirus and pollen grain, and even a small dog, about 10 kilos. We have so short collapse time, right? In the certain sense, we proposed this Gedanken experiment about using the famous Talbot law, the Talbot law interferometry. So, but we want to observe the wave function collapse, but we must deal with two requirements here. Of course, we must observe reasonable times. I mean, human lifetime, right? And you can do this controlling via the number of atoms. But this is the first thing we could control. But avoiding the coherence, we must control the environment. And it's challenging. Because how to do that? So, first of all, just to give you a glimpse about the difficulty of this, how far we are, we could consider it because of the room and temperature, the pressure and temperature, room pressure and temperature. I think we can deal with in outer space conditions. So, just to give you a brief description about the Talbot law interferometer, we have these three gratings, and we can shoot some particles on the first grating, and we can measure the Talbot point and to see the interference according to the patterns we can observe. And suppose we are dealing with these masses, with controlling with this K number here, about times 10 to minus 18 kilograms. We propose to shoot those masses with a specific velocity, like 10 to minus 3 meters per second. So it is based on, of course, mainly on the work about Zeilinger and co-workers. So using just two neighbor slits with this distance and computing this Talbot point is distance L, we just here take off the last grating, but we can calibrate the system with the collapse time and the travel time. So it's about 8 hours. So we can do this the simple thing. After we shoot different masses using the K parameter to see the collapse time, if you see more patterns, we are seeing the pattern expected for particles. So we had collapse before we have collapse. But if you see the wave patterns, we have superpositions yet, right? So it's a simple experiment we propose. So besides the difficulty here, I think it is the one thing to consider in near future. So, on time. My final remarks. Let me show you something. After we developed these atomistic models, considering the Dewdney-Penrose hypothesis, we reached those values I showed you about the atomistic systems and homogeneous media. And we used the many references considering the coherence times to compare with our results. And okay, considering atomistic models and homogeneous systems, we found those drawbacks considered the Dewdney-Penrose model. Just to cite two of them, extensivity problem and the self-energy saturation. And considering just 2 weeks, it's an amazing thing talking about science. Considering just 2 weeks, a group of scientists, researchers from Trieste and collaborators, they published a work based on this Dioship-Penrose hypothesis, and they found a new problem with the radiation excess. So I think the Dioship-Penrose model is simple, or of course it's amazing at the same time, but I think many people now are engaged, according to Stefan Adler, since he started to work in this field. I think now it's time to propose new experiments, to go to test the collapse models, the collapse theories. Those words came from Steve, right? And so when we engaged this project, we were newcomers, and until now we consider ourselves newcomers in the field, but we are facing this quantum measuring problem all the time, especially because it's not so clear if you're dealing with the coherence and collapse all the time. So after we dug a little bit like scavengers in the literature, we found many discussions about quantum mechanical interpretations. Like you can see here, if you do a little search on Wikipedia, you can find this amazing table about interpretations of about collapse. You can live with many word interpretation. You can live with cubism, or like Carlo Rovelli proposed, the relational quantum mechanics. And each one of Bohmian mechanics, and each one of them, we can see many pros and cons. But now I think we are facing this moment, especially here, listening to you all about this. We must find a different path to understand the foundations, because even we put some secrets under the ground, I think we can, that kind of thing, it's kind of a wave. It will come to us one day. So just to give you some approach, we have this list of interpretation or different proposals. So especially if you are considering relativistic and non-relativistic systems, or it's not the point. It's about we must look differently the quantum measuring problem. So after that, and a lot of efforts, Professor Mario Barbati wrote this essay. It's on the website of Institute of Arts and Ideas. It's an essay for everybody, for everyone, and we wrote this review about the quantum measuring problem, dealing with these recent trends, considered not just interpretations, but the new theories about it, like from Bohmian mechanics to collapse theories, objective collapse theories. And of course, that was a little bit of advertising. And this is our group, Light and Molecules. Professor Mario Barbati is the leader, group leader. And the postdocs and Stefano Barbotto, Matheus Bispo as PhD candidate, Tahir Hafiz as a master candidate, our visitor, Gabriele Uzzolino, and me and Rafael Matos and Dmitry as postdocs there. And dealing with this problem, just me, Professor Mario Barbati, and Rafael. So I would like to thank the funding agencies those agencies supporting our work. Subnano project from European Research Council, AMIDEX from the Aix-Marseille University, and the Institut Universitaire de France. So my last words is about all of us know this famous phrase, right? Shut up and calculate. Helps in day-to-day work. However, we shouldn't either give up on the foundations, nor adopt a pet interpretation. But I think, it's my opinion, we must challenge all of them and do not stop searching for a fundamental quantum mechanic theory to guide and improve us in binding the classical and quantum worlds. Thank you for listening, and I'm open for your questions.
So, very interesting and fascinating talk, actually, but my question would probably show that I didn't understand much. So, in all textbooks say that when you have atomistic, like molecules or atoms, gravity is the last thing, the weakest force which acts on them. So, if you have a molecule, it interacts with environment, with other molecules, like we are electrostatics, and we always disregard gravity. I mean, there are some textbooks which, like undergraduate textbook, which say, no, we don't consider gravity for molecules. And what makes it so special for collapse? And why it doesn't collapse due to interaction, like electrostatic? Well, if it's very small, we always...
It's very small, obviously, but I mean, you shouldn't dismiss it.
Yeah, I'm not dismissing it, I'm asking. I'm saying that I didn't really understand.
Drop off a building, you'll know what it feels like.
Yeah? So, can you basically argue with that?
Yes.
Explain me what it makes gravity so special that we have to take into account such a weak force.
Yes. Yes. Thank you for your question. It's a great question because... Oh, sorry. Thank you for your question. Sorry for this phone, the technical... It's on me. But thank you for your question. It's a great question because this approach surprised me also because I came from the quantum gravity background. So all the time I never heard about this, using so small guys to compute collapse time. But following the Penrose and the Yoshi idea, it's about to consider systems, consider mass distributions in general. So if you are dealing with huge molecules or you are dealing with big systems, we could show something about to compute the collapse times. As we know, the coherence is already well understood, but the collapse time, I think it's a different pathway to measure different systems. But since the proposal is totally agnostic about which kind of system we're dealing, why not molecules? Why not big? Because when we are, of course, I confess, from my side as a physicist, a theoretical physicist, I have just these basics about the molecules and the chemical world. But in chemical world, you can deal with huge proteins, complex systems, and some of them can approach to the condensed matter systems. And sometimes we are facing just using Einstein's equation. You can see small masses and okay, it's not sensible to do with this building energy moment tensor, for instance. But the idea is simple. We are dealing with Schrödinger equation with a modification. We are dealing with states consider the mass distributions, we are counting with a number of operators. So at some point, molecules are sensitive to that. According to Diyoshi, with this proposal, with this basis on continuous spontaneous localizations, we have this freedom to test this model, using even from small guys to the big ones. See, I think before the work, please correct me if I'm wrong, but before the work by Zeilinger, Arndt, and co-workers, I think that was amazing about to see carbon-70 showing superpositions, right? So carbon-70, I think it's not the biggest molecule in a chemical world. It's a small one. So the basic motivation is about okay, if you see that if we see superposition, we are trying to understand the localization of the wave function here in the macroscopic world. Why not? And the Oshy-Penrose proposal is about a mechanism to try to understand that. And I think if you can reach a full theory about to measure collapses, especially computing collapse times, we can see a new path for quantum mechanics without the extra postulate to do measurement. We know there is a industry to deal with the quantum measurements, especially, okay, successful ones, right? But I think we could start with this primal tentative to understand, since the simple systems like the isolated ammonia, but as you see, as you saw, using just a simple molecule, it's not a good deal because we found this 10 to 9 years to see collapse. But after that, we see another problem with this. But the problem could be about the model. But using continuous spontaneous localization, we can solve some problems, even this scenario using molecular systems. I don't know if I answered your question, but I think in some point, it's worth it to deal with this.
Just a couple of comments. Firstly, I think I'm right in saying in neutron interferometry, they actually have to take account of gravity, because you can see if you run them over a long time, they will actually start to dip, and so you do have to. I think it's neutron interferometry where you have. But anyway, and I think that I don't know where they're up to, but Marcus, the last time I was talking to him, they were actually using bigger molecules. I can't remember how big. I'm sorry but I mean, it's in the literature. They are. I think he's setting the world record every few years. He seems to come up with something else. And also, I'll show you tomorrow. We drop molecule atoms, but that's a totally different scenario. The question I wanted to ask you was, in your experiment using the Talbot Lau, you were talking about setting them up so that there was a third of a day travel time. Did I get that correct? Your Talbot Lau experiment, that you said there was an 8-hour travel time between?
Yes.
Yeah. Now,
yes.
Was the gravitational field going to be, so were you going to drop them vertically?
Okay.
Or was it, because what I'm trying to get at is that its orientation, or were you going to do this as a satellite experiment and maybe take it up into space where you might be in a non-gravitational environment? So I think, but the last thing I wanted to ask you was that whatever atom that you use, your ammonia atom, you've got to be careful, because I don't know if they need to be kind of coherent or whatever, but the trouble with these systems is that they can just quite spontaneously start to spread away from each other. They start to diverge. I mean, we run atomic beams and they just diverge for fun, and you have to. It's like herding cats, you have to get them back again, and so I can see I'm not saying the experiment it shouldn't be done, but I think one has to be aware of when you're doing long distances and long times, that there are effects come into play that you might not think about at the outset.
Well, yeah.
That's just my experience. Sorry.
No, thank you very much for your feedback, because I think when we proposed that Talbot law experiment, I think that time we were aware about the difficulty to handle with this, especially because of the main effect. See, it's like when we deal with this system, we understand that we put aside the electronic cloud to far away of the electronic cloud, the electronic part of the equation, just dealing with the nuclear masses. So I think at some point that proposal, it's about to deal with these difficulties considering the environment as you shared with me. And I think it's considering experiments in outer space, I think it's very difficult to handle with that. But yes, I don't know. I think you know about the Ulbricht, Professor Ulbricht team. Now he's trying he's conducting some experiment using this some satellites orbiting the Earth to try to understand this collapse, this objective collapse equations about to see the collapse times. So, or even now we have this in literature. We have this clarifying articles about the coherence times, about the coherence process, considering macro systems, mesoscopic systems, I think. But thank you for your.
So just clarification. As there are prospects to make an experiment which will see that there is a really collapse, the coherence is just changing the equation. So the question if there is a collapse or not, this is very important. So are these experiments feasible to be clean enough to see the gravitational collapse or not? Because you showed different numbers and it looks like they are not, but I just want your confirmation.
Yes, thank you for your question. And I think, yes, we faced this situation about to understand the difficulties about to compute the collapse time and the coherence time. So at some point, I think this first contribution was about to show we can deal with atomistic models, but we don't understand fully the difference now, the behavior about how to compute collapse times using just theoretical approaches, but considering different like tabletop experiments. We don't know. I think it is important to see we have this proposal about this tabletop experiment is about to understand the collapse before the coherence, and using this this knowledge about the coherence time about some well-known systems to see if you can we can compute collapse times. So to see the difference. But now I can, for sure, I don't know if you have this final proposal to test this. But in some point, I think the results are about to understand how to use this hypothesis in the chemical world and the molecular world. So I think there is a limitation about our results, of course. And now we are trying to understand different systems to see if you can compute collapse times in different scenarios. So.
Okay, thanks a lot. We need to move on to our next speaker, please. Please applause for our next speaker. Just sit right there. Okay. Thanks. Okay. So our next speaker is Nelson Pinto-Neto, from Rio de Janeiro on the Bohm quantum theory and its application to quantum cosmology and update. Okay.
So first of all, thanks for the organizer for inviting me to, what? Okay. For inviting me to give this talk. Well, I will talk about something, I suppose, very different for you, which is the application of the Bohm quantum theory to quantum cosmology, which is, I think, a subject that you are not so much familiar. So I will try to be very pedagogical. And not only I will try to show you that the application of the Bohm theory is not only gives a very nice picture, a clear picture of what is quantum cosmology, but also it gives some results that might be attested by observations. So I think it's a very interesting subject. So first of all, I will talk about just what's cosmology. About cosmology, well, cosmology is described by a standard cosmological model, which has a lot of success. Of course, there are some puzzles, some tensions, but it has a lot of very nice results, predictions, which have been observed by astronomical observations. But anyway, this standard cosmological model has a big problem, which is it has an initial singularity. So all Friedman models, which are the basis of standard cosmological model, possess the singularity. And not only that, if you enlarge the model, these singularities still persist. They are still there. So, and that's a point where no physics is possible. Now, in the singularity, the volume of the universe goes to zero, because, as you know, the universe is expanding, and if you go back to the past, if the universe was smaller and smaller and smaller, but with no end. So in the end, if you go back in time, you see that the volume of the universe was zero. So this is a singularity where no physics is possible. And that was one of the reasons that Einstein rejected the Friedman solution, was the presence of this singularity. But when he was forced to accept it, he claimed that this initial singularity was showing us the limits of applicability of general relativity. And so you have to, when you are approaching this regime of very high energies near the singularity, you should go to another kind of extension of general relativity. So there are some proposals, non-minimal couplings, which are couplings that are not standard between gravitation and other matter fields, or nonlinear curvature theorem, so extending also the gravitational theory, and of course, quantum effects. Okay, perhaps when we have this high energy period, then you should perhaps take into account quantum effects. Okay? Now, the question is, does quantum cosmology make sense? If you stay in the Copenhagen interpretation, the answer is no. Because in the Copenhagen interpretation, it's very important to have a classical domain with classical observers, which will bring to actual facts the observations that we make. So without the classical domain, there's no sense about quantum theory. And so, but if you are quantizing the whole universe, where is the classical domain? Okay, so within the Copenhagen interpretation, there is no quantum cosmology. And Rosenfeld already said that. So within the Copenhagen interpretation, you are stuck. You cannot go anymore. And I think this is a very nice example of something that Einstein said about the contact interpretation. He said, contemporary quantum theory constitutes an optimum formulation of certain connections, but offers no useful point of departure for future developments. And I think this is a realization of this criticism that Einstein made. Okay? So fortunately, there are alternative quantum theories or quantum interpretations, like the many worlds, consistent histories approach, spontaneous collapse, and of course the de Broglie-Bohm. Well, I was always fascinated with this subject, quantum gravity, quantum cosmology, so I work with other possibilities. And in my experience, the one that gives the clearest results, the results that are simpler to understand, was the de Broglie-Bohm theory, and that's what I will talk about to you now. Okay, so if I'm going to quantize cosmology and gravity, I have to explain that, cosmology, in cosmology, the major interaction is gravitation, because at large scales, the gravitation is the most important interaction. If you are high energies, then other interactions become important also. So you have to deal with gravitation, and the theory of gravitation nowadays is general relativity. So I have to discuss with you how to more or less recently quantize relativity, and for that I have to show you how to obtain the Hamiltonian and what does the Hamiltonian means. So, and also you must remind, I think you know that general relativity is a geometrical theory. So big masses do not interact by forces. Big masses curve space-time around it, and the other masses follows geodesics of this curved space-time. That's the picture of general relativity. So it's a geometrical theory. And so what is this dynamics of the geometry, so this geometrical dynamics? Let me try to show you this. So these are space-like hypersurfaces, okay? And this is the time direction. Note that I'm not putting the time direction orthogonal to the space-like surfaces in order to be quite general, okay? And so this is the one space-like surface with intrinsic metric h. This metric here just gives the distance inside this space-like surface. And when you go a little bit further in time, this coordinate time here, then you have another geometry, okay? Of course, there is also the normal to the space-like hypersurface, which has its own time, and the relation between this time with this general coordinate time is given by this, where this n here is the so-called lapse function. Of course, you can also project this vector here to the space-like hypersurface, and this gives a difference in the space-like coordinates, and this is proportional to dt, and this thing here is the so-called shift function. Okay. Now, in terms of these quantities here, the line element can be written in this way. This is the n and I, and this is the space-like geometry. Now, this theory should be covariant, okay? And so the Hamiltonian in general, so this is a general formula Hamiltonian of maybe not whatever, but for almost all theories, geometrical theories for gravity. So it's the combination of constraints. So this is n here arises as a Lagrange multiplier, and I arise also as three Lagrange multipliers. And so if you vary with respect to n, you have h0 equals 0. If you vary with respect to ni, you have hi equals 0. These are some equations. In fact, this constitutes 4 of the Einstein equations. Okay. And of course, there are now the Hamilton equations for the trimetric, the metric of the space-like hypersurfaces. And so here is the metric of the space-like hypersurface. This is the momentum canonically conjugated to it. Phi here represents whatever matter field that is there. And pi phi here represents all the momentum canonically conjugated to phi. It's just a risk presentation to you. Now, from the Hamiltonian equations, then you have the evolution of phi, pi phi, and age, and pi age. And these equations here are the other 6 Einstein's equations, and these are the dynamical equations. Okay? So, so in the end, this is the whole picture. So we evolved this hypersurface and the fields inside it through this Hamiltonian in this way. Of course, if you have general relativity, there is an exact expression for H0 and for Hi, but I will keep it, I will not show it because it's too much. Okay? So this is the classical geometrical dynamics. Now I'll go to the quantization, canonical quantization of this. Okay? So again, this is the Hamiltonian, okay? But now, how to quantize it? This is a theory with constraints because the theory is covariant, and so it must have constraints. And then Dirac, well, Dirac was the first one to try to quantize gravity in this way. And he said that, well, when you have constraints, a technical detail, first-class constraints, but anyway, when you have these constraints should annihilate the wave function. So the wave function should be annihilated by H0 in its operator form and by Hi in its operator form. This equation here just tells you that psi should be invariant under the spatial coordinate transformation. And this one here is the so-called Wheeler-DeWitt equation, or it can be something different, but it depends on what is H0 here, right? Now, if you proceed with the canonical quantization, then you have a Schrödinger equation, okay? But as the Hamiltonian itself is a combination of 2 constraints, and as these constraints annihilate psi, then this is 0. So psi does not depend on an external time. That's it, which is quite sensible. Now, usually when you do quantum cosmology, you stop here, and then it's very difficult because this equation here has not the form of a Schrödinger equation. You don't know how to give a measure for psi. There's a lot of problems. I can stay talking about this for an hour. But if you apply the de Broglie-Bohm theory with the guidance equations, then things become a little bit clearer. So here, the guidance equations will tell us, so we have the momentum canonically conjugated to H, which is proportional to H dot, which is the derivative of H with respect to a parameter, is the variation of the phase of the solution of this equation with respect to H, and the same thing for the matter fields. So with this, then you get an evolution for the space-like geometry and for all other fields. And of course, this S here is not the classical action, so this evolution will not be the classical one. And so these are the laws of motions. Now, looking at all of these, okay, I would like to, it's not my proposition, the first one to propose this was Goldstein and Zangi, but I think it's quite sensible. But take a look on this. Well, in classical physics, the Hamiltonian gives the laws of motion, right? But here, when you make the quantization and you see what psi is doing, psi is also giving the laws of motion. So I will interpret psi as giving the laws of motions, a nomological interpretation of psi, which for me is quite sensible because psi is not about probabilities. This wave function of the universe, the wave function of everything that you can think, It's not about probabilities, which is quite sensible because you are talking about the whole universe, a single system, so how to define probabilities or how to define practically probabilities, right? So you don't need to seek for a probability measure, and it's natural that the equation for the wave function of the universe does not involve time, because some law should not involve time. And of course, it should be good to have some boundary conditions to select one solution for the Valia-Allori equation, but unfortunately, we don't have yet. There are proposals by Hartwell and Hawking, Vilenkin, but there's not a consensus about this. But how probabilities arise? Probabilities arise in subsystems contained in the universe by the so-called conditional wave functions. As a simple example, let us suppose that there are only two fields in the universe, phi1 and phi2. And then suppose you have a solution, psi. Suppose one gets the Bohmian trajectory for one of these fields, phi1 of t. Okay. Now I can substitute this here in this way, and then you have a conditional wave function, which will be a function of this parameter t and psi2. Now, it has been proven, and I will show you an example, explicit example of this to you, that under certain conditions, this original equation for psi becomes a Schrödinger equation for this conditional wave function. And so in this situation, as you have a Schrödinger equation, quantum equilibrium may arise, because whatever are the distribution of initial conditions, given that they are soft and that they are okay, then it has been not shown, but it has been indicated that this, whatever is this distribution of initial conditions, it rapidly goes to the psi c square, the Bohm rule, and as a probability measure. So, taking subsystems, we can pass through these steps, then we recover for the subsystems the usual Bohm rule with psi c square. Okay? So that is the program. And now I will try to show you how to implement this objectively. So first of all, I will make a very simple thing, which is I will say, well, the geometry of the universe and the fields are all homogeneous. So they only depend on time. There's no space dependence. Okay? This simplifies a lot all these things. But anyway, it will be important for us. So I will take, for instance, a simple scalar field, a canonical scalar field, which has energy momentum like this. Okay, this is scalar field. There's an energy momentum, so the kinetic term and the potential term. Its pressure can be defined in this way, phi dot square minus v. And this is the Hamiltonian this is Hamiltonian for this. This alpha here is log of the scale factor. The scale factor is the thing that gives the physical distances in space. So this is the thing that gives the physical distance in space. And the singularities appear when this A goes to 0. Because when A goes to 0, of course, the volume goes to 0, right? Because this gives the physical space, the physical distance, okay? So this is the part related to geometry. It simplifies a lot. This is the only degree of freedom in case you suppose that the geometry is homogeneous and isotropic. And this is the part of the scalar field, okay? Now, it can be shown very easily that when you approach the singularity, this kinetic term becomes much, much bigger than the potential, whatever is the potential, unless very special cases. And so you could neglect the potential when you are approaching very high temperatures. And then what you arrive is that the pressure should be proportional to the energy density, And so the energy density would go with a to the minus 6. So you see that when a goes to 0, rho goes to infinite. And it can be shown, but I don't have time to show it, that if you have a canonical scalar field, this is the energy density that will dominate near the singularity. Okay, that's why I'm focusing on it. Okay. Now, if near the singularity, so if you take v is equals 0, if you neglect v, then the solution of the classical solution is alpha equal plus or minus phi. So what you have is that, you see, a equals 0 is alpha minus infinite, right? So you have a universe emerging from a singularity and expanding forever, or a universe contracting from infinite and going to a singularity. So these are the classical solutions. Okay. Now I will apply this scheme that I explained to you. Then I will turn these things into operator. It must annihilate psi. And this is a simple Klein-Gordon equation, which we solved. We got a wave function. You got the phase, and then you calculated the trajectories, and that's what we obtain. We obtain a universe that is contracting from infinite. Classically, it will go to a singularity, but quantum effect stop it, makes a bounce, then it begins to expand, and then it goes to the classical evolution. So you see that using the de Broglie theory, you can see clearly that quantum effects are avoiding the singularity, and this is a cosmological model without singularity, which can be connected to the standard model in the expanding phase. Okay? So I think it's a very first thing that's quite interesting. Okay, so this is for some background, but our universe is not homogeneous and isotropic. If not, so we would not be here if it was homogeneous and isotropic. So what is the picture in cosmology? The picture in cosmology brought by observations is that in the early universe, the universe was really very much homogeneous isotropic, but it has inhomogeneous perturbations. These inhomogeneous perturbations increased during the evolution of the universe, and then they gave rise to galaxies, stars, and all these things, and us. Okay? And so the picture for the early universe, the most realistic picture for the early universe, is saying that there are some... So this is a more realistic picture. So you add to the line element this thing here, which is an homogeneous perturbation. It is much smaller than 1. Okay, so it's a perturbation. It is related to the Newtonian potential in the non-relativistic limit. And this eta here is just a conformal time, which is related to cosmic time in this way. It's just a useful time that we use. And again, the matter content is canonical scalar field phi. Now I put this, I will calculate the Hamiltonian using these things here. And then what I get is the following. I get a first part, which is the background part, which is the same as the one I discussed before. And also I have a second term, depending on the perturbations. And this V here is the variable describing the perturbation, and pi V is its canonical momentum. This V here is a combination of the Newtonian potential and the perturbations on the scalar field, which has a lot of very important properties, which I cannot discuss here with much detail. Okay, and now I will make a Dirichlet quantization, so this thing must annihilate psi. Okay. So you get this, and now I will make this as an assumption. Okay. I make an assumption that there is a psi 0 depending only on the background part, and a psi 2 that depends, of course, on the perturbation part. And then when you apply this to this equation, you find a zero-order term, which is just the one that I have solved before. So what I made before continue to be valid here. But now, when I go 1, so when I try to see what happens to psi 2, now I use this idea of the conditional wave function, which is it's very usual in the de Broglie-Bohm theory. So once I solve for the background, I put it here. So I have the conditional wave function here. And then I put in the equations, and something that is very interesting is that there is a term there in the equation, which is this thing here, where S is the phase of the background wave function. And now, this is very important. Because I'm using the Broglie-Bohm theory, this guy here is the time derivative of A, and this guy here is the time derivative of phi, and really there is a minus sign between two because it's a technical detail. And if you read this, this is just d eta of this conditional wave function. So a term like the ddt of the Schrödinger equation appears naturally. But look, it was very important that I could use the guidance equations here in order to obtain this. So it's another way to say that the Broglie-Bohm theory is very useful to understand all these things. Now, when I put all these things together, well, as it is a perturbation theory, I can write psi as a sum, a product of psi k. This is the wave numbers, and the equation for each k is this thing here. This is the v there, and this is some function of the background, and the equations for the modes is this thing here, where now z is calculated from the quantum Bohmian trajectory. So the quantum Bohmian trajectory will affect the perturbations. Okay? Now, let me now connect all this with observations. Okay? And the most important observations for one of, well, not the most important, but it's one of very important observation for cosmology is the observation of the cosmological cosmological microwave background radiation. Okay? And so this is very important because it's a picture of the early universe. Not so early, but a universe with 300,000 years just after the beginning of its expansion. The universe is more or less 14 billion years after the beginning of its expansion. And the picture of the CMB is about 300,000 years just after the beginning of the expansion. So it's very, very early. And so the measure of this CMB is very, very important. It gives a lot of information about cosmology. And the last measurement was made by this Planck satellite, which made in European consortium. And what is the idea? The idea is, you have this V, which is the perturbation, right? This V is connected to the perturbations in the energy density. And of course, the perturbations in the energy density gives perturbation in the temperature in the CMB. Because the CMB, as you see it, is a Planckian distribution, photons that are coming to us, with a constant temperature. You look at all directions, and the temperature is the same, 2.7 degrees Kelvin. But it cannot be the same because if not, you wouldn't be here. So if you have these fluctuations of the energy density, so at some point where there is some more energy density of matter, the light that comes from it, because of this a little bit bigger gravity, will be less energetic than the one which comes from a region where there's not so much energy, and then the temperature of the photon will be a little bit higher. So these fluctuations of the energy density implies in some fluctuations of the temperature of the microwave background radiation, which has been observed. Okay. And so this is the result. Okay, so there's two-point correlation function of these temperatures, because what they do, they make the difference in some angle, then this angle, then this angle, then this angle, and makes the two-point correlation function of this. And and everything is written in terms of this power spectrum, and there are two quantities, this A and this NS, and the result is that this NS should be very close to 1, and this A should be 10 to the minus 10. Okay. This thing here gives a lot of information about our universe. For instance, that this peak here is in about 1 degree, tells us that the space-like hypersurface should be almost flat. So the information that comes from CMB is very, very, very important and very rich. Okay, now going to our theory. So I have 10 minutes more. Okay. And let us see about our theory. So these are the equations for the modes, remember? But in order to solve it and have a V as a function of K, I have to give some initial condition. And one initial condition that's usual in cosmology is the following. This term here, when the universe was very, very big in the past, this term here becomes very, very small. And then, if you are very, very far in the past of the universe, the only thing that is present is this term here. And so this thing here is just a bunch of harmonic oscillators. And if you say these harmonic oscillators are in the ground state, okay, so-called the adiabatic vacuum, anyway, it's a technical name, then you can say that at this moment, the V should satisfy this thing here. And if you have this, then you can solve this equation completely with a specific initial condition. And in the end, after making some many calculations, you'll find that the NES, which is the thing that is measured here, which should be close to 1, is given by this formula here, where this W here is the ratio between the pressure and the energy density of the scalar field when the perturbation scale begins to fill the space-time curvature. Because in the situation here, when the universe is very, very big, the fluctuations doesn't feel very much the curvature of space-time. But then when the universe contracts, then at some time it will begin to feel the space-time curvature. And it is in this moment that this W appears. It's a very important moment, but I cannot tell much details about this. And so the conclusion is that at this moment, what we should be dominating the universe is some field which has an effective W very close to 0. Okay, perhaps dark matter, but this is another thing. But anyway, this is the result here. So if you have this, then that's okay, and the amplitude, of course, is okay also. But I have enough time to talk about the amplitude. However, there is, and here comes again the importance of the quantization. However, this picture has also been analyzed by another approach to generalize general relativity classical extensions of general relativity. And in these classical extensions of general relativity, there is the problem that you don't have only scalar perturbations, we have also tensor perturbations, which are responsible to giving rise to the stochastic primordial gravitational waves. And the Planck satellites tells us that the ratio between tensor perturbations and scalar perturbations would be much smaller than 0.1. And if you make all these calculations using using only classical extensions of general relativity, you get that this is bigger than 0.1. So this is a problem. Now I will show you an example on how the quantization helps to solve this problem. Now I will have to talk a little. I put a potential here. Why I put the exponential potential? The exponential potential has some motivations from string theory and all this. Okay, and classically, what happens here? Classically, what is the evolution here? So either this is the singularity. The evolution is always in this circle here or here. So you can have that the universe comes from singularity, expands. Then here the scalar field behaves as dark energy, and then it expands forever as just dust with pressureless matter. Another possibility is that the universe contracts from infinite, behaving like dust, pressure equals 0, and then goes to singularity. Now, there is but remember, when you are approaching the singularity, this thing here, the potential is negligible, then you can use the Bohmian quantization to connect these 2 points. And that's the thing we calculated, we did it. And then, so what happens is that you go to this way, and then there is the quantum effects that makes the trajectory going this way, and then you come back to the quantum evolution, the classical evolution. So what is very interesting is the following. Let me try to explain to you a little bit better. So this is the scalar perturbations, okay? And these are the tensor perturbations. When they are much smaller than the curvature scale, they are only oscillating, as this equation, the equations here tell to you. They are just oscillating, and then they cross, they begin to fill the curvature of the universe, and then they increase like this. But you see that they increase both at the same rate and the same amplitude. Now, when you are near the singularity, for any classical extension of general relativity, this x here is always of order 1, and this is the thing that describes the evolution of these 2 things here. If x here, which is the phi d alpha, is close to 1, they are more or less the same. But because of the quantum bounce, this x can become very close to 0, and this makes the scalar perturbations increase a lot with respect to the tensor perturbations. So this is a phenomenon coming from the Bohmian quantization of the bounce, which is pushing the scalar perturbation to be much bigger than the tensor perturbation as it was observed. So maybe, of course I'm joking, but perhaps you have just observed an effect of quantum cosmology coming from the Broglie-Bohm theory. But of course, there are many other you can have many other justifications about this. So just to end, let me go. Just to say this thing here. There's not a single observation under, how much I have? 2 minutes? Less than 2 minutes? If you wish to answer. Okay, so I will jump this conclusion here. And I'll just tell you, well, the Broglie-Bohm theory is very suitable for quantum cosmology, psi-nomological, probability secondary. Well, yeah, they didn't have time. It was presented a quantum cosmological effect with a sizable observational consequence, which is the R less than 0.1, which would not be there if the model were entirely classical, and which we have already seen. Now, we always thought about quantum theory helping cosmology by solving the singularity problem, but I think also cosmology can help quantum theory by offering a possible arena to test different quantum theories. And finally, I will just tell you something about using Bohm here. I think quantum cosmology may be seen as an interesting concretization of some latent subtle David Bohm's concepts. I would say, I don't know if you agree or not, but I would say that the functional wave function, perhaps the Euler-Dirichlet equation, and the wave functional of the universe which arises from it are related to the wholeness and the implicate order. Now, the guidance equations which emerge from the wave function of the universe and the Bohmian solutions obtained from it constitute the explicate order emerging from the implicate order. So that's something that I think it's interesting, and it's a nice concretization of these ideas of David Bohm, which are the implicate and explicate order. Okay, that's it. Thank you very much.
Great, thanks. So in limit of the fact we have a coffee break coming up, I'm going to limit to one question, and that's coming from me. That's my prerogative as the session chairman, I guess. And in your talk, I may have missed something, but you had the number 300,000 years after the Big Bang as a time scale for, which I understand to be the time for which a scalar field begins to feel the space-time curvature. Was that, did I understand that correctly? The 300,000 year number that you throw out?
No,
No?
Well, in 300,000 years, what is dominating the universe are many things.
Yeah, yeah.
Okay, the scalar field is something which would be very important near the singularity.
Got it.
Okay, because it will dominate all the other fields. Okay? If there is this scalar field, of course, if it is there, if there is a canonical scalar field there, then it dominates near the singularity.
Sure.
But afterwards, then other things will come to action.
But I guess like I'm sort of curious about the origin of this 300,000 years, because it also it coincides with the time scale for which atoms became stable.
Yes, more or less coincides because first you have plasma with electrons and protons. And then when they combine to form the first. And then at this moment, the photons become free to come to us.
Okay, that makes sense. Okay, thank you. Let's have our questions over coffee then, and thank both speakers. And okay.
I'm sorry.
A lot of things to say.
Okay. We have a big lineup coming up. We have 3 talks in a row. So if you have a really deep, long question, please save it for dinner. I'm sure it will go great over wine. If we can get through, I'd also like to propose everybody standing up between talks just to sort of get the blood flowing back into your legs. Don't leave your seat, but just sort of stretch a little bit. Because we've got, don't leave your seats. Don't move around too much. That way we can all enjoy the last 3 talks. So with that, Ángel, please begin.
Thank you, Eric. Thank you to all the organizers. Eric Valdir, who is somewhere here. Good afternoon. Buenas tardes. It's a pleasure being here for me after a long time without seeing many good friends. Some of them, unfortunately, are on the other side of the wall, of the screen. Well, what I am going to talk today here about is Bohm mechanics. Well, the title says that, but it is not the usual Bohm mechanics. Okay, the take-home message that I want to convey is that Bohm mechanics is something else apart from an interpretation. It's a working tool. Okay, and that we can, as a working tool, we can apply it not only to quantum problems, but also to non-quantum problems. By non-quantum problems, Specifically, I refer to optics. And why is that? Because, as I'm going to try to convince you, Bohmian mechanics is about phase. Actually, wow, phase variations in space. And this has a very direct relationship to the dynamics that we observe, both in quantum mechanics, but also in optics. So, why do I start with the Aharonov-Bohm effect, the seminal paper? Well, because there we can see that there is no operator that describes this phenomenon. Still, we can detect it. Well, actually, it was predicted earlier on. Okay? In this paper by Ehrenberg and Sidai, they mention the word refractive index. So refractive index has to be with how the materials or how matter reacts to some signal. Which signal? Just fields. Well, specifically, as you all know, we have a shield flux, magnetic flux, and still electrons can notice its presence. Okay, we can see that there is a phase shift because of the action of some enclosed field. Maybe you, Leaf, will not be in agreement with me because you have this other different perspective. But still, well, we have no field there, or we cannot see it, but we feel the phase effects. Well, related to, this nice proposal or suggestion was corroborated experimentally by Tonomura and his team in the 1986. Why do I show here the picture? Not only to illustrate that Bohm's effect is, the Aharonov-Bohm effect is a reality, but also because this guy here, Tonomura, is another main character in this other experiment. Although Rob said that, I think it was in the 50s, when some Germans showed the first recordings of electrons arriving on a plate. Okay, later on, Giancarlo Pozzi also showed that in the 70s. The first movie that we have with this clear picture of the formation of interference fringes, was produced by Tonomura. Just a couple of years after the previous paper, the one about the Aharonov-Bohm effect. Here we have another phase effect. We have no observable, we have no operator describing what we are observing, but still we can detect that. Okay? Of course, if we talk about Bohm mechanics, this picture illustrates very nicely Tonomura's experiment in terms of trajectories. It's a very well-known picture. And here we have the quantum potential that would guide these trajectories up to the screen where we collect those electrons. This was produced in 1979, so published. A year later, we have this other picture where the two Chris Philippidis and David Bohm, reproduced the Aharonov-Bohm effect. So the two examples that I have shown before were immediately treated within the Bohmian realm. Now, let's go to the point of the talk. Given that there are phase effects that are not related to quantum operators, that is to to quantum postulates, okay, should we treat Bohmian mechanics, or what we call Bohm mechanics, as a quantum interpretation or a quantum interpretation? If we can see that it is a representation, leaving aside all the connotations related to representations, does it add anything new? This is a typical reply that one gets from the referees when you try to publish something on this stuff. Well, now another way to formulate that question is whether we can extend this to other fields of physics, that is, whether it is more general than simply the quantum realm. in order to cope with these questions, we are trying to understand first what's exactly Bohmian trajectory and what can it be good for, okay? What's the applicability of this? Well, let's go to David Bohm's paper, seminal paper. Here, we find that as long as, he says that as long as the mathematical theory retains its present general form, this suggested interpretation leads to precisely the same results for all physical processes as does the usual interpretation. By interpretation here, I guess that he wanted to mean the theory, the quantum theory. That is, this approach, Bohm's theory, is actually quantum mechanics. This is something that I discussed in many occasions. I had the chance to discuss in many occasions with Basil Haley. We both agree that Bohmian mechanics is just quantum mechanics. So, the good thing about this suggested interpretation is that it provides a broader conceptual framework and it makes possible a precise and continuous description of all processes. We don't need to appeal to quantum jumps and all these ideas. So, it is not necessary for us to give up a precise, rational, and objective description of the individual systems at a quantum level of accuracy. That is, we can still have a very nice and intuitive picture of quantum processes without thinking that everything is inside a black box. This is basically what this David Bohm wanted to convey us. Now, let's use simply quantum mechanics, standard quantum mechanics. We start with Schrödinger's equation. If we multiply it by the conjugate of the wave function, and then we subtract the conjugate, the complex conjugate, right, we obtain this conservation equation, this continuity equation. In this continuity equation, okay, this is a standard physics, although it is, I mean, this is mainly discussed in all books, like David Bohm's book or Leonard Schiff's books. The two agents are rho and J, the probability density and the current density. The current density is just the form that the probability density has to spread out in configuration space, in the position space. No? What do we call the position space? Now, and to do so, we need a velocity field. Now, look, if we divide J by rho, we directly obtain this V. But this V, if we elaborate this expression in terms of psi, is just the real part of this ratio here, the usual momentum operator acting on the wave function divided by the wave function itself. So it is a local evaluation of the momentum acting on the wave function. Well, let's work this a little bit. This is all standard quantum mechanics. Well, so we have this picture, a wave equation plus, well, this concept, plus the velocity. Well, let's see what David Bohm says in his paper. What David Bohm says is that, this is conventional Bohm mechanics, if you pick up this transformation relation here, and you introduce it into the Schrödinger equation, you obtain these two real valued equations, differential equations. One is the continuity equation that we have just seen. The other is a quantum Hamilton-Jacobi equation. Quantum Hamilton-Jacobi equation because it looks like the classical Hamilton-Jacobi equation without this term here, which is Bohm's quantum potential. It is a measure of the curvature of the quantum wave function. Only that. Okay? What David Bohm introduces is a postulate. This postulate says, well, if I have a Hamilton-Jacobi equation, then I have a Jacobi law for the motion, and from this Jacobi law for the motion, I can obtain positions for particles. These are the trajectories, and this is what is commonly regarded as a hidden variable. Now, the question
I pose here is the following. Can they be measured? Can these positions be measured? In principle, no. Therefore, I think that the reasoning here is a bit poisonous because it can spoil a very nice derivation. Now, to avoid that trouble, later on, I mean 2 years after the 1952 paper, Bohm and Jean-Pierre Villiers produced another paper about the causal stochastic interpretation. So they just re-elaborate all the theory, assuming that, well, we can consider that the particles are randomly moving, and all this diffusive motion in a configuration space gives rise at equilibrium these laws of motion. Therefore, these positions do not represent the actual trajectory, the actual positions of trajectory of particles. This is a sort of average position or average trajectory. Nelson in 1966 produced a similar model, and later on, Bohm and Basel in 1989 further elaborated this causal stochastic model. So, well, these particles, these trajectories, in principle, cannot be considered as hidden variables. No, in the way that people, local realists, use the concept of hidden variable, local hidden variable. Well, so far there is no evidence, empirical evidence, of the existence of these particles, or we don't know whether real quantum particles move along these trajectories. Instead, what we are sure, 100% sure, is that these trajectories allow us to understand how the quantum state evolves. They are like, appealing to a hydrodynamical analogy, they are like those tracer particles that allow us to see how the flows, the hydrodynamical flows, move and spread out in space. Or, if you want, like this iron crust that allow us to detect the force lines of magnetic fields. Okay, we don't know what a magnetic field is exactly, but we know that we have a field because this iron crust, they just cast over all space in a very particular form. So in this regard, my idea of what a Bohmian particle is similar to having a classical tracer. No? It is a way to detect the evolution of a quantum system. Moreover, not always we are describing with the Schrödinger's equation a particle itself. Many times we use it to describe vibrational, rotational, or whatever modes of molecules. Okay, so we cannot make this happily this identification between particles and these trajectories. Okay, so what we have now, the map that we have now is we have a standard quantum mechanics, everything is correct. We have some of Bohm's ideas, and this gives us quantum hydrodynamics. Quantum hydrodynamics, well, the main actors in this moving are Madelung, who in 1926 exposed that a Schrödinger's equation could be rewritten in terms of hydrodynamical equations, and therefore that the diffusion of quantum systems could be understood in terms of hydrodynamical view. I think that Mordecai is going to talk us about something like this. Later on, Hirschfelder in 1974 started to produce, based on Madelung's ideas, the first plots of trajectories in barriers, collisions, and so. And what is less now known is that Bob Wyatt, he started, sorry, this is wrong. This should be 69, not 59. Sorry, but my eyes start to fail. Well, in 69 and 71, he started to produce the first also studies of molecular collisions with these arrow maps. This ended up in 1999. I think it was you, Eric, who said yesterday about the famous paper by Wyatt and Lopriori. They produced the first computation, efficient computation with trajectories, which gave rise to a community. Some of the people is here. We have met over all these years, you know. And they showed, sorry. They showed that these ideas of trajectories, at least in quantum chemistry, are very useful. And you can get numbers with them, apart from explanations or nice descriptions. So, following these ideas, what we have is not we are going to postulate the existence of these trajectories, but we are going to obtain it. Now we have founded them on the fact that we have a velocity field. Okay, this velocity field has to do with local phase variations. So the description that we can make of our quantum systems relies on, first, local information from a global velocity field. Okay, this velocity field develops with the evolution of the wave function. And we are also going to have a local fluid dynamics that we are going to understand and study through the evolution of the trajectories associated with these local phase variations. Now, having said that, we can see that at least everything is well grounded. There are no, say, philosophical questions involved here. So in the same way that we have different representations for our quantum systems, Schrodinger's wave functions, Heisenberg matrix mechanics, the direct representation, Feynman's path integral, that also found problems for acceptance. No? Remember the 1948 paper, he received the same critics as David Bohm received later with his 1952 paper. Well, the same way that we have all these approaches, we should add here another one, which is the Breuil, Madelung, Bohm, and Takabayashi representation. So we have put everything at the same level. Now there is no ontological or metaphysical question. Now everything is an element just to compute. What can we do with that? Well, there is something very interesting in Bohm mechanics, which is the famous non-crossing rule. Two trajectories cannot cross to the same point in space, configuration space, at the same time. Well, how do we obtain that? Well, we take a superposition, we compute rho, we compute j, and we obtain this equation of motion. This equation of motion, if you observe, has here like the equation of motion for one of the wave packets of the waves, another of the waves, and here two mixing terms. Okay, this is what makes the difference with respect to classical trajectories. Actually, not only this, but also the fact that we have this divided by this term here. So we can have two types of representations. It depends on what we choose to look at. We can have some density-related information, or we can obtain phase-related information. In this plot here, we have the probability density, we have the two-slit experiment, we can see how the interference appear. This is a map of the phase. From here, if we measure the curvature of this state, we obtain the famous quantum potential, okay, as obtained in the 1979 paper, or we can have the velocity field. Okay, I'm going to retain the velocity field. Why? Because keeping the quantum potential, I just keep the same information that I have with the density function. So, and I want to take partly the density, which is going to tell me how particles or tracers group in configuration space, and also, on the other hand, I want to know about the dynamics. And for the dynamics, I prefer to retain this this velocity field. Now, if we plot this in terms of contour plot, here we can see the trajectories. Okay, this is for the density. Here we have the velocity field. You can see that there is a single, the velocity shows that the superposition principle is not simply 1 plus 1. And that it is not something that, well, I propagate one wave, I propagate the other, and then I make the superposition. No, everything has to start from the very beginning. Why? Because something that starts without any phase, it starts developing a phase. But more important than that, there is here a non-crossing line because of the symmetry of the two slits. Okay, there's a non-crossing line that cannot be crossed by the particles. It is forbidden. Remember, if we go to the quantum potential here, that there is a plateau, but nothing else. In the velocity, however, we have this strong kick here, this strong kick here with different sign, so the trajectories are obliged to move towards the end, towards the center, or to split up to other regions, okay? But never mixing. If you remember from this equation, this mixing can be understood in terms of the parity of this term here. We are not going to analyze this because otherwise I'm going to be short of time. Although I think I'm going to be short of time in any case. So what else can we extract from here? Well, we can ask for two questions. One is, in regions, what happens in regions when we have vanishing overlapping? When we have vanishing overlapping, all these terms here, these products here, disappear. And in principle, if we are far away, here in this denominator, only one of these terms is going to influence the motion. So it depends on where we are. So we can obtain either this equation, either one equation or the other. Sorry, because this doesn't synchronize well. The question is who is who? This is a rather interesting question. Another question is, well, if we have vanishing coherence, that is, if all these cosines and sines disappear, we end up with this equation here. But this equation here is not classical. And when we have incoherence, okay, in principle, we should recover the classical world. Well, let's see what happens in the classical world. We are going to study classicality versus quantumness. We are going to approach it from different points of view. So, typically, we learn in class that the classical limit is reached whether we have large actions compared to h bar, or when we have large quantum numbers, or when we have heavy objects. Because, after all, quantum mechanics is always regarded as a theory for very small systems. But is this true? When we think, for instance, of the Bose-Einstein condensates with 10 to the 5, 10 to the 6 atoms, that is not small. When we think about Marcus Arndt experiments with those huge molecules with a very complex structure, that is not small. So I guess that this is a bit tricky. Let's see. Let's go for this large object. Consider just single atoms, single rare gas atoms impinging on a metal surface, a corrugated metal surface. Okay. Well, we're going to have the diffraction by reflection at the surface, depending on the energy. This is for helium. On copper, depending on the energy, we are going to see that these peaks go towards the center. If we represent if we go now to the Bohmian treatment and represent the deflection angle of the trajectories leaving the surface, we obtain this step ladder structure. Okay, this step here is for the central peak. These other steps here are for the following orders, and so on. And this also happens if we make it a standard representation, but in the case of the double slit. Well, if we repeat the experiment classically, what we would obtain is this figure here. Okay, there is a maximum deflection at a given angle, and then the trajectories get backwards again. The deflection gets backwards again. So, how can we pass from here to here? We are going to feed these atoms and going to make them growing and growing and growing. Well, if we consider neon, argon, and something fictitious like 500 masses, the helium mass, we obtain these diffraction diagrams. We obtain something that gets closer to the classical figure. However, it is defined in terms of many, many, many diffraction peaks. Okay? Overall, more or less, we have the same shape, but we cannot reach it. If we go to the quantum, to the Bohmian representation, what we observe is what we have here, that trajectories somehow resemble what we would have with classical trajectories, but this structure of trajectories crossing one to others is never reproduced. Why is never that? Because of the non-crossing rule that we have just seen. Okay? This is a rule that we cannot violate ever. If we want to reproduce that classical deflection function, what we find is that we cannot do it locally. Okay? This deflection function was determined within the area covered by a single unit cell. However, quantum mechanically, we need to observe the global trend. Okay, we need to look at the whole extension covered by the illuminated surface. Okay, so when we do so, and we expand this profile, this classical profile, to cover all the region illuminated, we observe that effectively the Bohmian deflection angles get pretty much close to the classical ones. And there are still oscillations. Okay, here we have a particle which is 1,000 times the mass of a helium atom. But they nicely follow that pattern. So, first, we have seen that the non-crossing rule has not been violated. Second, that we always obtain in quantum mechanics, in the classical limit, global behaviors, but not local behaviors. Now, can we kill this in any way? Let's see. Let's consider what is known as the classical Schrödinger equation. The classical Schrödinger equation is a nonlinear Schrödinger equation with this term here. Where does this term here come from? Well, we want to kill the action of the quantum potential. The quantum potential comes from the action of the Laplacian. The Laplacian, when it's applied to psi, gives us this term, which is essentially classical motion, okay, or propagation, and it gives us this quantum potential. There is another term which has an imaginary component that we are not going to deal with it now here, okay? So let's introduce this term here, coupled by means of this constant here, lambda, with values going from 0 to 1. When it is 1, this action, the quantum potential action, should be completely cancelled out. Is this going to remove our quantumness? Well, if we apply Bohm's approach directly, it seems yes, because we obtain the classical Hamilton-Jacobi equation. However, what happens if we solve this problem? If we introduce here psi, and we try to see what is going on? Well, unfortunately, we have killed the quantum potential, but still we have some effects. What have we achieved with that? Well, we have removed the spreading. Okay, here we have two counter-propagating wave packets, one moving against the other. Okay, we increase the value of lambda, and we end up with this figure here. In this figure, the red and the blue lines are classical trajectories. So you can see that the trajectories starting here, they follow very nicely the classical trajectories. In this region, there is interference still. And in this other region, here, after the collision of the two wave packets, we can see that the bounce trajectories that came from this wave packet follow the classical trajectory that started here. So there is no way to recover the classical limit. Let's go to the classical to the oscillator, the harmonic oscillator, and see what happens there. Well, we have something that looks better to some extent, because, well, here we have our classical trajectories. Here we have the interaction region. Okay, we can see some interference range. This region gets smaller, smaller, and here it seems to disappear. So it's that finally we have achieved just this crossing. But this is, I'm sorry to say, an illusion. If we magnify the picture, we can see that, well, this is when we have the full active and the full quantum potential acting. And here, when we have almost annihilated, we have focusing, a very strong focusing due to nonlinearity. But we have not been able to solve the problem that we had, which is the non-crossing. How can we solve that? Well, let's do the following. Let's assume that we introduce some decoherence. Okay, here I have some trajectories. Okay, for a two-slit experiment with cold neutrons. This was performed by Challinger and colleagues. It was in the 1980s. Okay, here the white dots are experimental data. The black dots are just the results obtained with the Bohmian trajectories, just making a Bose counting of that. Okay, let's assume that we introduce a lot of decoherence here. Yesterday, Lev showed a formula about how to proceed. Okay, we use that formula. Okay, we work with the density metrics, and well, again, we have this damn non-crossing rule here. We have decoherence, but still there is something there. So what is going on here? What is going on here? Why doesn't this appear? Here I have this nice reproduction of this bump, which is the sum of what comes from one slit and what comes from the other slit. However, the trajectories are still detecting that both slits are open, even if I have no phase. Why is that? Well, the reason is precisely that one slit still knows that the other is open. So I need to remove somehow that information in order to observe here the crossing of the two groups of trajectories. If we consider this very simple model, 5 minutes, okay. If we consider here this very simple model, okay, and now I say, well, let's cancel out the presence of one of the slits with this exponential and increase the population of the other slit with the other exponential, or vice versa. With that, we do recover actually what we wanted, which is this quantum result, okay? No trace of interference. And also here we kill the non-crossing. But how is this produced? Well, this is a toy model. But if you consider a full two system or two particle entanglement problem, you can observe that actually you have that. I'm sorry that I'm not showing those results because I wanted to show other things, and finally I'm not going to show the results, neither the other one. So now we have seen focusing. Can we have focusing without nonlinearities? Well, this is a conjecture made by Perez in his famous book, Quantum Theory, Concepts and Methods. Well, let's see. The thing is that there are some functions modulated by a phase, a spatial dependent phase, which behave as such. At some point, they can give us a singularity. Well, Bohmian mechanics are also very useful to understand what is going on there. Here we have a flat top state. Here we have this kind of Lorentzian is Perez ansatz, and here there is a Gaussian, but there is a special Gaussian. It's a Gaussian with an added phase. Why? Because if we add those phases, now we know that because Bohmian trajectories, okay, tell us that phase is very important in quantum mechanics, we can play around with that, and we can make in a spontaneous way to appear a singularity. Here we can see how this looks in the case of Perez ansatz, how the trajectories get very closely packed without doing anything. Now, and where do we observe, or where can we find these behaviors, or where can we produce these anomalous behaviors? Well, in optics, we have spatial light modulators that allow us to modify the phase of the light and produce this kind of stuff. Actually, the next example I was going to talk about was precisely about this experiment with weak measurements, okay, to infer the Bohmian trajectories for photons. Okay, this is based on this idea of having weak values. But as Basil says, rather than weak values, maybe we should call this transition probability amplitudes. Actually, this idea, well, something that we also discussed many times, this idea traces back to a paper dating to 1978, I think, from Joe Hirschfelder also, who introduced the concept of transition probability. There, he already somehow gives a clue on how these things would help us to understand quantum mechanics in a different way. Well, the idea basically is that if we are going to perform a post-selection with a given basis, and the wave function in this basis is going to render some eigenvalues, if the operator that we used, okay, I mean, if these eigenvalues of the operator that we want to measure is fine, we obtain the usual densities. But if we do not use that basis, we obtain something which is a bit more complicated. Sorry. This is actually what we call the weak measurement. Let's see in the case of a post-selection in a spatial basis set. Okay. So here we have the usual position density, or the average of the position, and if we operate in the same basis with momentum, we obtain these expressions here. Okay. Well, if we introduce the Bohmian ansatz here, we obtain that here. Yes, I am over. Well, yeah. we obtain for this for this weak measure this expression here, where this is the Bohm's momentum and here this is the so-called osmotic momentum. When we average, this osmotic momentum disappears and we retain only this average of Bohm's momentum. So this allows us, using a famous Feynman's quotation that same equations have same solutions, allows us to apply it to optics. And actually, when you do so, you can find a one-to-one correspondence between quantum mechanics and paraxial wave optics, which allows you, for example, to explain in a very nice and simple way why Steinberg obtained that without the use of Bohmian mechanics. And why I say without the use of Bohmian mechanics, because Bohmian mechanics is supposed to be applied to massive particles, particles with a mass, and not to light, ordinary light, which is what, in the end, Steinberg used. Of course, you can use it also to describe other types of light, like structured light. Okay, you can see here some airy beams. Sorry about this. Okay. So, we have seen, and with this, Eric, I will finish. We have seen that Bohmian mechanics is actually a very comprehensive representation of quantum phenomena, but also of non-quantum phenomena. Why? Because phase coherence is very important. Okay? The essential element in quantum mechanics is phase coherence. It doesn't matter whether we are dealing with spatial coherence or with time coherence. This is the key in quantum physics. Okay? So in classical physics, why it is not so important? Why can't we have trajectories that cross and do all these weird things? Because this phase coherence does not exist. So, and with this, thank you for your attention, and thank you also for your patience.
We have 2 minutes and 40 seconds for questions.
So my question is, I didn't quite understand. For the free particle, when you went to the classical limit, the trajectories did cross?
No.
No, they still don't cross.
They still don't cross. You need to break that in some way, and this is only possible through entanglement. Entanglement makes that that the subspace of each particle decouples, and therefore, when you study the trajectory associated with each particle, they are going to appear like overlapped.
So you know, we've had discussions over the years. We have this variant on Bohmian mechanics, which we call Bohmian mechanics with complex action. And then the RS, the phase is complex valued, but we have no amplitude factor. And what happens there is that there's no problem with the trajectories crossing. And so the conclusion that the way my thinking has evolved is that we usually say that the Hamilton-Jacobi equation is equivalent, the classical Hamilton-Jacobi equation is equivalent to Newton's laws. But I'm not sure that that's true, because the classical Hamilton-Jacobi equation breaks down when you have at a single coordinate, you have two different choices of momentum, and that's exactly the crossing. So it's not only Bohmian mechanics that has no crossing, but it's also the classical Hamilton-Jacobi equation can't deal with crossing.
Yeah.
And so if I have to choose between the classical Hamilton-Jacobi equation and Newton's laws, when I have two different choices for momentum, I would choose Newton's laws.
Yeah, but I mean, Newton's laws plays with the advantage that it is a theory that goes to the configuration space, which, I'm sorry, the phase space, which allows this kind of crossings. However, quantum mechanics is everything compressed. We can see this, for example, when we plot the Wigner distribution. With the Wigner distribution for the Gaussian is something boring. But for any other state, you know that there are regions with, negative regions. Well, the reason why these negative regions appear is precisely because of that, because of this compression in a single space, this position or configuration space. But of course, if you change and you go to the complex Bohmian mechanics, things. I don't know why, because I have not studied the structure of the theory. I mean, just the mathematical details. But it's nice because there, of course, you can have many other motions and all these crossings and nothing happens. So, to me,
what happens is that the quantum potential is very different. Instead of AXX over A, and A in the denominator, every time it goes to 0, you get an infinite potential. But our quantum potential is just SXX. There's no denominator, so there's no problem. There's no infinity when there's no infinite potential.
Yeah, but my feeling is that there must be a connection between this complex version of wave mechanics and statistical mechanics, Boltzmann's entropy and all this stuff. Because at some point I hear that Schrödinger got this idea of the wave function, the way how it is formulated, taking these Boltzmannian ideas. But I have to find the paper. I know that it's a paper, but I don't know where.
Okay, I think that's probably 2 minutes.
Yes.
39 seconds.
Very nice. Okay, next speaker. Awesome. Okay, Sophya Garashchuk from University of South Carolina. While she's getting it queued up, I would say been one of the people has really pushed the idea of getting this whole Bohmian trajectory idea to work, finally, along with Bill. Stand up, everybody. Stand up on your toes. Get the blood flowing. Take the time. If you don't stand up, you have to be the session chair next time. Okay, go ahead.
Okay, thank you. So as I was preparing this talk, I had to go back maybe 10 years, as it's maybe computational Bohmian mechanics, for those who don't know this field. So I'd like to acknowledge people who contributed to the development of the theory and implementations. Vitaly Rasulov, he's here. Also Jacek Jankowski and my 3 former group members, Jim Mazuka, Bingu, and Lei Wan. I also want to acknowledge people who kind of drove me to this field. I've taken James Cushion's class on interpretations of quantum mechanics. They introduced me to Bohmian mechanics when I was a graduate student. Also David Tanner, who made me think about trajectories, and also John Light, Bob White, and George Schatz, who were supportive in implementing Bohmian mechanics and kind of making a computational and theoretical method out of it. So we have very diverse, scientifically diverse audience here, so maybe you will not remember much, but at least I want to say that there are quantum mechanical effects with the nuclei. So I'm interested in nuclear quantum effects, and my quantum particles are, let's say, protons, low energy, low temperature. You can have tunneling in an enzymatic system, as it is shown here as an example. So we have a hydrogen, proton tunneling from carbon to oxygen, and experiments show that tunneling is important there. We can have nuclear quantum effects on properties of thin films relevant to photovoltaics. And of course, this is one other example where we actually have electronically non-adiabatic dynamics. So this is an example of quantum effect, which we often kind of model with trajectories, but in reality, there is no classical analog for that. So it's a pure quantum mechanics. So with that, to put it simply, nuclear quantum effects are important in many situations, such as water, proton transfer reactions, bond selective chemistry. We can have photochemistry, light-driven processes, and even in some situations, such as polymerization and crystallinity, are affected by the nuclear quantum nature of the nuclei. And how to describe them, we have to worry about wave function localization, effects of the zero-point energy dipole moments, electronically non-adiabatic effects, tunneling, interference, quantum coherences. So out of those, maybe the first two can be modeled with semi-classical methods. The last two are called hard quantum effects. These are hard to reproduce with semi-classical or approximate methods. And then electronically non-adiabatic stuff, you really need quantum mechanics to do it properly. So I will refresh, maybe for some people, the kind of our only solution to the time-dependent Schrödinger equation, time-dependent Gaussians. Quantum trajectories, I don't need to talk very much, but I do have some colorful examples. And yes, thank you, Angel, for introducing them. And then I will talk about actual applications where we use quantum trajectories to describe experimentally observed phenomena. So we are doing quantum dynamics, which means quantum nuclei. We are solving the time-dependent Schrödinger equation, and if you are actually studying systems like we do in chemistry, we should worry about the system size. So here we don't have models, we actually have real molecules, atoms. You can solve the Schrödinger equation for the electrons that give you forces, and if you have a lot of nuclei or highly dimensional system, then we should worry about exponential scaling just of the wave function itself, let alone of how to solve the Schrödinger equation. So classical trajectories are, of course, very useful in many situations when we talk about nuclei, but not always. So what we can do for large systems is they use classical trajectories which excludes quantum mechanical effects, or we use Gaussian wave packets, which can include mild quantum effects. So in general, in my field of quantum molecular dynamics, people worry about time-dependent representations of wave functions. So what we want is like kind of having a caterpillar on a vehicle. So you want your representation to move along with a wave function that evolves in time. And we cannot solve the exponential scaling of quantum mechanics in general, so we have to find sort of our special regimes, use mass energy timescale separation whenever we can, and come up with methods that sort of describe the phenomena we are interested in. So the Gaussians, this is a general Gaussian. Why we use them? Yes, they scale very well with dimensionality because all we need is a complex matrix that's capital A here. And then the center of the Gaussian moves either classically or nearly classically if you're doing variational Gaussian. So you can have a wave function in many dimensions, and all you need are the forces along the trajectory and the Hessian of the potential energy surface. I also would like to point out that with this Gaussian, we do have extra terms in the phase, which is related to the quantum potential here, and also the quantumness comes in our quantum complex width matrix A here, which basically depends on the Hessian of the potential. So Gaussians are exact if you have a parabolic potential, and if you don't have a parabolic potential, surprisingly, they can be not too bad either. I was sort of impressed by this paper, which is already 10 years old, but there are other ones. And here we just have this one single Gaussian, and somehow it can provide us useful information about tunneling in the ammonia molecule. And, well, we've seen the ammonia molecule already, so that's an umbrella motion, and here is real experimental, I think, photodetachment spectra, and somehow the single Gaussian describes this motion in the what is potential double well for this molecule to make its inversion. So we have a number of sort of trajectory guided and related methods that are based on Gaussian bases, and Dmitry will talk about it. He is known for the development of the coupled coherent Gaussians, among other things. So we have multi-configurational Gaussians, which would be the method of kind of a version of the multi-configurational time-dependent Hartree method. We have David Ansatz. We also have just Gaussian basis function re-expansions. So the newest thing that's known to me is the Roth propagator. So there you represent your wave function in Gaussians. You first change your wave function, and then you re-expand what's left in a sort of new set of Gaussians. And there are very interesting applications that include actual electronic, complex electronic wave functions with that. So why do we want to use quantum trajectories? Well, besides all the theoretical and philosophical motivations, we would say that nuclei are nearly classical particles. Classical mechanics scales linearly, which is great. Trajectory framework is convenient because we can sort of mix and match, in a sense, in a large molecular system. Typically, quantum mechanics is important for some degrees of freedom when you have proton motion, or maybe you have an actual chemical reaction, some kind of large amplitude motion. However, other degrees of freedom can be viewed as spectator modes. They do interact with your system as far as energy flow, but they can be treated as classical particles. So quantum trajectories seem like a good match if we want to have a method which would say, okay, these hydrogens are quantum particles, but these carbons are not. And also, since we do have this kind of all the quantum mechanical behavior in the quantum trajectory framework kind of formulated as a quantum potential, we can put it in, we can remove it, and in this way, in some sense, we move between the quantum and classical regimes. And sometimes in actual applications, we just want to know if we should worry about the nuclear quantum effects in the first place. And here, even approximate implementation of quantum trajectories can be useful. So if you want like an accurate quantum calculation, you can think about quantum trajectories as defining an ideal grid in coordinate space, which is time-dependent and follows motion of the density, as is shown. Well, here we don't have the trajectories, but that would be kind of the typical behavior of a, let's say, Gaussian wave packet. So it moves in space, and also it's breathing in this case. So I can go to my quantum trajectories straight away, thanks to the previous talk. So the quantum trajectory equations of motion are derived from the writing your wave function in terms of amplitude and a phase. For me, what makes a trajectory quantum is if we say the momentum of this trajectory is a gradient of the wave function phase. So that's it. Now my trajectory is going to be quantum. You can massage your Schrödinger equation and switch to the Lagrangian frame of reference, which will tell me that the momentum of the quantum trajectory is driven by two forces, the classical force from the external potential and also the force associated with a quantum potential. And also we have the continuity equation. So here I'd like to know that once you go into the Lagrangian framework, it's the same as having a conservation of probability density within the volume element associated with each trajectory. And in fact, it's not important if you have quantum potential or you don't. What's important is that you have Newton's equations of motion, that your force is potential. Once you have that, you're going to have these non-crossing trajectories because of the continuity of equation. So if you add your quantum potential back, trajectories will not cross because the dynamics is still, you still have a potential force in this case. Another kind of general point is that all of the complexity of quantum mechanics is actually in the quantum potential right now. So that is the quantity I labeled U. It has h bar squared over m, which is sort of hand-wavy motivation why it might be a good thing to approximate if you're dealing with a nuclei, because we have large masses here. But if you want to have exact solution, this quantity, the quantum potential, will be complex in a sense of like NP-hard quantity complex in general. So therefore, I argue for making approximations to the quantum potential. But before that, I thought I would show you the colorful quantum trajectories for a change. So here we have scattering on a barrier. So I have this black set of trajectories representing a wave function as an ensemble. And then each new color is sort of a set of trajectories inserting in between the bifurcation point of the previous set. So this is Eckert potential describing H plus H2 kind of model tunneling. The barrier itself is marked by the horizontal dashed lines. That's half the height of the barrier. So it's interesting to see that it's not just like the front edge of the wave packet makes it over the barrier and the others are reflected. In fact, you do have interference, definitely, and reflection, internal reflection within the barrier. So on the right, I have tunneling from a metastable well. And once again, the colors kind of indicate the new sets of trajectories. And you can see tunneling out of the metastable well also demonstrates the interference phenomenon. So in a sense, we could say in general, tunneling is interference. So that's why it's hard. So now, on to approximate quantum potential. The idea here was that we want to make sort of simple approximations because we want the method to be applicable to large realistic systems. And maybe think about it like Hartree-Fock. It's a mean field approximation in electronic structure, which it's well defined. We know its deficiencies, but then we can also improve on it. So in this way, we have an approximate quantum potential that is accurate for the Gaussian wave packet. Here is this gradient of the amplitude, wave function amplitude over amplitude is sort of the working quantity that we want to approximate. If we say it's a linear function, then it's exact for a Gaussian wave packet. And it gives us a quadratic quantum potential. So the approximation itself is kind of limited by this functional form. It's set up in such a way that it conserves energy. However, we do not limit the form of the wave function itself to be a Gaussian. So we can still have bifurcation of a wave packet. And if our approximation is really inaccurate, we kind of go back to classical mechanics. So it can capture zero-point energy and moderate tunneling, moderate 10 to the minus 5 kind of tunneling, certainly not the deep tunneling regime. But also we understand, at least in principle, if we take more complicated bases that are, I would say, have to be tailored to your problem at hand, otherwise you'll be just lost in high dimensionality, then in this case we know how to improve the approximation and go towards exact quantum mechanics. So here is an application, and here I should thank Jacek Jakowski, who really interfaced quantum trajectories with electronic structure calculation on the fly. So it's a semi-empirical method that we are using here, DFTB, density functional tight binding method. We do have valence electrons and everything. And the first application we've done was hydrogen colliding with a graphene flake. So we're talking about, in this representation, 37 atoms. We tried like 85, and basically the main physics is captured already here. So this whole bunch of spheres represents the proton wave function. Collectively, we used 5 to 20,000 trajectories for the H atom, and the carbon atoms are treated as classically moving. So we are including the quantum potential only for the hydrogen here. So can we see the difference between dynamics with and without the quantum potential, and also can we reproduce the isotope effects. So in chemistry, isotope effects are all over. It's a tool of the trade to study enzymatic reactions. Let's say, so isotope effect is something we always look for. So on top, I'm showing 3 representative, so this would be here, right? I'm showing 3 representative trajectories of hydrogen kind of as they collide with the graphene flake at different collision energies. And these trajectories all are derived from a certain wave packet that's been evolved in time here. And the smaller panels B and C show what happens to the carbon atoms, once again, for 3 energies, and they are color-coded the same way. So basically, if our energy is very slow, the hydrogen is reflected. If our energy is very high, then the hydrogen, once again, is reflected, and that is because we shoot it really fast into the wall and just bounces back. But if we have some intermediate energy, then we have energy relaxation. The collision energy initiates motion of carbon atoms, and that is how the hydrogen atom can get stuck to the graphene sheet. On the bottom, I'm showing cumulative probability, and the dashed line on the left, I did not include the quantum potential into the dynamics, and we see that hydrogen tends to stick in the wide range of energies if you don't include the quantum potential. But if you do include it, then you have the blue curve. So it's absorption probability as a function of collision energy, and we definitely have a peak at about 0.3 eV of collision energy. On the right, the same data, but we have the deuterium atom rather than hydrogen. So for the same energy, deuterium moves slower, so we have kind of more chances to redistribute the collision energy, and the absorption probability is higher. However, you see that in both cases, they have the peak at 0.2 eV. And I guess in our community, people would say you can use it as a quantum sieve to select deuterium out of hydrogen. So that was a big calculation, but it demonstrates at least that we can account for the nuclear quantum effects, including the isotope effect in this case. So now it's a kind of more challenging system. I will tell a little bit about it. But as far as application of quantum trajectories, here my hydrogens that are attached to the side chain in this material are the quantum particles. So the question was, people at Oak Ridge National Lab can deuterate materials very accurately. So in this case, they have this polymeric blend. So you have this, what's abbreviated P3HT as your potentially electron donor material, and then you have this PCBM, which is C60 with some derivatives that can accept electrons, so they make a blend out of it. And basically, they can deuterate either side chains, right? These are the CH units on a side, or they can deuterate the main chain, or they can deuterate everything, or nothing, right? So now they can even deuterate more precisely. And the surprise was that they couldn't explain by any other means except for nuclear quantum effects is the difference in the open circuit voltage. So what happens here, you shine light, so your electron goes into excited state that happens actually on the thiophene ring here. And then it can be transferred to the PCBM. And if you set up your circuit, you can harvest this energy, and that's our photovoltaics, sort of basic photovoltaics. So why do we have change in the voltage if we deuterate the side chains where nothing actually happens? It's not where excitation of an electron happens. So in this case, we constructed a model of our system, and then we actually looked at the nuclear quantum effects of these CH stretches on the side chains, because that is where deuteration was. What we discovered that there are some fluctuations. The bond length for CH and for CD after deuteration is slightly different. If you think about the gap between the highest occupied, lowest unoccupied molecular orbital on the electron donor, these fluctuations lead to very small changes in the gap. However, it turned out that if you think about the unoccupied molecular orbitals through which the charge transfer proceeds on that scale, energy scale, the fluctuations of the side chains are significant, about 10% of that excited energy gap value versus like 1% of the standard homolumma gap on the electron donor. So with that, we were able to argue, at least explain the experiments that these are fluctuations affecting the unoccupied manifold of electronic states on the electron acceptor, and they affect the couplings, and this is how we have different open circuit voltage, whether we have deuterated species or pristine species. And deuteration on the thiophene ring, where actual electronic excitation happens, is not affected by this process. So on the right, I'm showing the 0-point energy, you can say, associated with the CH-CD stretches if we compute them, including the quantum potential. So here we had 39 quantum atoms, which is a lot. They were kind of easy in a sense. They didn't talk to each other. Each of them was separate, three-dimensional kind of quantum unit. So I also would like to mention that once you have trajectories, you can play with them and do different things. You can have evolution in imaginary time. I'm not showing here, but you can also add friction. And friction can represent something kind of physically relevant. But in this case, we use fictitious friction, and that is sort of the Schrödinger equation. So the way it worked, we have Newton's equations of motion. We know how to end friction there, just like in classical mechanics. And then we can rework our equations of motion into the Schrödinger equation, and this is what it is. I think it's known maybe in the area of stochastic Schrödinger equation, something similar, but here it's not stochastic, it's just fictitious friction. What it's doing, you have a large quantum system, you want to find the ground state. It's not simple. If you have, like in this case, 180 atoms per cell, so 540 degrees of freedom. But if you add friction, then you reduce the energy of your system and drive it to the ground state, just like that. So on top, I'm showing the kind of some slice of the potential energy surface to demonstrate it's very far from the parabola. And on the bottom, we have paracorrelation function that we obtained with quantum trajectories and also compared to information extracted from diffusion Monte Carlo, a quantum method. So they agree, okay, sorry, there is no correlation function from the quantum Monte Carlo methods because we don't have wave function. We do have the energy. So the energies agree well, and here we're just showing the paracorrelation functions for different isotopes, including fictitious isotopes. And the system here is helium. Okay. Now I have some time to talk about... Excellent, yes. I have some time to talk about the method we are working on right now. And it is inspired by the quantum trajectories, but they are not exactly quantum trajectories. So the idea here, we have the expansion of a wave function in terms of basis functions that are Gaussians, localized functions. And that's sort of the premise of the Gaussian MCTDH variational method. So you can say, I want my Gaussian functions to move according to variational equations of motion, and probably, that's the good instinct, and you can do that. What people have discovered, in particular, Eren and Burkhardt developed variational Gaussian basis functions method. Well, the discovery is those variational equations are very hard to solve. So basically, they had to make the method work, they had to reserve these kind of Gaussians for spectator modes, we can say, but to do actual hard quantum mechanics with standard MCTDH methods. So our idea was, let's keep the variational equation step for the Gaussians themselves, and instead use the idea of Bohmian mechanics to evolve them in time. Kind of no Bohmian trajectories give you this really compact representation of the wave function because of the continuity equation, right? So in this case, I would say we just define momentum of a trajectory according to the Bohmian prescription from gradient of the wave function divided by the wave function. We can also define the change of the Gaussian basis function of its width, right, to make them spread and avoid kind of them overlapping too much if they shrink, if they come close to each other. So these are the Bohmian ideas, and the expansion coefficients, those are coming from the standard variational principle. So that's the idea. We have basis functions, we have trajectories. They are, what I'm showing here are trajectories corresponding to the dynamics from one side of the double well to the other side of the double well. And out of those, we get a wave function represented in a through a time-dependent basis. So maybe I should say why we worry about double wells in chemistry. It's a representation of a reaction in condensed phase. So that's why we have a lot of models, and they are all about double wells. So on the left is our double well potential that represents inversion of ammonia. We have the snapshots of the probability density, and the idea, yes, we want to start on one side and without telling the basis functions where to go to move to the other side. And this is indeed what happened. We can represent all these fine oscillations in the probability density, reproduce the energy level splittings. Sorry about that. So now we are back to our double well, now coupled to bath of 20 degrees of freedom, and I hope at least you know 20 degrees of freedom is a lot. It's hard to do accurate quantum mechanics there. Our trajectories go, well, we have some that go from left to right, as they should, and we find that we can get reasonable results, reasonably accurate results, by using just one Gaussian to represent all those bath degrees of freedom. Okay, so we can look at correlation functions, and depending on the adaptability of our basis, we have more or less accurate results. The more adaptable the basis, the better, the more accurate the results are. I also would like to show this model that is somewhat different, also double well, and that is because we have exact results in this case, thanks to Dmitry. When I say accurate results, so at the end, what we are interested in something like a spectrum. So this is the power spectrum for the double well, including 20 degrees of freedom for the bath. And our simple implementation with 25, 40 basis functions gives reasonable resolution compared to the exact results. So our results are red dots in the middle, and the exact results are black on the bottom here. So Eric, how much time do I have? I really want to... Okay, great. Okay, so the method is implemented in Libra software. It's a platform to develop theoretical methods and played with theory that's initiated and maintained by Alexey Akimov from the University of Buffalo, and he is now and then also interested in quantum trajectories and is doing something about them. Right now we are working on non-adiabatic implementation, also hierarchical description of the degrees of freedom, variational determination of the Gaussian wave functions, and also I would say some maybe other ways to come up with optimal representations of the wave functions, and Vitaly Rasolov can tell you more about it if you ask him. So we have our quantum trajectories with Gaussians within this software, and now we are doing electronically non-adiabatic dynamics, once again extending Bohmian ideas, how to define the trajectory that describes dynamics on multiple electronic surfaces here. So far this is just the basic theory that we have, how we can define it, and our trajectories on a model system of two parabolic surfaces that are coupled. We have two sets of trajectories on different surfaces in gold and blue, and it seems to work for our standard models of non-adiabatic dynamics. So, in summary, if you don't remember anything, if quantum chemistry or chemistry is far from you, that we do have quantum particles that are not electrons or spins. We have nuclei. We can incorporate nuclear quantum effects into trajectory frameworks. They are really great for that. We know how to do approximate quantum trajectories and make use of them, and also use the ideas from Bohmian dynamics to develop more accurate methods, as we do right now with our quantum trajectory guided basis functions. So finally, I'd like to thank, of course, Bill and Valdir as organizers, and these are, So this is our meeting on quantum trajectories. I don't know, Bill, if somebody remembers what year, 2006 maybe, right? So we do have Bob Wyatt, right there, right? And some of you are here as well, right? David and Jeremy, right? And some other people. So quantum trajectories are still, I guess, evolving. I would say that. And with that, I thank my group and funding and you for your attention.
Wow, thank you for digging up that photo. That was 2008, actually. Okay. Yeah. Shelley Goldstein was also in that photo for the astute observer. So even then we were doing interdisciplinary stuff. So quick question for you about the graphene flake application. So I'm just curious, in the cases where the trajectories actually wind up giving you absorption, there has to be energy transfer. So how does that energy dissipate on the flake, typically?
Okay, so your carbon network starts fluctuating. Carbons are moving, right? So there is a...
Is there any kind of like obvious pattern or interesting dynamics there? Or?
After we published the paper, actually there were experiments. They called it, it's a real sound wave. It's literally like you drop a stone and wave goes on. So that was experimental visualization of what's going on, right?
Okay, thanks.
Mm-hmm.
So I'm a little confused about something. So Gaussian wave packets, in some sense, already contain zero-point energy, and it's through that extra term in the phase factor, isn't it?
Okay, so there is a phase factor, right? That's like Maslow's index.
Yes.
Yeah. Right. So that's the case of the coherent state. But if your Gaussian is not coherent, then it's more complicated. And you can show that it's related to the trace, whatever. It's related to the quantum potential in general. Right.
So I guess my question is, can you get zero-point energy with Gaussian wave packets, or does one have to use your method to get the zero-point energy? How does the zero-point energy show up differently between the two different approaches?
Okay, so Gaussian wave packet is a solution in a particular case. So if all you have is a Gaussian wave packet, you need to include that phase. You have to compute it. So what we were showing, like in an application, right, for the CH stretches, so that was actual quantum potential that we used to evaluate the same effect. But the main thing really was that you have to have your wave function localized, and there is energy associated with its phase, with its shape. So that's our zero-point energy. And I mean, we use it loosely. It's not ground state necessarily. It's just energy associated with the shape of the wave function.
Okay.
Thank you. Very interesting. Sonia, and when you have this calculation of hydrogen on graphene, right? So do I understand correctly that you introduce quantum potential essentially by hand, like additional term in the molecular dynamics force field?
Yes.
Right?
Yes.
Oh, that's great, actually. Yeah? I like it.
Oh, thank you. It's more curiosity, really. I did some molecular dynamics in my undergraduate. So I'm wondering, you mentioned the 20 degrees of freedom. Is there any quantum algorithms or things that will be computed on quantum computers on this horizon?
Not yet. But I heard from our program director we shouldn't worry about it for the next 50 years in general.
Okay.
Right, so unless you have some simplification in the structure of the wave function where you can use maybe tensor trains or whatever, you know, it's very sparse somehow. There is no simplification.
Okay.
Any last questions? Okay,
thank you, Sonia. It was really interesting. Now, this is connected to what Dmitry asked you. So when you have, for instance, this graphene flake, so you, if I understood correctly, you introduce atom by atom, plus the electrons and whatever, everything there.
Yes.
So, and the interaction, is it pairwise between
Coulomb,
every atom or?
Coulomb interaction, yes.
Coulomb interaction?
Everything, yes. We solved Schrödinger equation for the electrons.
Okay. Plus the approximated quantum potential.
Yes.
How long does it take this? What's about the time consumption and also about the stability? How much does it take one of these calculations with so many degrees of freedom and trajectories?
Okay, I think one calculation for an ensemble would be like 1 week, but these calculations are old. That was 10 years ago, and we use a supercomputer for that, yes.
So
but it's electronic structure.
So
yeah.
do you have parallelized codes and all this stuff?
Yeah.
Okay, and how does it work? I mean, does it work nicely? Because, I mean, you need to introduce many degrees of freedom that, in principle, they are non-locally interacting.
Okay. Well, the DFTB just gives you essentially energy and gradients. So it's like if you had potential energy surface, we didn't really have issues with that. I mean, it might be not very accurate, but we tweaked some parameters to match like maybe special scans of the potential energy surface. As far as molecular dynamics, that was no issue at all, because approximation is very simple. It's just linear quantum force. So it's just like you have to run all your trajectories at once, and now and then they actually exchange their locations, and that's all you need. So basically just positions of the quantum trajectories.
So for the more recent calculations, how much time do they take? More or less?
It all depends on the level of electronic structure you're doing. So I would think, 10 years later, it should be 1 day instead of 7.
Okay, and compared to MCTDH?
That I don't know.
You know.
Yeah. But I mean, in MCTDH, the issue is the actual dynamics. They have more accurate quantum dynamics, and they don't do electronic structure. For us, the cost is electronic structure.
Okay.
Yeah.
Okay, thank you.
All right, thanks. Could you send me this picture? I didn't realize I'm actually in this picture. So okay, cool. Thank you. Our next slide is Dmitry, and that will wrap up our thing today. Then we can go off and have dinner. This massive amount of steak or meat fest that Bill has promised us. Take the opportunity to stand a little bit, stretch. This is the drawback of turning 60, right? You have to stand up every once in a while. Okay, go for it.
All right, thank you very much for the invitation. It's actually a fascinating conference. Yes. Thank you very much for the invitation. It's actually a fascinating conference. There are some talks which I kind of expect, but there are some, and I know what people are talking about, and there are some talks which are completely new, and also historical talks are great. So it's really a fantastic conference. Thank you very much. And also I want to thank Sonia for introduction, because I'm going to be talking about similar things. Also, I'm a chemist as well, but I've tried to remove most of chemistry from my talk, so make it more about physics. And I will be talking about basis sets of trajectory-guided coherent states for multi-dimensional quantum dynamics in physics, mostly, almost nothing about chemistry, but there will be a little bit of chemistry. So, and what is the central problem of computational quantum mechanics is what people often call exponential curves of quantum mechanics. Basis set which you need to perform simulations in quantum mechanics scales exponentially with the number of degrees of freedom. If you have 1D problem, you probably get away with like 10 basis functions or grid points. If you have 2 problems, you need 10 by 10 grid points. And if you have 2 quantum particles in 3 dimensions, it's actually 1 6-dimensional object, not 2 3-dimensional objects. And this is really, this kills very much all straightforward methods of quantum dynamics. But in the recent, like in 20 years or so, a lot of people put a lot of effort into developing methods which work in many dimensions. And there are several ideas, and one of the ideas is to use trajectory-guided basis sets. And on the lowermost picture, so as you can see, if basis set can follow the wave function, then you can economize greatly the basis set size. And also you can often select those basis functions randomly. And Monte Carlo always scales much better with dimensionality, ideally as m squared. There is a price for that, but scaling of Monte Carlo is much better. And what are those? What I'm going to be talking about is about what are those wave functions which we guide, and most importantly, how we guide them. What are the forces which guide those trajectories? And the wave function is which we are using is Gaussian function, Gaussian basis function, and this basis function is actually, as you can see, it's a little de Broglie wave. So there is this I over Planck constant and momentum. So it's the de Broglie wave, which is kind of with the Gaussian envelope. So the de Broglie wave in red, and this is the envelope. And there is a parameter gamma, which determines the width of this Gaussian, and there are several options how you choose it. But in my case, it will always be constant. So we call it frozen Gaussian because of that. So Sonia used the term thought Gaussian, which can spread. But I will be only talking about frozen Gaussians. So gamma is a constant. And what's important is that this Gaussian wave packet is characterized by coordinate q and momentum p. So it represents phase space point. So it's a point in the phase space. In a way, it is it's phase space object. And often people use, instead of using Q and P, people use Z, one complex number which has Q as its real part and P as its imaginary part. And also it includes width and Planck constant. And in many dimensions, you just have a product of those Gaussian in each dimension. So this is the wave function I'm going to be using. And why do people use this Z notation instead of P and Q? So the reason, it's actually a physicist's choice of notations, Z notations. The reason is that Z is an eigen value of annihilation operator. So if you act with an annihilation operator on this Gaussian Z, you get Z times Gaussian. And so that's what it is. And remind you that Z is actually a combination of Q and P, and therefore wave function as a function of Z represents a wave function in phase space. And basically at the second page of every quantum mechanics textbook, we read that you cannot have P and Q in your wave function. It's either P or Q, but that's not entirely correct. So you can have these wave functions in phase space as a function of both coordinate and momentum, but you have to treat it in a special way. So the uncertainty principle works differently for these wave functions. Yes, and what's also important that Z can follow classical trajectories. Both P and Q can change with time. So I said classical trajectory, but it's not necessarily true. It can be all kinds of trajectories. And I will show some examples. Also, what's important is that Z is a linear combination of all quantum states of harmonic oscillator. So, and coefficient in front of quantum state n includes Z to the power of n and some factorial. This is what is known as Glauber coherent state. Why is it so? Why is it so good? In fact, coherent state was first found by Schrödinger, who was looking for an object which connects quantum mechanics with classical mechanics. And what's important, so if you look at harmonic oscillator, if you take this Z, which is called coherent state, so the exact solution of Schrödinger equation is represented by this coherent state moving along classical trajectory. So it moves in the phase space on this circle like this, just like a trajectory of harmonic oscillator in phase space, and the only addition is this little phase factor next to it. Yes, and of course, I mean, okay, harmonic oscillator, great, but we often, it's not the only problem we're interested in, right? So what if we have something more complicated than harmonic oscillator? And the recipe is that we cannot get away, of course, with one single coherent state, not for a long time, of course, but maybe a small ensemble of those Zs, of those coherent states, a superposition which serve as a basis set, can represent very economically wave function. And this is an example of how it works in many dimensions. So this is Hennen-Hayles model. In this case, it's 18 coupled harmonic oscillators. So these are harmonic oscillators, and there is a pretty non-trivial coupling between them, pretty non-linear. And these pictures represent autocorrelation function, projection of the wave function on itself at 0 time as a function of time. So the wave, it starts with 1, and then after a period, after 2 pi, it comes back, and it gradually decays because it's not just harmonic oscillator, the wave function spreads, and when it comes back, it's less and less like it was at 0 time. And these two pictures are obtained with two different methods. One is called coupled coherent states, and another variational multi-configurational Gaussian. So I mentioned both these methods. And it is compared with multi-layer MCTDH, like a benchmark, multi-configurational time-dependent Hartree. It's another method which is based on completely different principles, but it works also for many dimensions. But as you can see, this idea seems to be working, and I will talk a little bit more about this slide later. Okay, so let me show you some examples and how we actually get trajectories from, how we derive them. Let's consider the first example, just one single Gaussian, one single Z with an amplitude in front of that, just one single basis function. How we work out equations of motion of this, for this wave function. First, we introduce parameters of this vector. Parameters are amplitude and Z, and it can be multidimensional, it can be many degrees of freedom, so it's just several complex numbers. And then the next, we use variational principles. What is variational principle? This object is called quantum Lagrangian, so it's a wave function which surrounds this Lagrange operator. And we can do some algebra. We got out how we work out how it depends on the parameters. And then what we do, we just use Lagrange equations, just like in classical mechanics. And this is what we end up with. So these are the equations of trajectories. And essentially, it is a classical equation. The only difference is that the Hamiltonian is averaged over Gaussian. And this is what David mentioned. Gaussians take into account 0-point energies. So basically, the effect of that is that all wells become slightly more shallow and all barriers also become slightly lower. So, but it's essentially classical. It's always classical potential. And for the coefficient A, you can show that this is initial amplitude multiplied by the standard phase factor, which includes classical action. So that's how it works for one single Gaussian. So let's now consider an ensemble of Gaussians, of coherent states. So a superposition of several of them. And you can actually apply exactly the same idea. You have a bunch of parameters. You treat all complex numbers in here on equal footing. So you have a bunch of parameters, amplitudes, all those Zs, which describe trajectory Lagrangian is very complicated. That's why I wrote it in very small letters. Don't worry about that. But when you apply Lagrange equations, this is what you end up with. So this is the vector of parameter time derivatives, the vector. On the right-hand side, it is Hamiltonian averaged over the whole function and the partial derivatives, with a vector of partial derivatives. But there is this matrix, omega. Omega turns out to be a very big matrix. And also, even worse, it's a very bad matrix. So it has very small eigenvalues, almost zero, lots of them. And as you can see, you have to solve, it's a system of linear equation. Matrix times vector equal to the right-hand side, right? So if matrix is bad, it's a numerical nightmare to treat it. But this method is called variational multi-configurational Gaussian. In principle, it is the best possible solution. It is supposed to be the best possible solution. Which sense best? I don't know which sense. I'll show you some advantages of that as well. So this is something which, well, variational multi-configurational Gaussians. But then you can also do something else. You say, okay, I don't want to deal with this awful matrix, so why don't I choose my trajectories as if as optimal trajectories for single Gaussian, like in the first example I've shown you. This is it. But then I can work out Schrödinger equations for the amplitudes. After all, I can choose whatever trajectories I want, and it's still exact quantum mechanics. I'm not making any approximations. Yes, and then you get actually pretty nice equations. Yeah, so this is optimal trajectories from variational principle applied to single Gaussian. And then the matrix is simply the overlap matrix. It's small. It's not huge, as in the previous slide. And additional bonus is that you can show that the right-hand side contains this term which is always very small. You can show that it is very small. So right-hand side is almost zero. And numerically it's very well because everything changes very smoothly. You can have big time step because right-hand side is almost nothing. Yes, and this is called coupled coherent state. Coupled coherent states. And also you can modify it and you can use just classical Hamiltonian instead of that Hamiltonian averaged over Gaussian. Right? So, but in many cases it's almost the same, almost pretty much similar. Yeah, but also the matrix is nice. That's the main thing. And I'll show you some results. So this is, on the left, this is Morse oscillator. So the blue line is this almost classical trajectories of trajectory of Morse oscillator in phase space, this kind of X shape as it is supposed to be. But variational trajectory is this horrible, well, it's very complicated, has very complicated shape because all trajectories push each other. This one is independent. And variational trajectories push each other, and that's why they're complicated. But both methods nevertheless give excellent result. So on the right, there is real part of autocorrelation function for two-dimensional Helmholtz model. And the crosses it's two-dimensional. You can do whatever exact quantum mechanics, numerically exact crosses are the benchmark, and the lines in both cases, VMCG and CCS, they reproduce everything perfectly well. All this complicated structure of the autocorrelation function works very well. And notice that with variational multi-configurational Gaussian, we get away with smaller number of basis functions than with CCS. Because trajectories are actually more optimal, they guide basis set better, closer to actual quantum dynamics. You need fewer of them, but there is a price to pay. You need very small time steps, and you invert a very big matrix. So numerically, it takes a lot more time to get that result. But both methods can be done for more degrees of freedom. This is 18 coupled oscillators, and this parameter of coupling was actually adjusted to some real molecule, but no one remembers what that molecule was, but there were claims that this is real molecule. Yes, so, but both methods, CCS and VMCG, work for many degrees of freedom and reproduce MCTDH nicely. And I must say that CCS is, in terms of CPU time, is much easier, but still both work. So why I want to show you pictorial image why all those trajectory guided methods work. Think of this rock as a static basis function, and quantum waves come and hit it hard. And this is the image of coherent state moving with quantum wave. And this is actually a very accurate image of a basis set of coherent state which are driven by the wave. Because, and why is it accurate? Because the classical trajectories are actually orthogonal to the waves, right? So like aconal and things like that. So we know that trajectories are somehow perpendicular to the wave one way or another, more or less. And this is very accurate image of what's going on. Okay, so I'm actually a chemist, and usually I have at this point a very long, bunch of slides about chemistry, but I cut that out. But I still want to show something. In chemistry, we often deal with more than one potential energy surface. For example, in photochemistry, we deal with more than one state. So we have a photon which takes a molecule to the excited state, and then the wave function, the nuclear wave function, moves, and in the crossing point there are hops from one surface to another, and this is photochemistry, right? And how we do that? And we actually use similar idea. We have trajectory guided basis set, but it can actually bifurcate in those crossing points. So this image gives you pretty much the idea of what we are doing. And what are the trajectories? So again, pretty much the same idea. You can use variational trajectories. You can use more or less classical trajectories. But what you can also, the optimal, from my point of view, and I think we have shown that Ehrenfest trajectories are very efficient. What are Ehrenfest trajectories? When you have more than one potential energy surface, you can drive your trajectories by some sort of average potential, which is averaged over wave function, over contribution of the wave function at first and second electronic state. You have nuclear Gaussian dressed with the electronic part, with combination of electronic states. So these are called Ehrenfest trajectories, and they are simple and they have certain quantumness in them. And we have tested convergence of this Ehrenfest trajectory. So how exactly it works? So you have nuclear part described by coherent states, by Gaussians, but each of them is dressed with a combination of electronic states. And sorry, we have actually so this is we call multi-configuration Ehrenfest version 1. So each of these terms we call Ehrenfest configuration. So each of those Gaussians dressed with electronic states we call Ehrenfest configuration. But we have also another ansatz. In this case, we normalize Ehrenfest configuration, but to couple them, we have to add another amplitude in front of them. So, so we call it multi-configuration Ehrenfest version 2. How do we choose trajectories to guide this basis? And multi-configuration Ehrenfest version 1. So we assume trajectories of Z to be Ehrenfest trajectories. And they are coupled each one of them is coupled with A1 and A0 in its own, of the same configuration. But the amplitudes A1 and A0, they are coupled across configurations. Yeah, okay. So we have Ehrenfest trajectories, this and this, but we also have coupling across configurations. So this multi-configurational Ehrenfest version 1. Configurations are not normalized themselves, only the whole wave function is normalized. But then multi-configurational Ehrenfest version 2 works slightly different. They are coupled through these amplitudes A1 and A2, but each of the configurations is driven by its own Ehrenfest trajectory. And if we were doing variational multi-configuration Gaussian, then everything would be coupled. Lots of coupling, I'm going to show you. Yeah, lots of, everything is coupled. Yes. Now, numerical test spin boson model. So two parabolic electronic states, but these parabolas are actually multidimensional, like tens or even hundreds degrees of freedom. So it's multidimensional, and basically I gave my student this problem. So we knew that version 1 converges very well, and I told him, yeah, now test converge MC version 2. So, and what this, and he came and he said, yes, oops, yes, that's right. MC version 1 converges very well, there it is, compared with MCTDH, but MC version 2, I can get it, there must be a mistake. I go and fix it. And he went to fix it, and he worked and worked and worked, and in 3 or 4 months he comes and he says, no, there's no mistake, it doesn't converge easily. So how you converge it? So this was Chris. And eventually Chris managed to converge it using sophisticated sampling techniques. So he have used basis sets which are made of these trains. So the train basis set has a set of Gaussian which follow each other on the same trajectory. And it costs you almost nothing because you only need to know the trajectory for the first one, right? And the others follow with time delay. And also those trains bifurcated in the crossing point in the process which we call cloning. So each trajectory produces 2 clones. And when he did it, he managed to converge. This is what he was without sampling techniques, and this is where he was using sampling. So this is the difference in population between 2 and 1, right? So we start at state 2, and then we end up somewhere in the middle. Yes, basically, what is the conclusions from that? MC version 1 converges very easily. And why is that? Because there are some quantum forces. Because configurations are coupled with each other, there is coupling across. The Ehrenfest trajectories talk to each other. And this actually helps to move to the basis in the right place. And some quantum forces are good, but not all of them. If you try to do variational, no way you can get it done here. But multi-MC version 2 is much harder to converge, and with all tricks, you can converge it. And you may ask me, okay, you have this MC version 1, it works, why would you need MC version 2, which doesn't work that well? And the answer is that you can actually implement it for real molecules in Cartesian frame, and instead of having predetermined potential energy surfaces, you calculate them on the fly. You run trajectories, and each time step, from electronic structure, you get potential energies, forces, everything. And you can use exactly the same tricks we have used for spin boson. And this has been implemented in several codes, and people have done molecules like those shown on the picture. And this is multi-configuration Ehrenfest, which is between standard Ehrenfest and surface hopping, and this is where exact quantum result is supposed to be, actually. And as you can see, also it converges much nicer. Yeah, so MC version 2 is used in real chemical photodynamics. Now, if I have few more minutes, I will. How much time do I have?
7 before you.
Huh?
Technically 12, but 7 before I give you the 5 minutes.
Oh, okay. Oh, wow, that's a lot of minutes. So I will talk about more application of coherent states, and I will be talking about applying Gaussians in a different context, not in the context of nuclear motion, and also applying other types of coherent states, which is the most interesting thing, actually. So different context. So this is one of the applications which we have done. It's electron dynamics in laser field. So you take helium atom, put it in the strong field, and the field is so strong that it modifies the internal Coulombic potential, and it can take electron outside, ionize the atom, and can take. But then the field reverts, and potential energy. Now the field pushes it back. So the electron comes back, and it can interact with the atom again, and lots of interesting things may happen. What happens in this process? So this is the cross-section, ion signal of single ionization and double ionization. And triangles and red dots are our calculations, and blue dots and crosses are experiment. And what we actually used exactly the same approach, but to the electrons. The only difference, we anti-symmetrized our coherent states. This is 2 electrons. This is helium atom. So we have 6-dimensional problem in Cartesian frame with 2 electrons. We use Gaussian coherent state, anti-symmetrized, and we run that. And the advantage of this approach is that you really can see what's going on. So on this frame, there are some trajectories of electron. And have a look at this one, at this one, number 2. So the first electron starts moving in the electric field. So these oscillations is due to the pulse, the electric field pulse, which moves electron away and back to the atom. And then at some point, it hits the second electron and kicks it out. So double ionization happens via this recollision. Almost all trajectories which are responsible for double ionizations are like this. So you really see that. But it's not just trajectories. So all our basis functions carry proper quantum weight. So it's, in a way, it's almost fully quantum calculations. There are some cheating. There is a little bit of cheating, but at the end of the day, it is fully quantum. And this is 780 nanometer pulse, 120 femtosecond, 48 periods. So you cannot do it. It's not a highly dimensional problem, only 6 dimensions, but because it's a very long pulse, a very big amplitude of electron motion, standard grid must be huge. It's a very difficult problem. So another application, Bose condensate, so clusters of Bose atoms, so they can tunnel from one well to another. And in second quantization, bosonic systems are mapped to harmonic oscillators. So the harmonic oscillator Hamiltonian describes, in harmonic oscillators, you basically have, these oscillators describe populations of basis functions. So it's called second quantization, right? And, okay, so there's a bunch of harmonic oscillators, whatever they mean. We still can take our Gaussians and apply this to these coupled oscillators. And this is what we have. This is the motion of Bose condensate, several hundred atoms, I think, in the trap. And again, we compare it with MCTDH, almost identical to MCTDH. And it's, in a way, much multi-configuration time-dependent Hartree is kind of like golden standard in quantum dynamics, but we chase it and we nearly catch up with them. Yes, and now other types of coherent states. In fact, I have been talking about I was talking about Gaussian coherent states, right? But there are other types of coherent states. And here comes some São Paulo connection. Marcos de Aguiar from Universidad de Campinas, right, from São Paulo. He sent his student, Adriana Grigolo, to Leeds, and Adriana did brilliant work, which at that time I actually didn't understand, I didn't appreciate. But now this work is the basis for almost everything we are doing now in this direction. And so what Adriana said, he said that there are other types of coherent states, and they actually, you can use the same machinery, but for other types of coherent states. And now this has been picked up by other people like Frank Grossman. He's using the so-called SUM coherent states, and we have been using coherent states of two-level system. For example, if you have several two-level systems, there is it's called SU2 coherent state, and like a bunch of qubits coupled with each other, right? So they describe qubits you can describe by the so-called SU2 coherent state. And I'll give you an example of how to do it, and this is going to be electronic structure with the help of coherent states. So you have electronic structure Hamiltonian. It has also creation annihilation operators, like this is Coulombic terms. So everyone who knows a little bit of electronic structure looks familiar. And there is a big problem with electronic structure. In electronic structure, we always have a bunch of spin orbitals. Like here, each box is a spin orbital. I have 6 spin orbitals and 3 electrons distributed over these spin orbitals. And if you distribute electrons in spin orbitals, this is called configuration. But there are many, many ways how you can distribute electrons over spin orbitals. And this is this big factorial number. And this is another manifestation of the fact that many-body quantum mechanics is very difficult. So, and if you want accurate electronic structure, you need to take into, your basis becomes huge very quickly. So you cannot do it without some simplifications. And here is our suggestion. We call it zombie electrons. So why zombie? Because we put electron on each spin orbital. Number of electrons in our case is equal to the number of spin orbitals. But electrons can be dead or alive. And this is described by what is called SU2 coherent state. And this SU2 coherent state is a combination of dead and alive, of two states of the electron on each orbital. And then you can write a product, which actually has to be anti-symmetrized product when you talk about electrons, and you can write your wave function as a combination of this multidimensional SU2 states, right? And it is actually very similar to the SU2 state is a combination of 0 and 1. It's just like Gaussian. It's a combination of all quantum states of harmonic oscillator, but here we have only 2, so it's only 2 terms for SU2 state. And okay, and then you can do with this wave function whatever you want. With this ansatz, for example, you can work out the ground state by propagation in imaginary time. And this was done by my PhD student and postdoc, by Oliver and team. And this is what they get. So you select this random, you select all those SU2 states randomly. And you get something interesting, so you can work out your energy and norm, but you see that, in fact, we have 6 electrons, but we have contribution from 5 electrons, from 7 electrons, from 4, from 8, from all electrons, from all possible. So these SU2 states, they don't really preserve the number of electrons. But with some clever sampling, you can actually reduce contribution of this slash of garbage, and you end up with pretty accurate ground state of lithium-2 molecule in this case. And see Michal's poster, he will tell you a better way how to do it, so which preserves electrons. Yes? And that's the end. So my conclusion is coherent state basis can be very useful for multidimensional quantum mechanics. Some quantum forces can be very useful, like in multi-configurational Ehrenfest version 1 or VMCG. If you're careful, you still can make use of it. So some quantum forces can be important, but you have to be careful with them. If you take too much, it doesn't work. And here is lots of people who contributed. Dima Machov was particularly instrumental. Chris, James, Kenichiro, and lots of my collaborators. And I want to thank you. Oh, and the main thing, it all started when I was a postdoc in Oxford, and this is Mark Child, who was my supervisor, and I want to thank him as well. And thank you very much for your attention. So we have a few minutes, right?
We have like 5 minutes for questions, and then so you're.
So your guiding trajectories are obeying classical mechanics, right?
Well, so they obey if you have one single electronic state. So the best choice, in my opinion, is this quantum averaged with correction for 0-point energy. So that's what we use in coupled coherent states.
So how does tunneling come about?
Yes, if you have tunneling, you have to put them by hand in the opposite well, and they will talk to each other and transfer amplitude.
Okay, so tunneling doesn't, in a sense, it doesn't come out naturally from just the independent
Yes,
motion.
it doesn't come out naturally.
Okay.
That's true. Okay. But when you do non-adiabatic dynamics, when you do MC version 1, you can actually do pretty quantum cases when trajectories push each other, but not to the extreme. They push each other, they're still stable, but there is interaction between them. And this actually works much better for tunneling cases. But when you do an MC version 2, when they're just Ehrenfest trajectories, it's basically analogous to this averaging over Z, right? So, but we average over two surfaces as well. In this case, we have this procedure which is called cloning. So when they split in the, and again we introduce it by hands, but this is really very important for description of, strongly tunneling cases.
You showed the nice results for the double ionization of helium. I'm wondering, have you tried looking at strong field tunneling ionization and high harmonic generation?
We have looked at high harmonic generation, but with high harmonic generation, it's actually more difficult. For high harmonic generation, you have to have very accurate wave function, really numerically extremely accurate. For this double ionization, it's logarithmic scale, right? So you have this, you basically reproduce the shape more or less. But for high harmonic generation, you need very, very accurate representation, a very, very accurate, numerically accurate wave function with really many digits. And you cannot really achieve that with randomly selected basis function. You have to use additional tricks like reprojecting it, but you don't really have much advantage comparably to standard technique. No advantage at all. Mm-hmm.
So David asked my question about high harmonic generation, so now I'm going to ask his question. So David asked my question about high harmonic generation, so now I'm going to ask his question about Ehrenfest. So I'm sure you get a lot of questions in front of chemistry audiences when you say Ehrenfest is the best, particularly if you have surface hoping people in the audience.
Right.
I mean, do you have to justify that actually it is better than this idea of...
Yeah. Standard Ehrenfest, which is mean field, it's not the best. It's only multi-configuration Ehrenfest. When you have many of them, that's the best.
Okay, that's
and with all those tricks of cloning and trains and with all those sampling tricks, it works. But not without them. And you need many Ehrenfest trajectories together.
Is there a fundamental or like deeper reason why that is, or just
yes,
like empirically you learn this by
we
messing
learned
around?
Empirically, but I think the reason is that all trajectories misguide the basis set. So when you have Ehrenfest trajectory, you pass intersection, and you need to split your wave packet. how do you split your wave packet? You need to do it by hands. So I probably have a slide here, which I actually cut out. Maybe, okay, so there's lots of slides which I have thrown away, but I'll try. Yeah, so the next one, yes. Oh, no. Is it? No. Oh, yeah, that one. Yes, when we pass through the conical intersection, so we start on this one, right? So one amplitude is 1 and another is 0. Then we pass intersection and then they both become non-zero. And then we create two trajectories, two clones. We add 0 and we add another 0. We do nothing. Yes, but then we create two trajectories, one on the first state and another on the second state. And this is we call cloning. And this is actually analogous to spawning, which Don does, but it's a kind of, I think you accept that as well, that this is a better way of doing spawning, simpler way of doing spawning. And we actually have, when we suggested that he is a co-author on that paper. Yeah, so, but this is really, this splits the wave packet between the two electronic states and makes it real quantum.
Okay.
But you do it by hand.
And then I had another quick question. So for your 2D Hennen-Hiles, where you showed the VMCG trajectory that was going all over the place, are you sure that's the real trajectory, or because that's a case that's numerically difficult to analyze?
Yeah, well, it is real because it gives the good result for our calculation.
Well, I did notice that.
So,
but...
and basically, also, I think you need fewer of those trajectories than coupled coherent state trajectories. So it means that in a way they're better. So they guide a wave function better. But there is, like I said, there is a price to pay. They're very, very difficult to calculate. All those singularities, all those zeros in the denominator. Horrible.
I wonder how sensitive it is to every little crenellation and so forth.
Yeah, that's a good question. I mean, I don't know, but apparently, they work.
Yeah. Okay. All right. Thank you.
You need few of them, so in a way they're better.
Okay. Any last question before we declare the evening closed? One more. Okay.
I guess I'm not going to ask you about the high harmonic generation because I think that at least there are 3 people here interested in it, but you have already given the answer. No, regarding the Hennen-Hiles, have you checked that there are no effects due to the chaotic dynamics involved in this? Because
no, we were not focused. Yeah, Hennen-Hiles is a favorite object or favorite system for people who do counts. So there is a regime, non-chaotic and chaotic regime, and it's a big issue for mathematicians. They love that, but we were not really focused on that. We just wanted to get the result for many degrees of freedom. I kind of suspect that we are in the regular regime because we have kind of long survived coherence. If it was chaotic, it would probably decay very quickly.
Well, but actually, in your pictures there was kind of exponential decay.
Yeah, there was a decay, yes, but it was not. I would say that if it is truly chaotic, it would be much faster decay. But I
don't remember. I mean, Heller, I think that he has some results also with the Gaussians and this stuff. I think it is from the 1970s. Something or also.
Yes.
Okay, and another quick question about the Bose-Einstein condensates. Have you tried to check? I mean, you have there shown the double well, but have you tried to split that mathematically the condensate and then to make it recollide again?
So right. So we actually haven't done tunneling. We only have done dynamics in one well, and but we are working on it. So this is what Michal is doing. And we actually have much better ways to do it because you need coherent states which preserve the number of Bose particles or number of electrons. So, and we know now what they are. but we didn't know it that time. In fact, you know.
Just out of curiosity, how does it compare to the rest of the test group?
Well, it's in principle it has to be exact quantum mechanics. There is such thing as MCTDH-B, bosonic MCTDH, and they.
I guess like in your case, they say I know what the mean field theory.
Yes, definitely. Okay, we haven't done that, I admit, but MCTDH people have done that, and they've shown that this is different. But you know, MCTDH is such a big community, right? And we are just a little team. But the fact that we have done a lot of things tells you that these methods are actually easy. In a way, you cannot write. You cannot ask your PhD student to write MCTDH code, right? But all my students and postdoc wrote their own coupled coherent states or multi-configuration NFS code. And it's really, you know, it takes a student, you know, like a month, and the postdoc writes in a week. So, and yeah. So we are chasing MCTDH, and that's great chase. It's really a lot. Yeah, it's a lot. It's really very useful to have them ahead of you, and you know what to do.
Excellent.
Our advisor has a final announcement.
All right, I have some good news and some bad news. The good news is we have 2 buses that'll be taking us to dinner. So everyone who's going to dinner will get a free ride to the restaurant. The bad news is what happens afterwards. There may be 1 bus afterwards for speakers to take them back to their hotels. Everyone else, you know, you're getting a free meal. So you'll be on your own afterwards. But I mean, Ubers are really easy. You've probably already explored this on your own at this point anyway. So, all right, we'll see you over at Bovinus.
All right.